వచ్చేసి కింద స్టేడియం మీద చెప్పకూడదు.
towards them, but they were giving talks and then they were kind of willing to interact with people. I mean, you name the Nobel laureates who were visiting us. So that is the kind of background from which the school comes, and I'm very happy that Shamu was very insistent that we should celebrate it, and then we had a very, very narrow window of opportunity where the IOE funds
average P, you can, now comes the next thing. But you can also calculate, it is, quantum mechanics requires you to know all the moments. So what happens if you calculate the x square average and its time dependence? For this free particle, you can actually do it. And you can go ahead and do it for every power of x and every power of p, and you go on doing it, and at the end of the day, if you have all the moments known, you can calculate what the wave function is, and that is what you can do, and you can immediately get back the standard textbook answer of this problem, which is this. So the point which I am making out of this trivial calculation is that if I don't stop with Ehrenfest at just, don't give up at the level of saying that I take a first derivative and at most a second derivative and stop over there, and that's, you can go ahead, and who asked you to stop? Things were at that time probably very difficult and Ehrenfest, but the point is that, all right, I mean, I can take Ehrenfest and calculate all the moments. It's not easy, but you can do it. And you can do it, and as this free particle example shows, that I can very easily calculate, being a free particle, things are easy, and you can easily calculate all the moments, and you can get what Schrödinger equation gives you, that given the wave function at time t for this free particle, what does it look like at a later time, and this is what it is, and Ehrenfest gives you exactly that. And you can do the same with simple harmonic oscillator, and you can get the propagation. Textbooks do it, as I said, with Schrödinger equation. You can calculate moments and get it also with. So, but then you say, all right, I mean, you are doing some extra work, and what's the point? I mean, we can get, so there is an answer to that as well. So what if I change the potential on you? What if I say that, look, I don't want, my oscillator is not your simple harmonic oscillator. My oscillator happens to be like x to the power 4. And if you say that, can you get x oscillator where there is no x squared term and there is a x to the power 4? Go and look up the mechanical engineering literature. They can arrange rods and the particles in such a manner that you can develop any potential you want. So they can get rid of, by adjusting these rods and these bullets to get rid of the springs and bullets. You get rid of the x squared term with some configuration, and you can get the potential starting with x4. So it is that, all right, what if somebody gives me a potential x4? Now you want to do quantum mechanics, and you are stuck because you are not going to be able to solve Schrödinger equation and calculate all the eigenvalues and eigenfunctions. You can do it numerically. That's always there. But can you do it as a calculation? And as soon as it is at x to the power 4, the potential, you try to use Schrödinger equation, it is not going to, you can't calculate it. You can numerically compute it, you can't calculate it. Now this is where Ehrenfest, this is what the important point is, but Ehrenfest can still shed some light. Yes, go ahead. Yeah. Yes, right, sure, you can have an elliptic function to, but elliptic function is not something which I can write down in terms of. All right. I mean, that I could use a elliptic function in this particular case. Certainly, yes. But if I have a x square plus x4, I wouldn't have. Yeah. Sure. Yeah. No, no, not if you have both of them. All right. So I want to do. I want to that. What would Ehrenfest do with a x to the power 4? Well, it's a question of writing the moments as it is. So you start with the average of x. You do that. You go ahead and you do that. And now you see the point is that average of x, average of p. But now look at the right-hand side over here. It's the average of x cubed and average. I mean, had it been now you have to go on. But now the point is that what you have to go on is that there is this v over here for which you will have to write down the dynamics. So you go ahead and use Ehrenfest. And you can go, and you can imagine that. All right, you say that. Look, now you can have to, but constructing all the moments are such a problem. So you will be stuck and wouldn't get an answer. So the thing is, sure, it's I can't calculate infinite moments, but there are so many problems in classical physics, where you cannot do that. You are stuck. A particular example is the dynamics of spinodal decomposition, where you are stuck because the classical equations involve solving some nonlinear problems. So there are those examples, and the point is those examples also tell you what am I going to do when I face this one over here, and what is it that what should be a way of going forward. So the way of going forward, that I take the second order, which is the variance over here, and as you see, the thing is, it has got me a fourth order, which is the kurtosis that you are looking over here. And you see, you can say that will you go and write a dynamics for the kurtosis? And all right, if I do it, I will get higher. So I have to close somewhere. And the point is, the closure is, if I close at this level, then what I have to do is I have to express kurtosis in terms of the variance. And that is where the approximation comes, that you say that I make a Gaussian, the state to be, wave packet to be Gaussian, to remain Gaussian, and then you set the skewness equal to 0, you do this, and so, all right, so does it, how does it work? There is also a conserved quantity energy which we have to write down. So this is that, and you know this, and now you have come somewhere. You have come somewhere, and that is, I have a closed system in the sense that there is the usual Newton's law type looking thing, and then there is but it has the variance in it, and I have the variance, I have got the dynamics of the variance as well, and now you have to, what have I ended up with? I have ended up with two coupled systems. Second, the position, which is dynamics, which is looking like this, and there is the variance dynamics, which is looking like this. And the variance dynamics has where I have cheated, because there was the kurtosis and the skewness, and that is what I have used a closure to. I could have gone to the next step and used a closure, but anyway, so you look at this and you say that what am I supposed to do with these two now? They don't look very friendly. but they are friendly if you know the standard class. If these are just differential equations, a set of coupled differential equations. If you have a set of coupled differential equations, you are supposed to look at their fixed points and so on and so forth and get some idea. What is a fixed point? The fixed point is when the right hand side is equal to 0. A more correct statement would be that it is, I have to write these as 4 first order differential equations, and the right hand side would have to be 0. That's a technicality. This step over here ensures that the first order, it's a fixed point. The first order derivatives would also be 0. But now what you are getting at is that you have the variance, which was the purely quantum mechanical, and you have a particular, the fixed point is a particular value of the, this is what the variance is at the fixed point. And you can say that what is the frequency for oscillation? The frequency for oscillation is found to be there. So Ehrenfest gives you this is the leading term in the frequency of oscillation, and the point is what if I did, I mean, I'll give you the answer to the exercise. The answer, if you were a classical problem, this would come out as the exact answer to the classical problem. What you are seeing over here is a result of the truncation that I have made, and there are an infinite number of correction terms over here which are not so difficult to pick up, at least the first couple of them. And so the point is that what Ehrenfest is allowing you to do is get a way of calculating the frequency of this anharmonic oscillator in a power series expansion in terms of the coupling constant. So and as expected, the way we are going, the leading term is the matches the classical answer, and then there would be the correction term. But the point with this, what is notable is that without Ehrenfest, I wouldn't have got this classical answer as a first crack to the problem. So Ehrenfest has, this is the one of the interesting things about Ehrenfest, and this is the clarification of what I just told you. But then let's go to something which is more demanding and see what, this is a double well potential, that is a potential where you have, in addition to the x4, you have a x square, but it is with a minus sign. So it is with a minus sign, which means that this is actually two oscillators. If you draw this up, if you draw this potential, what you will find that instead of a single well, it has two wells. So that is why it's called a double well potential. And what if I have a double well potential? Well, if it is a classical particle, it is going to stay in, and the energy is not very high, it will be rattling about in one of the wells. If I put it in the left well, it will be rattling about over there if it does not have more than a critical amount of energy. If you put it in the right well, it will be rattling about over there. It cannot go if it does not have the requisite energy. You can't send the particle from the left well to the right well. The whole idea of quantum mechanics is that quantum mechanics can. This is what tunneling is all about. You can, I mean, there is a potential barrier, but the quantum particle will tunnel out of the left well to the right well and vice versa. So the whole quantum business is tunneling the classical trajectory is disallowed. The classical physics disallows the low energy particle which is confined in this well to be able to go there, but quantum mechanics says that's not a problem, where the whole idea of quantum mechanics is that it can tunnel from here to there. So tunneling, that is, you have a barrier and yet you can go to the other side, is a totally quantum mechanical concept, and the whole point is, can Ehrenfest get you that? If Ehrenfest were to be classical, it would not get you that. So the question you should be asking is, so all right, you go to work. I mean, you write down what the position average, what is the dynamics of the position average, and as you, at this point, there are no approximations. Over here, there, all right. I mean, it is the absolutely right equation with the, what is it, this even skewness set to 0. But you see what the answer, you see what has happened. What has happened is that you look at this on the right-hand side, you are looking at this omega square, I mean, that corresponds to this term over here. This comes from there. So normally, it would tell you, if it were a classical particle, it would say that there is no there is no term like this over here, and the classical particle would just have a omega square x minus lambda x cube, which would tell you that x, it can't stay at x equal to 0. Which is the, if you picture the potential, x equal to 0 is the top of the potential, and on the two sides you have the bottom. So x equal to 0 is not, if you don't have the term, this term over here, this is omega square x, and therefore, if it is x equal to 0, it is not going to be able to stay over there. For the moment, stop looking at this term. It is d2 dt square of x equal to omega square x. What's the answer? E to the power x. So you cannot stay at x to the power 0. Classical physics would say, look, I mean, that's, it is either in this well or in that well. And obviously, for large energies, it would be constrained by the x to the power 4. But this is what, what's quantum mechanics going to tell you? Quantum mechanics tells you, when you do, everybody has done, they looked at this guy, it can tunnel from left to right, can Ehrenfest tunnel. And here is the answer, you see, that this is my, at the very crude level, this is my set of coupled equations. The variance, which is the x square moment, the variance of this, the various moments, the next thing after the mean value is the variance, and the variance has come over here. The variance is entirely quantum mechanical. There is no such thing as variance in classical mechanics. And this has come with a negative sign. And this is telling you that if this variance is large enough, then this can become negative. Once it becomes negative, it means that this, it need not any longer stay in one of the wells. It can oscillate about the point x equal to 0, which means x equal to 0 is the center of this thing. So if you oscillate over there, it means you can go from here to there and there to here. So x equal to 0, the central point can become stable if the variance is large enough. And when is the variance large enough? The energy is a constant of motion, and you write down the energy in terms of the way, and from the critical variance that you pick up over here, you can find the critical energy, and that critical energy turns out to be in the well. So the critical energy that you get is inside the well, and that with that critical energy, you can still have a variance which can take you from this well to that well. That is the, I mean, that tells you that Ehrenfest, if you take it seriously, do some calculations, you are going to get the result right. So that was the, that's just going on telling you. And now the point is that it takes me, how much time do I have? 10 minutes? 10 minutes. Very good. All right. So I'm on time. So the critical for this double well, you see the concluding line over here, that the critical value which comes out of all this calculation is that the center is stabilized and there is a motion from one well to the other, and the energy, which is the critical energy, that is what all these calculate things which I had written down, which look sort of not so friendly. At the end of the day, what they tell you is that here is the expression for the variance in terms of the energy. The point was of calculating the fixed points of this system. It's a dynamical system whose fixed points have to be calculated. The energy is the constraint over here, and that's what actually here is the variance fixed point from which I can pick up the energy of the system, and it is the energy comes out to be this chap over here. And the energy comes out to be this chap over here, which is negative. That's the first thing that you should, because the potential is minus x squared plus x4. So the potential has a peak at the center, and it then goes up on the two sides. At the peak at the center goes down and climbs up again with the x4, goes down over here and climbs up again at the x4. So when you are inside the box, the energy is negative, and that's the that is when the classical particle will always have to live in the box, and until the energy becomes positive, when it can get out of that box and be confined by x to the power 4. But for energy negative, there are these two wells which you can see, and the classical particle can only reside over there. But this is what the quantum fluctuation has done to you, that it has, for the critical energy over here, how big is the well? The well is omega 4 over 4 lambda. So that is the size of the well of a double well potential, which I wrote down, omega square x square and minus the lambda by 2 and lambda x4 over 4. So this is inside the region, inside the well, which the critical energy is, and beyond this critical energy, where that is, you can go from the variance will take you from one side to the other. So this is actual tunneling demonstration of tunneling by making use of Ehrenfeld's equation. The fact that the fixed points which correspond, I have written down a dynamical system for this whole business. That is what the dynamical system looks like, what you see over here, and constrained by the energy conservation which you have to look like. And the dynamical system gives you a critical value of the how big must the quantum fluctuation be in order for that system that V, to manage to take it outside of one well to the other, which point which is now stabilized, instead of the fixed points inside the well being stable, it is the central point which is stable. Central point stable means you can go from one side to the other, and that is exactly what happened at this with this condition, which corresponds to an energy of this, and the depth of the well is 4 instead of 5, so this is inside the well, and it's all very consistent. So you see that essentially makes my primary point that Ehrenfest is quantum mechanics. Quantum mechanics is tunneling. Ehrenfest can give you tunneling. It is just that you have to work for it, and that is, you have to work for it with Schrödinger's equation as well. Tunneling just does not come and sit on your lap. So over here, you have to do some work, and at the end of the day, Ehrenfest was not doing something which is ridiculous. So let me end this with a different potential, which is a cubic. A cubic potential has a barrier on one side and goes off on the other side. This is this x cubed term over here, which tells you that as x goes to plus infinity, this potential simply goes to minus infinity. So a classical particle can also run away from this potential if it has the right energy. So the classical particle can, and now the point is, what can the quantum variance do to you? So you do play the same game. You write down the what for x average, what is the dynamics, and this is exactly what Ehrenfest tells you. This is what the dynamics has to be, that it is minus omega square average x plus this, and the average x square is the variance V plus the average value of x square. So you see, if I ignored quantum mechanics and I drop this term over here, you just get Newton's law for this potential. So that's all very consistent. So you have this, if it was Newton's law, I would just be writing down x double dot equal to minus omega square x plus mu x square, and there it would be x equal to 0, would be around x equal to 0, the potential is rising, and then it just on the other on one side it rises, on the other side it falls. So so long as it is on the energy is negative, you would see that the particle is moving around inside this well over here, the classical particle, and then just reflects off and goes off to infinity for higher energies. The quantum particle, what does the quantum system do to you? Well, what the quantum system does to you, you see now over here, there is a fixed point at which the fixed point would have to be taking this into account, and what this is going to do is going to aid the escape. You can just work it out for yourself very simply, that it will give you a fixed point which is no longer the stable fixed point, is no longer it's just picture the cubic potential, and you can see that what happens is that classically there are two extrema which is one is a minimum and the other is a maximum. And what does the quantum variance do to you? What this would do is simply that it starts moving. The one at the bottom, it moves to the right, and the one at the top moves to the left, and they merge and disappear. The classical fixed points move towards each other, and as soon as here is the quantum fixed point with the v not equal to 0. As you can see, with v equal to 0, you have the classical fixed point. One of them is x star equal to omega square over mu, the minimum of the potential, and the other, of course, is x equal to 0. So x equal to 0, one is x equal to 0 when you v equal to 0, so you take the minus sign, and it's a fixed point at x equal to 0. So x squared part, it's oscillating, and then potential gets a peak, and then potential falls. So this peak, where it is beyond the peak, the classical particle will escape. But what about the quantum particle? Quantum particle, the fixed points start moving with this v over here. So the variance makes the fixed points move, the fixed points move towards each other, and they coalesce, and the classical fixed points start moving because of the quantum fluctuations, and all the fixed points disappear if this v star is greater, that is this over here, is greater than v star is greater than omega, where this becomes imaginary, and that just shows that now there is absolutely no similarity with the classical problems at all. It's all quantum fluctuations at work, and you can come up with a little more work with some additional features which are quite interesting, but almost wholly technical. But this is actually good for getting a picture. The picture is that if you take the quantum fluctuations into account and work with Ehrenfest, you do get to see what quantum fluctuations are supposed to do, and what it gives you reasonably, you see, working with the first few moments is not very difficult. People who are used to handling nonlinear differential equations do it very quickly, and therefore this Ehrenfest technique of looking at quantum mechanics through expectation values is entertaining, certainly, and sometimes can be quite useful. These terms today, I understand, have to be everything can be done computationally. You can do it numerically, and therefore all these are sort of weak statements. But the point is that if I am interested in making get an analytic picture before I go to the computer, Ehrenfest is a good bet for you. So that's what I want. Thank you.
Cannot be solved. That's what I thought you said.
Pardon? What?
X squared plus x to the fourth with some constants. You said that cannot be solved in a closed form. Is that the statement you made?
Yeah.
Now, supposing I complete the square, then only a constant will be left. X squared plus x4 plus x squared. I can write it x squared plus some constant whole squared.
Yes.
And then subtract that constant. Then I move my x by that amount.
You can't. You have to move x squared.
I will move x squared.
Yeah, but then if you No, you can't move x square. The point is, where will you move your x square?
I will move it to some capital X squared.
But you are now going to have the kinetic energy term looking absurd.
Okay, maybe we should discuss this in detail later.
I mean, look, if you want to do a nonlinear transformation, your ddx squared,
No,
d2
supposing I
dtx squared
take
would
x
also
squared,
be gone.
Supposing it is a squared is the term, then I move x to x minus a.
No, look, I agree that x squared plus x4, I can write it as x squared plus y, x squared plus a whole square, and that, but that does not help me now,
No.
because I have to say that if it is a quadratic, I have to write x square equal to y.
No, but I
should take time, I think. One student question. Yes. You are discussing about the two turning one problem.
Yeah.
You are talking about the section and the implication on the section. You are saying about the section that will be the integral.
When the center will be stable, the energy will be minus omega to the power by 4 by 5 lambda. You are saying the depth, when we consider about the depth, it will be minus omega to the power 4 by
It is
4
1 quarter and 1.
The minimum energy, or means the particle is stay in that state more time.
No. The point is, as soon as the can I write? That's the anyway. I'll see the picture the point is that as soon as picture the potential. Try to picture the potential. The potential as a hump at x equal to 0 goes down and rises. As soon as this center, the x equal to 0 has become unstable, you see, so long as it is stable, you will be oscillating about the center. So if your energy is very low, then you will be the classical particle. It will be trapped in the well, and it can only be there in the well. Either you put it in the right well, or you put it initially in the left well. It cannot go from one to the other. If it is beyond if it is at high energy, it just sees the x4 part of the potential. The whole business of quantum tunneling is that your energy is inside the double well, and yet you should be able to go from one to the other.
I think this conversation should continue over. In the interest of time, let's go on to the next. Yeah. Thank you.
Okay.
Thank you very much, Professor Bhattacharjee, for insightful and illuminating keynote lecture. May I now request the chair of the session, Professor B.J. Rao, to kindly present a memento to Professor Jayanta Kumar Bhattacharjee as token of our appreciation. Thank you, Professor, once again.
Okay, sure. So do you want me to move away? Yeah.
We now move to the next invited talk of session 1. It is my pleasure to introduce Professor Subroto Mukherjee, professor at Indian Institute of Science, Bangalore. Professor Subroto Mukherjee is a distinguished theoretical physicist. He obtained the PhD degree from Princeton University in 2005. He worked as a postdoctoral fellow at University of California, Berkeley from 2005 to 2009. He joined the Indian Institution of Science, Bangalore as a faculty member in 2009. He works on various areas of physics, in particular transport in strongly correlated systems, many-body physics of cold atomic systems, thermalization and localization in quantum systems, and low-dimensional quantum systems. He will deliver a talk on statistical mechanics from quantum mechanics, May I now invite Professor Subrata Mukherjee to kindly deliver his talk with a round of applause.
Thank you very much for that very kind introduction, and I'd like to thank the organizers for inviting me to this wonderful conference and for placing me among such a distinguished lineup of speakers. And just like with the previous speaker, this is also my first time speaking in front of a Vice Chancellor, so it's a special moment for me. I'll be telling you about how statistical mechanics emerges from quantum mechanics. So as you know, statistical mechanics and quantum mechanics are two of the pillars of modern physics. And of course, the difference between them is that statistical mechanics stage, as I said, statistical mechanics basically has to do with the properties of collections of objects of degrees of freedom. And the degrees of freedom in question could be, spins, for instance, which make up a magnet, could actually be organisms. For instance, here there is, this is a flock of flying birds, and it turns out the laws of statistical mechanics apply to this as well in interesting ways. And even sort of abstract objects like stocks in a stock market, and one can come up with a statistical description of even that kind of system. Okay, so when you start learning statistical mechanics, so it's usually introduced in the following way, in this particular following form with this physical scenario. So the standard setting in which it's usually introduced is with a gas of particles. So you have some particles which are confined to be in some kind of a volume or a box, and then you're told that this particular system has a certain fixed energy, a certain fixed number of particles, and is confined to a box of a fixed volume. And this setting, as all of you know, is what's called the microcanonical ensemble. Now the whole point is that the reason that you need to resort to a statistical description of such a system is that you have a very large number of these particles, and it's absolutely impossible to solve for the motions of these individual particles, regardless of whether the laws of motion that you're considering are classical or quantum. It's just a hopeless thing. And so you have to resort to a statistical description of macroscopic properties, physical properties which emerge from large numbers of these particles, like temperature, pressure, heat capacity, and so on. And so statistical mechanics is really the discipline which tells you how to calculate these kinds of things. So the way that you go about doing it and establishing a connection with the microscopics of this system, when you assume that the particles obey classical mechanics. So for the first few minutes of my talk, I'm going to forget about quantum mechanics and just tell you what happens when the particles in question are classical, and what we sort of know about how statistical mechanics emerges from classical mechanics, and then I'll move on to quantum mechanics. So in the classical case, of course, what you say is that there is a precise state of all the particles in this system, which is called a microstate, and this precise state is specified by specifying the values of the positions and the momenta of all the particles. And this can be represented graphically in terms of what's called a phase space. So a phase space is basically this multi-dimensional space which is a space of all the position coordinates and all the momentum coordinates, and a particular state of the system is some point in phase space, like this one, and then it has a certain evolution in time which is traced out by this phase space trajectory. So this is what's called a microstate of the system, this collection of all the coordinates and all the momenta, and any physical information relating to the system at any instant of time can be obtained from this microstate. So this microstate contains complete information about the system, and these states evolve according to the laws of classical mechanics or Hamilton's equations. Okay, but as I said, that those equations are impossible to solve, so it's not really a meaningful thing to ask what would be the microstate of this system at some time t given some initial microstate. What is actually more meaningful and more practical is to ask about these collective properties. And so for that, you need to define a density in phase space. So you're now looking at the system statistically, and so you need to have some probability density in phase space of these microstates. And the microcanonical density, the equilibrium density for the system that I told you about it right at the beginning, is something in which the density is just 1 divided by the phase space volume basically something like the number of phase space points, which correspond to the constraints that you have imposed, which is the total energy, the total number of particles, and the total volume of the system. So this is basically the phase space volume between some energy E and E plus delta E. And so the point now is that if you're given any phase space density, then in principle you can calculate macroscopic observables by integrating the expression for the observable in terms of the microstate variables over the phase space density. So by averaging over phase space with the right distribution. So this is basically the value of an observable at time t according to this definition. This is the value of the observable in the microcanonical, with the microcanonical distribution. And the notion of thermal equilibrium.
Why? Rho is a function of time also, right?
Which one? Yeah, so that's the reason I put the t here. Right, okay. And so the notion of the system reaching thermal equilibrium is basically that this observable, whatever it might be, after an observably long time, over some time scale that is experimentally accessible, reaches the microcanonical value. So this process is called equilibration or thermalization. And so the question you can ask is, if this happens for all observables, that means that in some sense, this distribution function, this phase space density, is also tending to the microcanonical density. And this is what's called the ensemblist approach of statistical mechanics, as pioneered by Willard Gibbs. And so the idea is that you somehow talk about how, this phase space density tends to the microcanonical density in some observably long time for a given system of particles. Now, the way in which this happens, also, as you know from your courses on statistical mechanics, involves an increase in the entropy of the system. So as the system is approaching thermal equilibrium, there is this particular property of the system called the entropy, which increases, which also tells you about the fact that the approach to thermal equilibrium is in some sense irreversible. And so the Gibbs entropy can also be written in terms of this distribution. And this is the expression for the entropy in terms of this phase space distribution. And I'm sure that you've probably come across this in some class in statistical mechanics that you've taken. And so the idea is that this increases with time, it tends to a maximum, which is the entropy of the microcanonical distribution, and also the equilibrium density, the equilibrium entropy. All right. And so this microcanonical distribution, of course, doesn't depend on any of the microscopic details of the individual degrees of freedom. It only depends on these macroscopic constraints that one has put, the total energy, the total number of particles, and the total volume. So in this sense, there is some notion of irreversibility, because the distribution that this is tending to is something that is forgotten about the initial distribution. It only depends on these macroscopic quantities. Okay. So you can ask, well, how exactly does this happen? How exactly does some initial distribution tend to the microcanonical distribution? And it turns out that there are certain complications and subtleties here, and I'm going to be a little glib in terms of describing them, because I only want to talk about them in the specific context of how quantum mechanics comes in and fixes some of these problems. But the idea is that if you literally took this definition of the entropy in terms of the distribution function, then it turns out that it actually does not change with time, because of Liouville's theorem, which talks about the conservation of phase space volume. And so if the system is a Hamiltonian system, then this doesn't change with time. Okay? But you want it to change with time, because you know that the entropy is increasing. So how do you deal with that? And so the idea is, as proposed by Gibbs, is that you don't literally integrate over all of phase space. You actually divide phase space into these blocks. This is called co-straining of phase space. And then what you do is, you basically, so you have some initial distribution which looks like this, and then the dynamics of the system is such that it actually spreads out the initial distribution in some way. So in such a way that, in some complicated way, but which still preserves the volume of the initial distribution. And this is what's called mixing dynamics. I've actually used certain words interchangeably in describing this dynamics. Now, those of you who are experts in the subject might wince at my doing this, because there are some subtleties between, there are differences between what these words actually mean formally. But as far as my limited requirement is concerned, I'd refer to this kind of dynamics as something which actually spreads out this kind of initial blob of phase space volume. And the important thing is that when it's spread out, it's actually spread out over these different blocks, these coarse-grained blocks. And then instead of integrating over phase space in this way, you actually convert this into a sum over these blocks. And the only blocks that you include in the sum are those which have some non-zero phase space density. And in this way, one can show that the entropy actually does increase as a function of time. So coarse graining is important. And this particular dynamics of spreading out this blob also washes away the effect of initial conditions because of its complicated nature, because of the fact that it has this property of mixing. So that, qualitatively speaking, is the way in which you think of this approach to equilibrium in this ensemblist picture, in which you start with some initial distribution and then ask how does that initial distribution end up becoming the equilibrium distribution. Now there's a different approach to the same problem, which was pioneered by Boltzmann and Paul Ehrenfest, whom you heard about in the last lecture. And as emphasized by the last speaker, Ehrenfest's philosophy was not to worry about, in his case, quantum states, in my case, distributions, but actually to look at the values of observables. So this picture focuses not on a distribution, but actually on the values of the observable. So there's no notion here of some distribution, initial distribution tending to a microcanonical distribution. What you say instead is that the values, the initial values of observables tend to the values of the observables in the microcanonical distribution in this individualist approach. And what gives it its name is the fact that you don't talk about a distribution at all. So at any instant of time, the system actually happens to be in a single microstate and not in a distribution. And so the idea here is that the initial condition is just that of a single microstate, and the system continues to be in a single microstate during its entire evolution. But what happens is that if you look at the phase space where this microstate is, that keeps, the place in the region in phase space where the microstate is keeps changing as a function of time. And you can partition phase space into these different cells depending on the values of macroscopic observables. And then there is a cell within this phase space which has the overwhelmingly large phase space volume in which the values of these observables are equal to their equilibrium values. Okay? So the idea here is that the system starts out in some initial state, and then it might start out in some atypical cell where the values of macroscopic observables are not equal to the equilibrium values, but it eventually, over some observably long time, will make its way into this equilibrium cell. And so over this observably long time, all these observables will have their equilibrium values, and once it is in here, then it for the most part continues to be in this equilibrium cell. The dynamics is of that sort, and this is easier said than actually proven for a system, but that is what the individualist approach is, and the entropy which increases here is basically the Boltzmann entropy, and the Boltzmann entropy, as you know, is given by this formula, where the W in this formula is the volume of the particular cell in phase space in which this particle is, and because the equilibrium cell has the largest volume, this increases as a function of time because this initial phase space point is moving to larger and larger cells in phase space and eventually reaches the equilibrium cell. Okay, so these are these two pictures, and I'll show you how quantum mechanics actually in some sense reconciles these two pictures and also resolves a discrepancy between them. So something which is interesting and important in statistical mechanics is the consideration of subsystems. So if, let's say, you take a system, a physical system, and you partition it into a large part which you call a bath and a small part which you call the system, then there is a notion of the bath bringing the system to equilibrium. Okay? And so you can ask, well, how does that happen? How do I know what is the way in which I understand what the equilibrium state of the system is when it's coupled to a bath? And the idea is that you think of the system plus the bath as a larger system. And then from the state of the larger system, you argue that the smaller system, what I'm calling the system here, is in equilibrium. Now the whole point, so this is basically the derivation, for instance, of the canonical ensemble from the microcanonical ensemble. Now the whole point is, as you know from your courses on statistical mechanics, that you can do this only when you assume that the whole system actually is in a distribution by itself. If the whole system is in as described by a single microstate, then there is no way in which you can think of this particular part of the system also as having a distribution. This also has to be in a single microstate. So in the individualist picture, in which you're thinking of a system always being in a single microstate, there's no way in which you can think of a subsystem actually having a distribution if the whole system is in a single microstate. Whereas in the ensemblist picture of Gibbs, that can happen because you're always thinking of the larger system as having a distribution, and from that distribution you can derive a distribution for the smaller system. Okay. So, but then you can ask, well, so that's good. So that allows you to, if you like, obtain the canonical ensemble from the microcanonical ensemble. But you can ask, well, what produced this initial distribution of this larger system? Why was the larger system, why did it have a distribution? Why wasn't it in a single microstate? And now you'd say, well, the reason it had a distribution is that, we were uncertain about the exact state that the system was in. Well, why were you uncertain? And then eventually, if you try to answer this question, you will be led to the conclusion that the reason that there was an uncertainty in the first place is that this larger system was also perhaps in contact with something else which introduced this uncertainty. But then you can apply this same logic to this even larger system, the original system plus whatever it was in contact with, and ask, well, why was that in a distribution in order to place this larger system in a distribution? So you can see that even though the Gibbs picture works very well in terms of giving you a distribution for the smaller system, there is in some sense a hierarchical inconsistency. That whatever is your starting point, if you say that that had to have a distribution, then in some sense you have to think of that as being part of a larger system with a distribution and so on. Whereas the individualist picture does not have that problem, but then the individualist picture cannot produce a distribution for a smaller system if the whole larger system started out in a single microstate. Okay. So where am I going with all of this? So what I'd like to convince you in the remainder of my talk is that quantum mechanics actually steps in and resolves this problem, and in a very interesting way, which involves uniquely quantum mechanical phenomena. Now, it was proven fairly recently, only about 10 years ago, that the strongest form of thermalization is really a form of thermalization in which you think of subsystems being brought to thermal equilibrium by a bath. Okay, so I'm not going to dwell too much on the subtleties of what this is, but just suffice to say that there is a notion in which this is the strongest sense of thermalization, and if a system thermalizes in this way, then whatever other notions of thermalization you might have, realistic notions of thermalization you might have, are also automatically realized. Okay. So therefore, it is crucial to understand in any sort of consistent formulation of statistical mechanics coming from something microscopic how subsystems thermalize. And the problem, as I mentioned earlier with the ensemblist versus the individualist picture, is that the ensemblist picture can produce a distribution for a subsystem, can tell you how a subsystem thermalizes, but it requires the full system to have a distribution, and you can't really justify why that's the case. In the individualist case, on the other hand, the full system does not need to have a distribution. It can be in a single microstate, but classically it cannot produce a distribution for a subsystem. So that's sort of the impasse, and it turns out that quantum mechanics actually steps in interesting ways to solve this. So first of all, if you now think of quantum mechanics and you want to translate this problem into a quantum mechanical context, the first question is what you mean by phase space, right? And as also mentioned by the previous speaker, the thing which gets in the way of you defining a proper phase space for particles in a quantum mechanical setting is the uncertainty principle. That it doesn't allow you to specify the position and the momentum of the particles with infinite accuracy. And so how do you even talk about a phase space and phase space trajectories? What is the setting in which statistical mechanics plays out? So von Neumann said that the setting in which statistical mechanics plays out in the quantum mechanical context is just the Hilbert space of the system. Because the state of the system is always some state in the Hilbert space, and that state contains all the physical information about the system at that instant of time, just like a microstate in classical statistical mechanics, contains all the information about the system. So the analog of a microstate in the quantum mechanical context is just the state ket of this system, the quantum mechanical wave function, if you like, which obeys the Schrödinger equation. All right. So now there are certain other issues which, of course, you have to worry about. So in a classical context, any microstate has a well-defined energy. In fact, it has a well-defined value of any physical observable. Quantum mechanically, that's not the case. And again, as we heard in the previous talk, what is meaningful in physical in some sense is the expectation value of an observable. And so if you want to give a particular microstate a fixed energy quantum mechanically, then you really have to talk about the expectation value of the Hamiltonian in the microstate. So that is the energy associated with the microstate or the quantum mechanical state in question. But then there's a certain uncertainty, there's a certain spread in energy. And so if you wanted to, in some sense, still ascribe a fixed energy to an arbitrary quantum mechanical state, you have to assume in some sense that the spread is small. And the way you make that assumption is by saying that the state, which you can write down as a linear superposition of the energy eigenstates of the system, essentially has weights which are appreciable only for energy eigenstates close to this expectation value of the energy. So you're thinking of states like this in terms of associating a well-defined energy with a quantum mechanical state. Okay. But now there's still a further issue, which is that unlike in the classical case, where the dynamics of these microstates is in some sense complicated, chaotic, mixing, and that is what gives you the approach to equilibrium and the washing away of initial conditions, quantum mechanical dynamics is very simple. This state just evolves in principle according to this dynamical equation. This is called unitary evolution. And if you just look at this, there is no sensible way in which you can think of unitary evolution as being chaotic. You can think of initial states moving arbitrarily far away from each other so that in some complicated manner so that the memory of initial conditions is washed away. So then there's automatically an issue of how equilibrium is even approached in a quantum mechanical context if the microstates in question are these quantum mechanical state kets which obey the Schrödinger equation. So that's an issue. And of course, we are worried, we're talking about expectation values of operators being the physical observables. And so these expectation values as functions of time have to be calculated in this manner. So they're the expectation value of the operator in the instantaneous state ket. Okay. So what we want now, again, for this notion, so if we forget about even trying to think of this approach to equilibrium in terms of some chaotic evolution of the microstates, the state ket, and think in terms of how the observables tend to their microcanonical value, a la Boltzmann and Ehrenfest, then we know that the expectation value of the observable from the evolution of the state ket is going to change as a function of time like this. And we want this to eventually at observably long times not have any time dependence, tend to some constant value. And you can see that all the time dependence is sitting here. And so you might think that and it's sitting in some phase factor here. So you might think that what happens is that as you go to very large times, this phase factor, which also involves a difference in energies in the spectrum, is eventually going to become like some random phase if you wait sufficiently long. And then this is going to be like some random thing which averages itself out to zero. But the problem is that that will happen, but it will happen at a time scale which is larger than the inverse of the smallest energy difference, Em minus En, and that for a macroscopically large system can be very, very small. So if this was basically your justification for how equilibrium is approached, then you might have to wait for time scales which are longer than the age of the universe in order for equilibrium to set in. So something else has to get rid of this term. It can't just be sort of the randomizing of these phases. And so, by the way, this process is what's called dephasing. So it's not just naive dephasing which can do this for you. So how exactly does equilibration occur? And so this brings me to a very modern, sort of modern understanding of how this process takes place. And this goes by the name of the eigenstate thermalization hypothesis. So what that tells you is that when you're looking at this expression for the expectation value of this observable as a function of time, this is what it's going to tend to, and the time dependence is sitting here. But the reason that the time dependence goes away at observably long times is not just because of dephasing, but also because of a certain type of behavior of these off-diagonal matrix elements, and especially the fact that the off-diagonal matrix elements fall off inversely with the size of the Hilbert space dimension. That these are actually very, very small in some sense for a generic quantum system, and that in conjunction, of course, with these random phases gets rid of this term. And then what you're left with is this term, which is the thing which is supposed to describe for you the equilibrium state. And as far as this term is concerned, the way in which you can get this microcanonical expectation value of the observable from this term alone, when all of these weights are confined to some small window near the energy that you're interested in, is if this expectation value of the observable is independent of the energy eigenstate. So all energy eigenstates within some small energy window have exactly or roughly, the same value of this, the expectation value of this observable, so that this can tend to this microcanonical distribution, and the effect of the initial conditions contained in the CNs is just washed away. So this goes by the name of the eigenstate thermalization hypothesis, first sort of proposed by Eugene Wigner many, many years ago, refined to some extent by Michael Berry, and then the modern understanding of this is something which goes back only about 30 years or so, and is due to these two gentlemen. Okay, so so a conceptual insight for the eigenstate thermalization hypothesis is just the following. So there's one crucial difference between a generic quantum mechanical state system and a generic classical system. So if you take a generic classical system and you think of its microstate, so let's say initially the system has is in some particular microstate, and then it evolves as a function of time, the microstate is almost inevitably going to change with time. And so why is that? So if the system in question is, let's say, some gas of particles, the microstate is specified by specifying all the positions and all the momenta, and if you know all of them at some instant of time, then you know at the next instant of time something has to change. Some particle is going to move from here to there, some momentum is going to change, and so your microstates will evolve as a function of time classically. And so, but quantum mechanically, that's not the case, because quantum mechanically, you know that there is a set of microstates of the system which actually don't evolve as a function of time, and those are the energy eigenstates of the system, because they just pick up this phase as a function of time, which doesn't influence any observable. And so, if you now demand that a quantum mechanical state has to thermalize in this individualist picture, starting from any initial microstate, any initial quantum mechanical state, including from an energy eigenstate, then the only way in which this can happen, given that the energy eigenstates don't evolve as a function of time, is if the energy eigenstates were thermal to begin with. If the energy eigenstates themselves were like some thermal ensemble, and that is really what underlies this particular requirement, that this diagonal matrix element or the expectation value is independent of the particular energy eigenstate within this window and only depends on the energy, like in the microcanonical ensemble. So these energy eigenstates are already thermal to begin with, and so that sort of underlies what our understanding, our current understanding of how quantum mechanical systems thermalize, that it's this eigenstate thermalization hypothesis. And all of it, and all the important physics is contained in these matrix elements. So the diagonal matrix elements basically contain the analog of the concept of the equilibrium cell in the classical individualist picture, that, if you look at the expectation values of these observables in these energy eigenstates, then they're independent of the energy eigenstates. And so if you look at all the energy eigenstates in the Hilbert space of the system in some window, almost all of them have the same value of this quantity, and so that's like the equilibrium cell. This, on the other hand, has no classical analog because it involves off-diagonal matrix elements, but this is the thing which is responsible for telling you why there is an approach to equilibrium within observably long times. Okay, so this is sort of a cartoon picture of what happens, that if you take the Hilbert space now in this individualist picture, then there is again some subspace of the Hilbert space which is the equilibrium subspace or the equilibrium cell, like in the individualist picture, and then you can start the system out in some particular state, and then eventually the evolution, the usual unitary evolution, will take it into this equilibrium cell. Okay. So I'll probably finish in another 3 or 4 minutes. Okay. And all your energy eigenstates which determine this evolution are sitting in this equilibrium space, and this is basically qualitatively, pictorially what the eigenstate thermalization hypothesis is telling you, that you go from some atypical state through this usual unitary evolution and you end up in this typical or equilibrium cell of Hilbert space where all your energy eigenstates are sitting that are determining this evolution, and then once the system is there, it sort of essentially continues to be there. Okay, so let me just skip this. I mean, so this is some numerical evidence of this actually happening in a generic quantum mechanical system. But let me now come to this, the point that I was making, which was that one of the problems with the classical way, of thinking of statistical mechanics coming from classical mechanics was that in the Gibbsian view, in the ensemblist view, you could actually get to this view. The full system is in a single microstate, and so you don't need any, so you can always imagine some self-contained system always being in a single microstate as opposed to a distribution, but then classically there's no way in which a subsystem ends up with a distribution. But quantum mechanically, even if the full system is in a single microstate or a single state ket, then it turns out that you can actually get a distribution for the subsystem. And the way that works, and the reason that happens is because of this quantum mechanical property of entanglement. So imagine now that you have a system plus bath which makes up a larger system, and you ask, well, what is the microstate for this larger system? So imagine that this larger system is in a single microstate, it doesn't have a distribution, and so it's described by a single state ket. And so you might think that the most general form would be that this state ket would be a function, would be a product of a state ket for the system and a state ket for the rest of the bath. But it turns out that that's not true, because quantum mechanics allows for superpositions. So the most general form of the state ket is some superposition of such products. I mean, that just comes from quantum mechanics. And so when you have a superposition of such products as opposed to a single product, then what you can do is you can actually, when you focus on just the system and remove the bath, then you have to perform what's called a partial trace over the state. And some of you might have already studied this in some quantum mechanical course, but long story short, what that does is it actually gives you a distribution over the state kets of the smaller system, as opposed to saying that the state ket is in a single state, which is what would have happened if you didn't have the superposition. So even though you're starting with a single microstate for the whole system, you end up with a distribution over microstates for the smaller system when the full system is in this kind of superposition, and that is nothing but the property of entanglement. So it's really entanglement which is responsible for putting the subsystem in a bath, even though the full system is in a single microstate. Okay, and this is essential for the bath to thermalize the system. Now you can say, well, that's true, but how do I know that the distribution that I get is actually the canonical distribution? So it turns out that that can also be proven and goes by the name of canonical typicality. Okay, so since I'm running out of time, let me skip this last thing which had to do with the level spacing distribution and maybe just stop here, but let me emphasize something. So one very interesting conceptual aspect which comes out of all of this is that normally when you think of a system classically, right, in contact with the bath, and you ask what is it that the bath is doing to the system in order to thermalize it, what actually is happening, what kind of interaction is taking place between the bath and the system for the system to be thermalized or equilibrated by the bath. And usually in textbooks of statistical mechanics, you'll be told that there is something which is being exchanged. There's some conserved quantity, like an energy or the number of particles or something else that's being exchanged between the bath and the system. And the dynamics of this exchange is ultimately what is putting the system in thermal equilibrium. It turns out that quantum mechanically, when you think of a system being thermalized by a bath, of course there can be things which are exchanged between them, but that's not necessary at all. What is fundamentally necessary is that the system gets entangled with the bath. So entanglement is really the crucial thing quantum mechanically in terms of any bath equilibrating a system that's in contact with it, okay? And so anyway, so I just skip this last part and go to the summary of my talk. So ignore this. I'd be happy to talk about this last part with anyone who's interested. I'd be happy to talk offline. But this is really the summary that quantum mechanics, the way statistical mechanics emerges from quantum mechanics, actually resolves some kind of a discrepancy in the way in which you would think that statistical mechanics would emerge from classical mechanics, in the sense that a single microstate can actually put a subsystem in equilibrium, which is the strongest form of equilibration. And what is central to that idea, what is central to that is basically the concept of entanglement, the fact that the system can get entangled with the bath, and it's really this process of entanglement which is producing a distribution for the system, even when the system plus the bath is in a single quantum mechanical state or in a single microstate. Okay, so thank you very much.
Hello.
The system what, sorry? Yeah. Yeah. Okay, so there are two different things. So one thing had to do with what a subsystem is doing, so that's the system plus bath part of all of this. But if you forget about that, if you forget about partitioning your larger system into a smaller system and a bath, and just look at the larger system by itself, so there is a notion in which the larger system also has to equilibrate, right? And so that was this business of tending to the microcanonical distribution. Now, in the Gibbsian picture, what you say is that the distribution, so you start with some initial distribution, and then it tends to the microcanonical distribution. And of course, if the initial distribution is tending to the microcanonical distribution, then all observables will also tend to their microcanonical values, right? Just from the definition of what the observable, how you obtain the observable. In the individualist picture, you don't even worry about a distribution. You're always thinking of the whole system as being in a single microstate, right? But nevertheless, you still want observables, because those are really what you measure physically, to tend to their microcanonical values. So here there's no notion of some distribution tending to some other distribution. Here it's directly a notion of initial values of observables tending to their final equilibrium values. Right, right, okay. And the subsystem in bath was a different aspect of this. That's another aspect of equilibration, in fact the strongest form of equilibration, in which you talk about some arbitrary subsystem of a larger system being brought to equilibrium, and you can show, as these authors did, that if that happens, then even this other notion of equilibrium of observables for the whole system tending to some microcanonical value follows from that.
Okay. Any other questions?
Hello.
Yes, please.
It was a nice talk, and I learned a lot of things from this. So I had a question that you told that the microcanonicality will be preserved from only taking the diagonal matrix element of the observable. Okay. So why this is so?
Okay. So I didn't mean that. So what I meant was this. So let me just go back to that slide, the one that you're talking about. Here. So if you look at the expectation value of any observable as a function of time, right? So it has two pieces. So one which involves the diagonal matrix elements of the observable, and this is all in the basis of the energy eigenstates of the system, and one which involves the off-diagonal matrix elements. Now, if you want this thing at observably long times to become time independent, to not have any time dependence, to asymptote to something, then somehow this term has to go away, right? And so this term has to drop out. So which means that there doesn't, in the end, there shouldn't be any influence of the off-diagonal matrix element at long times, and then what you're left with is only this, which has a diagonal matrix element. So if this observable is tending to its microcanonical value, then that microcanonical value should only come from the diagonal matrix elements and not from this term, because this is the term which has the time dependence.
Okay, okay. So basically this term has a evolution part.
Yes.
Okay, time part.
Yes.
So, but you are taking the, there is a hypothesis called eigenstate thermalization. How this leads to the En is equal to Em is equal to some energy?
No, okay. So here, see, what we're doing is we're first of all saying that we are looking at states which don't have a large uncertainty in the energy. So that was in my previous slide, somewhere here. That when you're constructing these states, if you want these microstates to have, in some sense, a reasonably well-defined energy, right? Which doesn't have to be the case quantum mechanically, but is always the case classically, then you have to choose those microstates in which these weights are only in some small window of energy, right, close to the energy which you want the state to have. So the only energy eigenstates which have any appreciable energy, weight here, are those which have an energy close to the energy that you want. So that is by construction. So once you have that by construction, then basically the only values of n for which these Cn's are non-zero are those for which the En is close to the energy that you want the state to have. So you are looking only at these states, and in fact the states which you're throwing out by doing this, which in some sense you're saying are unphysical as far as having a reasonably well-defined energy is concerned, are what you normally in a different context call Schrödinger cat states. So you're throwing away what would be Schrödinger cat states and looking at what are called non-cat states.
Okay. And one more.
I think we should discuss later again.
Okay.
This should continue.
Okay. Thank you.
Thank you very much. I have two observables.
Yes.
One observable is, I found no traces of Bengali in your diction.
Okay. Well, all right. So since you mentioned that, that's because this city is my hometown.
Excellent, excellent. Second observable, I learned today that quantum mechanical states have no memory of their past initial conditions.
Eventually.
It's such a beautiful state to be in.
Okay.
Thank you very much.
Thank you so much.
Thank you very much, Professor Subruto Mukherjee, for delivering this clear and insightful talk. May I request the chair to kindly present a memento to Professor? Before we conclude session 1, we would like to express our sincere gratitude to the chair of this session, Professor B.J. Rao, Honorable Vice Chancellor, University of Hyderabad, for graciously chairing the session and guiding the proceedings. May I now request our convener, Dr. Abhiram Suri, to kindly present a memento to Professor B.J. Rao. Thank you, sir. Yeah. This formally concludes session 1 of 100 Years of Quantum Mechanics 2026. We now invite all participants, including the session chairs, speakers, organizers, volunteers, and attendees, to join the official photo session. The photo session will take place outside the auditorium near the high tea area. This will be followed by high tea, which will be served outside Zakir Auditorium. And we'll begin the next session at 11:40 a.m. So please occupy your seats before the session begins. Thank you. And I request all the participants to kindly wear their ID cards. Thank you.
tumor. I had an operation. Yeah. And so it was here. You can see this. We are childhood friends. In the sense of our physics childhood. Hello.
Good morning once again. I hope everyone enjoyed the photo session and the tea. We now resume the program with session 2, the next technical session of conference, 100 Years of Quantum Mechanics 2026. This session will be chaired by Professor Bindu A. Bamba. May I request the chair to kindly take in charge of the session. Thank you.
Yeah, I'm very happy to introduce the next speaker, and I asked that I should personally do it rather than read off some facts which you can read. What I want to tell you is about a new number that I have introduced in physics. There is a number in mathematics called the Erdős number, and it tells you the step to which you are connected. Then in the Girish Agarwal's 70th year, because Erdős was publishing prolifically, then in the 70th year of Girish Agarwal's life, we introduced the Agarwal number because he has like 5,000 publications. So now, but in physics, there is, besides publications, there's also teaching. And the name of Professor Mani is one of the primary names that come. There are two names that comes. One is Professor Rai Chaudhary's name and Professor Mani's name. And everybody can trace a Mani number.
Oh, come on.
Because we have had teachers and colleagues who were taught by Professor Mani. And so, because you are so young in the audience, you wouldn't know, but all of you have a Mani number because all of you have been taught by people who have been taught by people who have been taught by Professor Mani. So you are the nth order approximation of the Mani approximation, and his teaching is legendary. So I am very happy to introduce Professor Mani, telling us about.
Thank you so much, Bamba. How do I go to the next step? Okay, I have fond memories of spending a semester in UOH. All my friends from there are here, and I have learned a lot from them. My interest is, of course, theoretical physics, but also to do some experiments. That inspiration came to me by looking at the work of some of the most famous theoreticians. As Wigner's name was here, he was a chemical engineer and he knew facts cold. So did all the famous people, and they knew many experiments by themselves. They would go to the lab, learn, and they would get ideas for their work from there. So in India, of course, Professor Meghnad Saha, Professor C.V. Raman, and then Bose, then Homi Bhabha, several people in India, Professor G.N. Ramachandran, several people in India had been inspired both theory and experiment.
So this is my little effort to continue in that direction. The thing which I am going to do is start with quantum tunneling and Hartmann effect. The Hartmann effect I learned from the late Professor Binayak Datta Roy. He is no more, a very close friend of many of us. And there was a book which came, and I think we all wrote a few things about it. So let me proceed to the next slide. Here it is. Let me look at it from here. Just a minute. So you see from here, there are 5 Nobel Prizes which have been received for the quantum tunneling, which is an effect which we all teach in first semester of quantum mechanics, wherever we do that. I will not repeat all of this here. And recently also, quantum tunneling has played a very important role in analyzing a lot of data coming from electrons emitted from an atom, and they notice the time delay. So that is how it is. So let me firstly give a simple explanation of this in ordinary classical mechanics. Supposing I have a particle which is traveling with a velocity v. Supposing I am sending it to Professor Nirmal Vishwanathan. It takes 5 seconds for the particle to reach him. But on the other hand, if there is a barrier between the two, when the particle comes, it will slow down at the barrier, and so it will reach him at 7 seconds. So the time delay is 2 seconds. We can do the same thing in quantum mechanics. When we teach, I send up this 5 minutes is the major thing. The rest are all going to be mathematics of its life. At that time, you people can do whatever you want, looking at mobile and things like that. So, but please just concentrate in the first 5 minutes, and you will see the main effect. So, quantum mechanically, I send a particle. Then I write down the initial current going. When it comes to the barrier, it will slow down. That the energy, the kinetic energy will be less because the potential barrier is there. Given that, it will take some time and reach it. Now, the major punchline is this. The barrier should depend upon the width of the barrier. If the width is large, it should take little longer to reach Professor Nirmal Vishwanathan. But supposing the barrier is, say, 10 centimeters, it will take, delay is 2 seconds. 20, you would expect 4. No, the answer is again 2. If it is 40, it is again 2. That means that particle travel with infinite speed going from this place to that place. This is the main story about Hartmann effect. You people now can relax and do what you want. This is the main point which I had wanted to say. Now I will do the mathematics of it. This is the standard thing. I am writing the potential V of x as V in region here, outside this. That is, the potential is only from minus a by 2 to plus a by 2. And this is the standard equation which we all write. When a particle is coming from that direction, we will drop this. Oh, what did I do? How do I make it a pointer? Thank you. So we drop this term because this is the term which is going forward. This term is not. Again, the standard Schrödinger equation which we teach in the undergraduate class. And then in the potential barrier, this is the equation we write. Inside the barrier, clearly this is not, notice the I is gone, and this is how the wave function looks inside the barrier. Kappa is this, notice this is a potential, and 2m v minus e by h cross. Very standard material that we teach. Is it all right? Can I move to the next slide? So now you match boundary conditions. the first one is given by here, initially there. This is the reflected wave. Okay. This is the incident wave, this is the reflected wave, this is what is inside. Here the one is that not only psi is continuous, the derivative of psi is also continuous. The reason for that is, if it were not continuous, the second derivative will be infinite, but that will cause energy, momentum, all sorts of observables to be infinite. So we always assume that that does not happen. Remember, in a particle in a box, the edge, the second derivative is discontinuous. That's because the walls are all infinite. That's the reason. This is a standard thing which students who are learning quantum mechanics for the first time should observe. They should know this. So I write that here. These are the equations, and you can verify that t squared plus r squared is equal to 1. Why is that? Because the potential is purely real. Had it an imaginary part, as it does in modeling nuclear physics, absorption takes place, you have to write down imaginary potential. We of course will not do that. So this is the expression. So now question is, how do you define tunneling time? It's very problematic, and there are many multiple definitions of tunneling time. What are they? Is a delay defined as an excess of time spent on the particle to interact with the barrier compared to the traveling in free space. It is measured by comparing some characteristic like phase or spin of the transmitted particle of the wave. Even though different definitions for tunneling time are there, no satisfactory explanation could be given for transit time. It is still, so whenever you talk about delay, you must tell what kind of time delay you are talking about. It varies on the definition that is. But of course, the difference is not very important. Ultimately, the Hartmann effect is there. That is, if the barrier is big, the time doesn't change. It travels with infinite speed inside. Does it violate relativity? Answer is no, because we are doing non-relativistic physics. We are not including Dirac equation and things like that, or Klein-Gordon equation. I'll just wait. Group delay is the difference between the time at which the wave packet arrives at the barrier and the time in which it leaves the barrier. So this is what you do to calculate, very standard thing. The Hartmann had used what is called the Wigner time delay. That's a very interesting thing, and one should teach that at the first course. And let me explain that. That's a very interesting effect. We are doing one dimension, of course. Here is my, I have changed the notation a little bit. This is the equation. I have not minus a by 2, but I have just written this, and x is greater than a, it is 0. So this is the potential. So the initial wave is given by this expression. This A incident is a complex number. I have just taken a Fourier transform of the wave function. It's a complex number with several frequencies. This is the wave packet. So I write down that as psi xt as A incident times T of k and forward moving one. The amplitude will be written as A incident k mod of Tk e to the I Tk. We have to concentrate on this. Now we will use the method of stationary phase. Again, I will repeat what that is. Supposing this thing is oscillating very rapidly, because if this quantity is large, as k changes a little bit, this will oscillate rapidly. If it oscillates rapidly, then these things during that change hardly changes, the entire thing will be 0. When will the oscillation be very small? When I satisfy this condition. This must be stationary as k is change. That is the stationary wave approximation. So I write down that expression, d dt delta k plus, of course, I drop and do that. And this is the crucial expression which is there. This is the crucial expression. Now let us see, this is what Wigner did. Important result. Let me just go back to the previous slide. Please notice, this is the important equation. I have here, so x can be written as, t can be taken as a side, d omega dk, dk cancels, so I get dt by d omega. So this is the Wigner time delay. So the time delay calculated by Hartmann was this expression. Very straightforward. You know what the delta t is. It is now just undergraduate mathematics. Just calculate. Yes, Professor Bhatnagar. Please say that again. Yes. It's taken into account, of course. Yes. The barrier is between 0 and A. Okay? Now I send in the wave. Here some phase shift occurs. The phase shift is a function of k. So I want that value of k when the phase shift doesn't change. Pardon? Exactly. By the way, I learned all this when I was in SN Bose Center when Vinayak was there. So now it's just straightforward algebra. Here it is, the transmission expression, and t, I can simplify this, where we can define what is omega and so on. Tan omega is defined here. So now this is the expression, final expression with omega. Rather is not a simple expression, but not too complicated either. So now if you substitute that there, you will see the time delay is this expression. As tan tk goes to 1, it becomes independent. You can just check that. When tan of here, this goes to 1, then it becomes independent of, notice, ultimately where is that a correct expression? Where is d omega by dk? Anyway, if you calculate it, I will not do the calculation here. It's straightforward to show that. Omega becomes independent of k. The time delay due to the barrier is independent. This is the main effect. Time saturates as they become infinite. It means the particle travels at infinite speed. This is known as the Hartmann effect. This is the main effect. Have experiments been done? Yes. More recently, these experiments have been done. I will not go over here. Before that, let me mention, I believe, yes. No, it is independent of the shape of the barrier. Right. Because I can always make any shape barrier as a bunch of rectangular barriers. So it will work out. Right? Now, I believe those experiments, not this one, but something similar, is being carried out by Professor Ramachandra Rao here. He most probably said he will not be able to come. But those experiments are being, not this, but some time delay experiments of the order of femtoseconds are being carried here. These are the lab experiments. That's why I find a university a very attractive place compared to just a research institute. Okay, now there is another time. This is a very interesting work. This is by Buttiker and Landauer, who introduced a varying barrier like that. So let me tell you the main point. You send in a wave, and the wave is going to come there. There is this oscillation taking place. So beats will be there, right? Supposing the initial one is some omega 1, it will be omega 1 plus omega and omega 1 minus omega. I switch on this variation at some time. Before the time, that beats will not be there. When I switch it on, the beats will come, but there will be a time difference. That is the time difference of Landauer and Whittaker. I will repeat it again. Before I introduce the time oscillation, I will get a wave there. That wave will only see the frequency of the initial wave. Then when I switch it on, the beats will start coming. The beats will reach there at some time. It was started at some time. The difference will be the time delay. Actually, your talk gave me some ideas which I will talk about afterwards. Okay, so let me go to the next slide. Next is Larmor time. This is also another very interesting effect. Supposing I have a particle which is spinning up like this, and at the barrier I put a magnetic field. Okay, what will happen to this spin will rotate. So I know what the initial spin is, I know what the final spin is, and so in between I know what the speed is, so I know how much time it spent. I will repeat it again. Supposing I have a particle which is in this direction, magnetic field is like this. It will turn like that or this way. It comes out. So how much turn does it have will tell me how much time is spent there. Okay, so that is the other effect. So there are multiple definitions of time. They all do not agree, but every one of them gives the Hartmann effect. Minor differences here, factor of 2, factor of 3 and things like that. Dwell time. There was some person who mentioned about dwell time. You did? Dwell time in a particle? Jayanto? No. I thought somebody don't know. Maybe then I am imagining things. Dwell time is the time the particle spends inside the barrier. So this is straightforward definition. Here it is, this one coming here. This also can be calculated. This is not a simple answer. There is no unique answer to this, as many things in quantum mechanics. Dwell time is a property of the entire wave function. It does not make any distinction between either reflected or transmitted. Hence, dwell time is not an accurate expression for transit time. It is just characteristic time associated with the potential barrier. It can be defined as, these are all straightforward way of playing with the whole thing. Nothing new. I am through with quantum mechanics. Professor Harikumar had told me that I should not keep everything fun physics, but have some quantum mechanics. There are a few more quantum mechanics fun problems, but I thought I am more interested in some of these fun problems. It is the following, that when President Kennedy was assassinated, a bullet went through him from the back. They had taken a video of that. The head moved backwards, not forwards. So this immediately brought a theory saying that the bullet perhaps came from the front, and this went to court. The court judge was a sensible man. He said, we cannot answer this question, let us go and ask a physicist about this question. Physicist was Professor Alvarez. He calculated and found indeed the head should move backwards and not forwards, because head is not a solid body. It contains a lot of liquids. So the bullet, when it is going forward, due to friction, it takes the liquid mass of the brain forward direction. One can calculate, I will show you the calculation. The momentum is larger than what the bullet comes, because it's heavier. So to conserve momentum, you have to go back. This, he went to one of these rifle ranges, took a melon and shot. The local experienced people said, you are wasting your time, the melon will go forward. But they were all proved wrong. So this is one of the most famous experiments. Here it is, and it is complete undergraduate physics, if not high school physics. Okay, let me just go over it slowly, because I wish those of you who are going to teach will use this example at some place or the other. It is here. Momentum forward. This is the momentum of the bullet, must be equal to the momentum mv of the melon. Energy must be this. Only a fraction of the energy of the bullet is transformed into melon's kinetic energy. Not all of this is transformed. So here it is. Where is it? The fraction I am taking, I am just some figure, 1000. Assume 10% of the kinetic energy TB is taken up by the fluid part of the melon. Then the momentum forward of the fluid is given by this expression, where TF is the energy of the fluid part. This gives, you can just substitute and calculate, you end up with this answer. Here we have assumed mass, substitute numbers here, all straightforward, actually class 12 physics and maths, and it comes to this expression. Thus, now notice, this is the main point, thus the forward momentum of the fluid, where is the forward momentum of the fluid here, root 10 TB is that of the bullet. It is 3 times more. This is what causes the melon to move backwards. Such a very elementary calculation which can be done. Now, people have performed it in a very nice way. I actually wanted to perform this, but I don't have the expertise how to use liquid nitrogen. I am sure here it must be child's play for people, and I am hoping that Nirmal will take care of it someday. I am sorry, Nirmal, I am bugging. You are sitting in the front, that is a mistake. Okay. Now, so what I will also share this paper. A ping pong can boy checks with this kind of counterintuitive phenomenon. The details are described in this paper. So here is an experiment which they perform. This is too big, but you can perform on smaller ones. There was a lot of ping pong balls kept, yellow ping pong balls, and then you put liquid nitrogen. And then you do something to make the liquid nitrogen boil, becomes some kind of a gas, and that gas pushes the balls up. You would expect the basket which contained the ball to come down, but this is what happens. And let me just see whether, how do I operate that? Can somebody help me with that? I want to click this. Can you please repeat it? See, the basket also went up. Completely counterintuitive. But I would have shown more. Let me just mention a few of them. All of us ride a bicycle. If you look at it carefully, the handle of the bicycle is connected to the front wheel. If this is the front wheel and the handle, it is connected like that. The point where that line meets the road is forward compared to the point where the cycle touches the ground. I could have made the design the other way. I could have made my bar further and do it this way. It would be unstable. Why? I will not answer that question here. Okay? And people have designed and shown the experiment, and indeed they are available in the various websites, and that's unstable. The other one is a regular bicycle rickshaw. Have any one of you tried to ride a bicycle rickshaw yourself, as I have? I learned this from Amitabh Ghosh, where we actually constructed the cycle. You must have seen it. And the cycle rickshaw, if you ride it, it will turn to the left. You need a torque to keep it to the front. Otherwise, it will not stay. Why? Of course, the reason why you have to turn it left is our traffic comes this way, so the cycle and it takes a lot of effort to do this. Again, why? And then Amitabh had designed one in which the rickshaw driver need not put so much energy. He had done some device. This is another one. There is another two in which Professor Jayanta Bhattacharya's son Shayak, he has given a very good explanation of it. They are available in the net. I have them, and this is called, if you have some kind of a boat, and if you turn it one way, the boat will remain remaining. If you turn it the other way, the boat will stop. These are available in various Amazon and so on. And the other one is called devil's stick. You take a thing and you on a rectangular rod and you make it rotate like that. You rub it like this, it will rotate one way. You rub it here, it will rotate the other way. Why? Then the last one I will mention is you have a train. The track bends like that, but the wheels don't get derailed. They continue being. This requires a very careful shaping of the wheels. Shayak has 2 papers on this, and I have seen them. They are of course brilliant papers. So I think I'll just stop here.
Any questions? Yeah, please.
Just a few comments.
Sure.
Actually, you are mentioning this Wigner relay and this Hartmann effect. Mandel did the experiment first.
Who?
Mandel, Jordan Mandel. Mandel did the first experiment.
I didn't know.
Showing that it is proving Hartmann's.
Oh, I didn't know this. I see.
Okay. Actually, we also didn't know about that. We did lot of work.
Can you share the details?
Yeah, sure.
All right.
I'll share the details. And the main point is that we also didn't know. We were working on the same thing with Girish Agarwal, and then we didn't know. And Professor Everly told us this is Hartmann effect. He educated us on this Hartmann effect.
I see. Okay.
Okay, that's a great thing. And all the details are there in our textbook, which we wrote in 1995. This Wigner delay, Hartmann effect, so on and so forth. There is a new twist to this problem, because this is connected to not just temporal shift is there is a spectral shift also. Okay. And this problem is intimately connected to the weak value amplification. So you can connect it to the Aronoff Weidman weak values, and you can enhance this effect by means of the weak value amplification techniques. That people often do. A lot of experiments are there. 2016, Professor Bliok had a paper, long paper on that in Nature Communication.
Who did?
Professor Bliok, Konstantin Bliok, and his team had a big paper on that. So that they show that they can enhance this weak value by means of weak value amplification, all these shifts and delays. Of course, there is a one-to-one correspondence between spatial shift, Bose-Einstein shift, and the Wigner delay. One in time domain, and other one in space domain. So it's just a comment.
Can I take 1 or 2 minutes more? Okay. There is also one more effect which I didn't discuss here, called the weak measurement. There, it is a paper in PRL by Aronoff or Vaidyan and so on, showing a very, very startling title: how can a spin a half have spin 100 components? Right. But it is not a measurement, normal measurement. It's called a weak measurement. People have named it weak measurement. And if you change your definition, you can do anything, and that's what happens. It's a very interesting thing, but unfortunately a little complicated for undergraduate physics. I don't think it can be taught at the undergraduate level. So that's it.
Any other questions from any undergraduates here? Any questions? Anybody? Okay. If not, let's thank Professor Mani.
Thank you.
Oh, okay. And
thank you so much, Professor, for this engaging and enjoyable talk. May I request the chair to kindly present a memento to Professor H.S. Mani as a token of appreciation.
Okay, so our next speaker is the University of Hyderabad's representative in the quantum mission, Professor Subramaniam. And what this slide doesn't say is that he did his MSc from the University of Hyderabad. Therefore, he has a money number of 2. And because it probably was taught quantum mechanics by Professor Ashok.
Vipin Srivastav.
Oh, okay, still money number. Okay, so anyway, and he is currently the leader of one of the groups in the quantum mission project, and I'm very happy to.
This works, no? Can I have the slides? Which is the thing? Pointer. Okay. It's a privilege to speak at this conference with such nice speakers. Okay, so the topic is quantum entanglement. A little bit of entanglement, you already got exposure from previous speakers, and this picture I've just taken from this sciencesource.com. Okay, these are the gentlemen who won a Nobel Prize for 2022, Clauser, Schrödinger, and Aspect, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. 7.5 crore Indian rupees shared equally. And this is a citation of Nobel citation. It's long, describes each person's work. Instead of reading that, pictorially, what Clauser did is basically has some atoms here, calcium atoms, illuminated by this special light, and something happens, and then measure the polarization of the photon coming out. And Aspect is actually done switching off the initial conditions in a clever way, and also higher rate of emission. And Anton Zeilinger shines laser on a crystal and randomly switch. That's why all these 3 people got Nobel Prize together. Okay, so the plan of my talk is that I'll speak briefly about quantum theory, or maybe the chronology of quantum theory till now, behavior of photons and electrons, then come to quantum entanglement, which defines what is called locality and realism, which brings us to Bell's inequality, and then briefly I talk about quantum operations. What are the valid quantum dynamical processes? In fact, entangled states can determine what is a valid quantum evolution. And finally, this is a major part, harnessing quantum entanglement. 3 simple cases, dense coding, teleportation, and secure communication. All right, so all of us have studied classical mechanics and quantum mechanics, part of the curriculum. So the major difference is, of course, very simple. In classical mechanics, you determine position and momentum from Newton's equations, deterministic, predict future from initial conditions. It's like in astrology. Values of variables revealed by measurement. Variables have those values before measurement, and that is what is called realism. That means if I measure the length of, let's say, this object, it has got, let's say, 10.5 centimeters. The object has that length, and the measurement reveals that value. So the value revealed is the real value that it has. That is the property of classical systems. For instance, you prepare a angular momentum state with L equal to 0.3 along x direction, then you measure z component, then you will find that it is 0, which is a classical object. There is no z component. However, in quantum mechanics, you have state determined from Schrödinger equation. You cannot assign definite values to x and p, assign only probabilities, average values, compute expectation values. It's like in gambling. You depend on probabilities. Values of variables revealed by measurement, still true. However, variables may not have those values before measurement. For instance, prepare spin angular momentum state with s equal to h by 2 along z direction. You prepared it. But now measure x component now, and it reveals the measurement reveals that it is non-zero. So which means when you reveal a value of Sx equal to h by 2, the particle may not have that before the measurement. It looks like that measurement itself causing that. This is more or less the chronology all of us have know. Planck 1900, Einstein 1905, they said E equal to h nu. For photons, for light, which is supposed to be waves, they said no, it can behave like particle. And the second number is the year in which they got Nobel Prizes. 1918 for Planck and 1921 for Einstein for this photoelectric effect. Bohr and Dirac, basically Schrödinger equation, uncertainty principle, just textbook stuff you learned. And more importantly, complementary principle. Bohr has come up in 1928. It's very, very essential in actually discussing his discussions with Einstein to defend quantum mechanics against local realism. This 1922 is not the work of this. For atomic spectra I got, that's why I put a star here. So quantum mechanics is very successful in explaining all the existing spectroscopic phenomena, and it is responsible for all the technology that we have, including there's laser light here, there's a computer, your mobile phone, everything is coming from quantum mechanics. Quantum entanglement, which is basically part of quantum mechanics only, is offshoot. EPR products, Bell's theorem, quantum information computation, evolution from 1930s to 2022. All right. Let us take a simple system. Let's say you have a simple photons coming one at a time, sends one at a time, and then there is a simple beam splitter here. So splits half this way, this way. You have a detector 1 here, detector 2 here. They will detect 50% of photons here, 57 photons here. However, each photon will either come here or here. It is not that you split a photon and then half is coming here, half is coming there. If you send a million, half a million here, half a million, that's correct. If you send only one, either this will click or this will click. Same thing is true for electrons also. Now, if you have an interferometer where the source is coming, the beam splitter is split into two, and you have a mirror, it comes here, and other beam splitter, and then you can arrange this arm length such that all the photons will come here and zero here. It's basically interference. Similarly, electrons also will exhibit interference. And in the same setup, if you introduce some new element here, to detect if a photon is passed through this without actually absorbing it, then the interference disappears and you get 50%, 50% here. The same thing for the electron spin. You have Stern-Gerlach experiment, projective measurement you're doing. So any component of spin half can have plus minus h by 2 values. Let's say you have spin up, which is z up. Then this Stern-Gerlach apparatus has a magnetic field along z direction. Then all the particles will come and put in this box where spin up. And there will be zero in the spin down box. That's because initial state is up and then you put magnetic field in z direction. However, this polarizer, instead of putting a z field, you put along x direction. Then it projects this along x direction up or down with equal probabilities. This is analog of splitting. However, you cannot determine whether it is up or down. For instance, let's say here is coming, it can come here or here, but you cannot define which particle will come here or here. Quantum mechanics cannot determine. It only tells you probabilities. At the end of the day, million have come here, maybe 0.3 million here, 0.7 million here, that is okay. But you will not be able to say where before one coming, which will come here or there. Seems that measurement apparatus determines the direction of the spontaneous direction. Here I put x direction, it will come x h by 2 or minus h by 2. If you put some other direction, it will be taking that direction. Are there any hidden variables that preset the spin component value? That was a question for about 50 years. It was resolved. Similar to the outcome of tossing a coin with the result head or tail. For instance, I have a coin, I'll toss, it will be either up or down. However, the coin has a large number of hidden degrees of freedom inside, right? So if you solve all the Newton's equations, you can maybe find what is the outcome. So that means hidden variables actually determine what is the outcome. Whereas you have spin halves, there is no hidden variables anymore. Okay, this is the EPR paradox. Just want to mention a little. It's actually a classical correlation. Actually, EPR paradox of the quantum correlation. Two photons going either side. So this is a simpler version. So you have a box, there is one ball. Now I cut this box two parts. This left side is B1 and right side is B2, and B1 is gone left side and because very separated. So now the ball could be anywhere. So either ball is here or here. So now the person sitting here, if he opens the box and finds the box here, that means he knows that the box is not here. So it looks like without doing any experiment on B2, the reality, physical reality of B2 is known to B1. So is there anything hanky-panky going on? Actually nothing. You can analyze this and see that, okay, this is the initial correlation that you have. You have the correlation here, nothing has happened. The same correlation is here. Whether they're here next to each other or far apart, that is not changing. And what is surprising in the quantum world is that the correlation seems to exist for a long time. Okay, this is of course Einstein, who has had a very serious objection to quantum mechanics. He says that physical theory cannot violate realism and locality. The realism I already told, quantum mechanics doesn't have any realism. Locality means that if I do something here, let's say in this room, then let's say in physics building, something should not be affected. So the effect should be local, and then it should take some time to go to the faraway places. So quantum mechanics seems to violate both of them, so he's unhappy about it. So quantum theory seems to preserve non-local correlations, and that's how it defines local realism. What is more bizarre is that this is actually mentioned in Professor Subrato's talk. Let's take a system AB, total system is AB. Classically, the total entropy is non-zero if one of them is non-zero. For instance, let's say entropy of A is non-zero, then the total system is entropy is also non-zero. However, in quantum systems, quantum mechanics, total entropy can be zero, but part A can have or part B can have non-zero entropy. That Bell's theorem basically says that local hidden variables cannot reproduce quantum predictions. Meaning, if you construct any local hidden variable theory, it will not be able to give you results that quantum mechanics gives. So Bell has come out, constructed a Bell correlation that can be measured experimentally, either to rule out hidden variable theory or to validate it. So these experiments of Closure and Aspe actually have shown violation of this inequality, which means that local hidden variable theory is not tenable. Only quantum mechanics is a tenable theory, so quantum mechanics wins. Okay, so that brings us to quantum entanglement. So you have two spin-half particles in spin S equal to 0 state, the unique state, up, down plus down, up. This is particle 1, particle 2, and this is particle 1, particle 2. So this is one state. However, if you look at the particle, individual particles, for instance, particle 1 can be up in this part or down in this part with equal probability. So in such a state, we'll say that particle 1 and 2 are entangled. So if spin is measured for particle 1, then we also know the result of particle 2. So if you have such a entangled state, one particle is here and another particle is in Mumbai, then by measuring particle 1's state, let's say you found some value up, then we know that particle Mumbai particle is in down state. So this is what is the EPR. And what more, this state, you can also, this is in Z basis, you can also do it on the X basis. That means you measure the particle 1 in X direction spin, then if it is plus, that means the particle in Mumbai will be, X component will be the minus state. And these are called maximally entangled states or Bell pair states. There are 4 of them. In fact, there are many of them. Okay, you can simply write as 4 of them: up, down, plus, minus, down, up, or up, up, plus, minus, down, down. This is for the 2 spin-half particles. So let us formally define entanglement. So let's say you have a total system consisting of subsystem A and B. Let's say the total system is in a pure state, either direct product or entangled. So this is in a pure state psi. This is psi stands for the total system AB. So the entropy of the total system is 0 because it is a pure state on single state. And the subsystem will be described by the reduced density matrix rho A by tracing out B on the total system. Now, if this rho A happens to be a pure state, then the entropy of this density matrix 0 means that the entanglement between these two is 0. If the reduced density matrix is a mixed, then the entropy is non-zero, of course, and then that means the entanglement is non-zero. So here we are defining entanglement between A and B by the subsystem entropy. Either entropy of A or entropy of B will be same if it's a pure state. This state is not entangled because up here, up down, so you can take up common. So the particle A is in up state, particle B is in up down, up plus down. So superposition is not only enough, but you need much more. Should not be factored. So you have down up plus up down. This cannot be factored into part A state and part B. So any state which is not direct product, you can say that some entanglement will be there. And similarly, if you have a 2Q state system, this is a 2-state system. Particle A has 2 states, up and down. Particle B has 2 states. Q state systems, you can have phi 1 chi 1 plus phi 2 chi 2 like that. This phi 1, phi 2, phi q are orthogonal states, and similarly chi 1, chi 2, chi q are orthogonal states. This is the maximal entangled state. Entanglement for this state is log q base 2. So in this notation, the 2-state problem, entanglement will be 1. So Bell pair has entanglement 1. So bipartite state rho AB, pure or mixed, then if rho AB is of this form, rho A times rho B, it is an entangled because it's direct product. If rho AB is some P times rho A rho B plus Q times gamma A gamma B, it is unentangled because it's the incoherent superposition of direct product states. It can be constructed using local operations in classical correlation. Such a state is deemed as unentangled. And if you have such a state, rho AB is a pure state, but the state itself is not a direct product, then it's entangled. It's a coherent superposition of direct product states. And if your rho AB is the form, let's say this state comes with some probability P, this state has some probability Q, it can be entangled or unentangled. It's an incoherent superposition of entangled states. And there's something called entanglement monogamy, which only means that if you have multi-party states, let's say in this room so many particles, they're all, look at the whole state. If A and B are maximally entangled, implies that A is not entangled with any others. So maximal entanglement is like marriage. Okay, if you are married to somebody, you cannot be marrying to somebody else. Ideally. So this, there are large number of entanglement measures. One we already discussed. If a joint state is a pure state, then the entropy of subsystem is an entanglement measure. However, if you have a mixed state, then you have Wooter's formula. Let us not spend too much time on that. There is also Perez criterion. If a density matrix becomes negative under positive partial transpose, that means there must be entanglement. There is a localizable entanglement, there is a CMI entanglement, etc. And so on. All these I have written because I have worked on these sort of things. There are actually dozens of entanglement measures. If you know half, if you know 6, you can write 10 more. Okay? The only criteria should be that it should be monotone. In the sense that one measure says that A is more entangled than state B, the other measure also should say, then it is an entanglement measure, monotone. Okay, this Bell inequality violation, this is the context in which they got Nobel Prize. So basically, EPR argued that quantum mechanics is not physical theory, it's not incomplete. But Fornheim in 1932 proved that there is nothing other than quantum mechanics based on simple mathematical axioms. You cannot consider a better theory than quantum mechanics. And John Bell, he constructed a simple measurable quantity based on hidden variable theory. Hidden variable theory means taking realism and locality into account. Then,
You know, we always reduce EPR to that Einstein thought that it was not a physical theory. But actually, what really Einstein was worried about is that the process of measurement violates his relativity because it seemed to occur.
I'll come back to that. I'll come back to that. Okay. So then we'll come back to this closer element. They actually showed that violation of Bell inequality. And what is Bell inequality? It is very simple. You have an entangled state. One particle is here, let's say A, and one particle in some other room. So you measure spin of this and measure spin of this. But here you measure along A1 or A2 directions. And here measure B1 and B2. So A1 will be A1 direction if you measure, either you will get plus or minus 1. If you measure A2 also plus minus 1. Similarly here. This CHSH Bell correlation is simple. This is this. A1 B1, A2 B1, A2 B2 minus A1 B2 expectation value. Expectation means you repeat so many times and see what you get. Now this is so simple that it is astonishingly simple. If you look at B2 minus B1 or B2 plus B1, if this is 0, this is 2. If this is 2 plus minus 2, this is 0. You can this whole thing can be written A1 times B1 minus B2 plus A2 plus B1. So if this is 0, this is plus 2 or minus 2. And this is maximum 1. So that means this will be bounded by plus minus 2. So this correlation is always bounded by 2. Magnitude of S is bounded by 2. This is basically local hidden variable theory. Why it is local hidden variable theory? We are thinking that these are independently measured. They have independent existence. However, quantum mechanics, if you go and measure, do quantum mechanics calculation, A1, B1, these are all, for these directions, it is simply cos pi by 4 is 1 by root 2, and you will see that this number becomes 2 root 2. This is a maximal violation. So, hidden variable theory says that it is less than 2. In quantum mechanics, it is possible that it is bounded by 2 root 2. So, when in the experiment, if you find between 2 and 2 root 2 some values, that means hidden variable is out of the window. This is the same thing what they have done. This is I have taken from Sakurai's book. Actually, the Bell violation and entanglement I want to learn. So you can take a 2-qubit state. You can consider the correlation matrix. Basically, you have rho 1 to here, sigma 1 m, sigma 2 n. M will take 1, 2, 3, x, y, z. N will take x, y, z. So it's 3 by 3 matrix. It's a second rank polarization tensor. So you take the two largest eigenvalues of this matrix T. Then beta is 2 root u1 plus u2. These are two largest eigenvalues. Herdecke in 1995 has done that. Beta greater than 2 is violation of Bain inequality, and maximum violation is 2 root 2. Then in 2002, Sanardi has written an article on Heisenberg antiferromagnets where he showed that the local neighbor entanglement can be related to this Bell violation. So it's fine. Bell violation implies entanglement. C is the entanglement measure, not 0. However, in this range, when beta is between 2 and 2 root 2 by 3, you will see that there is no Bell violation, but entanglement is non-zero. Okay, so that means all entanglements may not lead to Bell violation. No. Okay, now how much time I have? How much time I have? Okay, so these are simple evolution of a quantum state. We'll go through quickly. So starting from here, you can change the state of a system. Let's say 1 qubit state. So if it is a closed system, all it can happen is a unitary evolution. So that means up state can become plus state. So it's the interaction with outside magnetic field. If it is an open system, that means this particles in an open system, then evolution can be unitary or non-unitary. The state up can go to this. So now you have this a mixed state. So without non-unitary evolution, a pure state cannot become a mixed state. So if you have 2 qubits, let's say they evolve from pure state to pure state, let's say up to this state through this interaction. Then here is a direct product state, so unentangled. So each state of each particle is up, which is the pure state. However, in time they evolve into this state. Here the particle rho 1 and rho 2 both are of this state, so it's a mixed state. So which means that the whole is evolving in a pure to pure, which means unitary evolution, but part of the system, particle 1 actually undergoes a non-unitary evolution. So this is the hallmark of open system dynamics. Interactions implies entanglement. This entanglement is a 2 qubit state. So this is unentangled state, AB state, and this is entangled state for AB state. However, for A, the dynamics is actually decoherence. So if you say decoherence or entanglement is actually the same thing, but the way you interpret is different. Okay, so this 2 qubit state is entanglement. The 1 qubit actually decoheres. This is the open system evolution. As a density matrix goes to a density matrix. Now through some operator. So what are the valid operators? So any evolution of S can be generated by unitary on S plus E. So this system, whatever it is, you add some environment, make it close. Once it's closed, a unitary evolution. So you take a unitary evolution on S plus E. This Steinspring factorization theorem 1955 is a very phenomenal theorem. What it says is that every evolution of S can be gotten from a bigger unitary evolution. So start from rho SE cross rho E with a factorize state, do a unitary transformation, rho prime you get by unitary. Now, here if you do partial test, you get rho s, and here you do partial test, you get rho s prime. These two are related by this evolution. So, the state rho s goes to rho s prime, as in terms of cross operators is written like that, and this is actually a completely positive traceable map or CPTM map. Sometimes it's called super operator or a quantum channel. This is the most general evolution of a quantum system. Why I talked about this is a very simple thing, very simple reason for that. What evolution is actually a valid evolution for an open system. So rho according to rho prime is a map. So one state is mapped to another state. So this map is a positive map, which means that rho prime eigenvalues are between 0 and 1 and trace rho prime is 1. So that means density matrix is mapping to density matrix. So any positive map will do this. But that is not enough. What has to happen is, you have a joint state evolution, take rho AB, evolve only A is evolving under this map and B is not evolving. However, rho AB goes to rho prime AB, then rho prime is still a valid density matrix, then I call this map completely positive map. So which means that you need a completely positive trace preserve map. That is only the real valid thing. Now to check a map is a completely positive, all you have to do is take a state of a system and put a B as an environment. For all possible B you have to search. This is a horrendous, computationally very complicated job. However, practically if a system is d-dimensional, construct a maximally entangled state with d-dimensional environment and check the action of the map on the system S and identity on the environment, and if the maximal entangled state gives a valid state density matrix, that process is a valid process. Okay, there is also no signaling theorem. For want of time, actually, okay, this is actually answers your question. Okay, this is a very important theorem. If you have a rho AB go to rho A prime through this process, reduced density matrix of B before and after. Here it is rho B, here rho prime B. They are exactly the same. So which means B sitting in Mumbai, by doing a experiment on his system, will not be able to know whether I have done something in here. I have done a process on my system. If I have not done anything also, he is doing the same. So which means that the communication speed from A to B is actually 0, is more restricted than Einstein. And however, after doing this process, if we do a further unitary transformation on the combined system, joint unitary evolution after QDP can distinguish if QDP is occurred or not for a time greater than separation by C. Thus, is the special theory is increased. So quantum mechanics is never a contradiction with special theory, because Dirac has already constructed relativistic quantum mechanics. There is absolutely no.
We usually use Schrödinger to calculate.
Yeah. So there was no. So which means there are two things I want to say. The part does not know if joint state whole is decohered in a non-unitary evolution. Similarly, the whole joint state does not know if a part is decohered in a unitary coherent evolution. This is the hallmark of the whole thing. So maybe I think I have 5 minutes more.
No, I think 3 minutes.
3 minutes. Okay, so then instead of going through this many examples, I'll only talk about quantum secure communication. Okay, this so if you have entanglement, you can do many processes. Many information processing tasks can be achieved by using entanglement. Entanglement is like a resource. One of them is secure communication. Let's spend 1 minute on this thing. Secure communication means A and B want to communicate securely using a key. Okay, this is Vernon's cipher, is more than 100 years old. This is one-time pad. What it means that A wants to send B a message. Instead, what he does is, this is a message he wants to send. He will take a key K and adds to it. M plus K is giving N. So add means 0 plus 1 is 1, 1 plus 0, like that. Then B receives N, but this is not the message. And he decodes. N plus K again he does, he gets N. That's because K is being added 2 times. If you add any 1 plus 1 will be 0, or 0 plus 0 is also 0. So this is what is called Vernon's cipher. A and B use key only once, communication is secure. So security basically boils down to key distribution. If A and B have a key, preassigned key, then they can communicate securely. This RSA cryptography This is a cryptography based on number theory of mathematics, and this is widely used. In fact, all our password security is because of that. How it works is a simple thing. You take two big prime numbers x and y, multiply that and call it z. And then call this p x minus 1 to y minus 1. This is Euler torsion. So for encryption, choose a number e less than p. This p is there. Choose a number e less than p with no common divisor with p. Decryption number d times e equal to 1 modulo p. That means e is the inverse of d is the inverse of e. So encryption public key is this z and this e, and decryption private key is that this z and that d. So sender encrypts m as n equal to m to the power of e modulo z. Receiver gets n and decrypts to m as m equal to n to the power of d modulo z. So this is how it works. Eavesdropper intercepting communication cannot crack the code easily. Why? This x and y, let's say 50 digits each. So z will be 100 digits long. Then to find factors, it will take some time. If it's a supercomputer, you can do it in 10 minutes. So when you receive a password, they'll say that it expires in 10 minutes. So the process finishes, so it is secure. But understand that security relies on inability to find factors of a large number. A quantum computer comes tomorrow, there is no limit, because all password security is compromised. But however, you can do quantum key distribution. What you do here, A and B get entangled straight from the source, 0, 0 plus 1, 1. A is sitting here, B is in Mumbai. This repeat, many. So the first time I labeled as state 1. Second time I got state 2 and so on and so forth. A and B mutually agree to do measurement either in Z or X basis. Before B moves from here, we agree that our measurements will be done as Z or X. This is not known to anyone, which basis we do. A in Pune measures in randomly chosen base Z or X basis. Outcome is 0 and 1. B in Delhi measures in randomly chosen X or Y basis. This is also Z or X. Outcome 0 and 1. They repeat, they got let's say 1,000,000 copies, they'll repeat 1,000,000 times. So now A and B have a huge number of digits, 0, 0, 1, 1 like that. Now A and B disclose publicly the sequence of bases used by each. Because Z and X randomly I am choosing, so I'll say that first time Z, second time Z, third time X like that I disclose it on my website, and B also discloses it, and then they match. They compare their bases, keep only outcomes for corresponding match of bases. So wherever the bases match, they keep only that sequence, delete the rest. And then compare some chosen bits out of that relay for eavesdropping and delete them from list. Now A and B each have the same remaining long sequence 1100, that is a secure key. And quantum security is from physics principles. It is impossible for anybody to crack it. Only thing is that eavesdropper can actually spoil the matching. So that's why we have to compare. Thus, a secure key is generated purely randomly using quantum correlation. So I think I'll stop here. Before that, this last slide is very important. How do you know if the joint state is entangled state? What I'm saying is, we are saying that if you have entanglement, you can do dense coding, you can do teleportation, you can do secure communication. But let's say you have an entangled pair. How do you know whether this is entangled or not? So let's say the entangled state is here, you do a measurement in a direct product basis, 0, 1, 1, 0, 0, 0, 1, 1. Since output will be one of these, they are unentangled, so it will not reveal anything about the entanglement here. However, this entangled state, if I measure in the joint measurement basis, entanglement basis, 0, 1 plus 1, 0, 0, 1 minus 1, 0, 0, 0 plus 1, 1, 0, 0 minus 1, output is anyway entangled. I don't know whether input state is entangled or not. So that means if I have an entangled state, if I want to check if it's entangled or not, I will not be able to do it. But the proof of the pudding is in the eating. If I have the entangled state, I'll try to see if I can do teleportation. If I can do it, then I know that I had it. Okay? So entanglement is like quantum currency. Currency because this is what you have to pay to do some job. It's quantum because it is not there sometimes. So you cannot put in a bank and issue a check against it. Because it can bounce, you will be in jail. Thank you for that.
Yeah, any questions? Yeah, go ahead.
Sir, in quantum mechanics, entropy can be negative.
Which entropy?
general entropy, the disorderliness.
No.
So when you consider two object, whole system A and B, the total entropy will be 0, but one system entropy will be non-zero.
Non-zero, other also will be non-zero. Both are same. If A and B total entropy is 0, A has entropy 1, B also has entropy 1. So total will be 2 if you add that.
No. Total entropy will be 0.
Total entropy is 0, but rho A entropy plus B entropy is not total entropy in quantum mechanics. Understand that. Total state has 0 entropy.
And one more question. In the local hidden variable theory, the S total state constant less than or equal to 2, but in quantum mechanics it is less than or equal to 2 under root 2.
Correct.
Means it is violate the maxima. So how it is possible? It's just measurement or it is
No. Wait. Local hidden variable theory is a fiction. It doesn't exist. Quantum mechanics is reality. All this is coming from quantum mechanics. Bell has constructed a local hidden variable. Within that, he constructed a measure to test experiments. Experiments are telling that the hidden variable theory should be there or not. Experiments are violating the Bell inequality, which means that the hidden variable theory is not there.
I see.
Hello. Hello.
Yeah, go ahead.
Thank you, sir. Had a knowledgeful talk. So I have two questions. So first is, you told in your slide that after admixture or mixing of the states, there is a unitarity will not be violated. Am I right?
In what context?
In your slide, after admixture or after entanglement, the unitary will not be violated. Am I right?
I don't know exactly what you're saying. Okay. Let's say I'm right. You're right. Then go ahead. I'll answer the question at the end.
Okay. So the question is, if unitarity will not be violated, then can I use, because I am from the weak part, means the neutrino, I mean working in neutrino, so can we use the neutrino can neutrino entangle, because
yeah, why not? Yeah.
Okay, so one thing, if I have two states and one state has a some phase, e to the power exponential some phase is there, then is this possible to get some signature in the after entanglement there is any signature of this phi?
No, why not? It will be there.
So then we can use this in for Majorana case, because in Majorana case there is a
sure. Okay,
case,
let me answer that question for everyone. You have state phi, it has no entanglement. If you evolve unitarily, it can get entanglement. That's right. Okay.
Okay.
And you think are entangled and tripartite entanglement.
Okay. Thank you.
Any more questions? Oh, then let's thank the speaker again. Wait, I have to go to it.
Okay, may I request the chair to kindly present a memento to Professor V. Subramaniam.
Okay, so it gives me great pleasure to introduce the next speaker, whom I also have known for a long time. This is why they call old people to chair sessions. Of course, this doesn't really tell you what he's famous for, so I should tell you that. No, it's really interesting because they should know. See, the thing is that if you think, why are the constants of nature such that this universe exists? Are they fine-tuned? Okay, and that would be, if they were so fine-tuned, you would say the universe exists because God exists. But what Partha Majumdar with his collaborator, Professor Kaul, said is that if the constants are to be what they are, and there are so many of them at such different scales, they should be another symmetry, and that is supersymmetry. Of course, that symmetry has not been found yet, but we are still looking for that symmetry. And so that, but the idea of constants independent of small variations,
this is for you,
and
so I was showing you.
able to be denormalized was done by realize it that the idea was 1981.
Yeah.
Was the paper about called that really made it seriously looked at. So one should say history, right? Okay. So please, and of course, then after that, the quantum mechanics is that even black holes have some quantum mechanics associated with it, and that's what the other thing he's famous for.
Thank you very much, Bindu, for that very eloquent introduction. I'm kind of reminded of this, that, past sins, and I call it a sin because if it was true that I found a really new thing about nature, I would be celebrating, but nature refused. Okay? So I decided to do other things. My friend Ramesh, for a long time, believed, I don't know if he still believes, I haven't been in touch with him, that, one day you might get a call from, where, Stockholm. I don't believe that. But the question that I want to ask you now is, okay, so. Just PDF file, so this is always a problem. You can't read it, of course. So basically, the way I would like to begin is to remind you all that the four fundamental interactions, it's only gravity where this question arises, because all of the others have been formulated nicely as quantum field theories, which of course rely entirely on the axioms of ordinary quantum mechanics, which you have been hearing about since morning. So the question now arises, what about gravity? And why is even there a debate? Well, it's very hard to do, for one. Secondly, the scales are so completely different. I will give you the number right away, 10 to the minus 33 centimeters. Of course, that's an impossible scale to achieve in any kind of experiment. So, why should we think about physics at 10 to the minus 33 centimeters? What I'd like to do is make a case for it. It's here, very good. Yeah. Starting with the way, after Maxwell, and for a long time, 50 years after Maxwell, people believed that, yes, light was made up of electromagnetic waves. That's well known, and you study it at various levels. Now, why would this 26-year-old man who didn't have a job in physics after he did his PhD, pretty bad, right? Because he was working in a patent office as a clerk. Why would he even think of a change in the laws of electrodynamics as laid out by Maxwell, starting with Faraday and so on? So that's where we begin from. But remember that this was the time when the right-hand side had already begun to show departures from what people like Maxwell had assumed, namely that it was not a continuum source anymore. Charges and currents, so you didn't have a bag of charge where all this charge was smeared around. You didn't have a continuous flow of current. Instead, charges were quantized. So I've classically written down this expression to underline the nature of discreteness of charge. And this notation is known to you, so I'm just giving you the way electromagnetic waves are supposed to be generated by a bunch of discrete number of charges. You can count the right-hand side, but you can't count the left-hand side. Now that Einstein found weird, and this is his argument. So he says that there must be something wrong in this. And yet we do problems from Jackson or whatever book you want with such kinds of things. I mean, you of course can take the particular case of I equals 1, and that's well known. This is a simple point charge, and you can solve this to get the linear Beaker potentials, right? So this is not something very mysterious. And yet, why was Einstein worried? See, this is what he was worried about. Two particular phenomena in which all the energy of matter was converted into radiation, and all the energy of radiation was converted to matter. Okay? The first is the black body radiation, and of course, I'll come back to why I write Bose here. And the second was the photoelectric effect, which was already mentioned. Then he picture, okay? Those are these little formulas signify that. And this generalizes when you talk about lasers and stuff like that, because you can think of a quantum field, a free quantum field in particular, like free photons, free particles, as harmonic oscillators, okay? A whole bunch of uncoupled harmonic oscillators. So this is what happens in a laser, for instance. And then you go further and talk about the interaction of photons and electrons. All that is known. And some of you who are in the more advanced classes will be looking at these beautiful diagrams known as the Feynman diagrams. And you can see those guys which started it all. This is Feynman, and they're all the great luminaries of the time. This is, I think, Schrödinger, this is Willis Lamb, so on and so forth. And this is the Solvay conference of 1949, which changed the course of physics forever. It also told you that you can do calculations at an incredibly precise manner using these diagrams and the Feynman rules and so on, confirmed by Schrödinger's very mathematically profound ideas. And then you compare with experiment and look at this accuracy. So my point about this accuracy is we hear a lot about what is true and what is not true. Get this accuracy, then I'll believe that you're talking about the truth. Okay, so this is a definition of truth, if you will. But then all this beautiful quantum stuff, you ask, hey, what happened? We were told that if you have a simple pendulum, t is 2 pi square root of L by g, right? Then you solve the harmonic oscillator. Classically, you got cosine omega t, sine omega t. Where is all that? Where is that hiding in the quantum domain? So you know that the quantum harmonic oscillator is often written in terms of occupation number states, which give you the energy eigenstates. If you take any of these energy eigenstates and look at the wave function, you get some weird, complicated functions like Hermite polynomials and so on, right? So where is the cosine omega t and sine omega t? Those high school things that you learned first time you learned about this. Well, this is the issue of coherent states. You have to take a particular linear combination of the occupation number states, and then if you look at the expectation value of the x in that particular state, these are called coherent states, you get your high school answer back. Beautiful. Of course, these states also give you the minimum uncertainty. So they are very classical-like, and yet they are quantum states constructed in that way. And I should mention that this was applied by none other than the great E.C. George Sudarshan, and in some ways replicated by Roy Glover. And I'm sorry to say that you can guess who the Nobel Prize went to, because Sudarshan did not get a Nobel Prize. Sudarshan discovered two things for which he didn't get the Nobel Prize. I might as well mention that because quantum optics was mentioned. So he discovered the field of quantum optics, and Girish Agarwal was a close associate of his. And he also discovered the V minus A structure of the weak interactions. So Sudarshan used to say that people who had used his work and done far less important things have got Nobel Prize, but he has been ignored. Anyway, but they found, so the answer was, the question was, where is the continuum then? So you have these photons, how do I find the continuum? The answer was simple. Look for coherent states of quantum electrodynamics. And then you can show that they satisfy equations which look like the same old Maxwell equations. Okay? That work is still not completely I should say, kosher, but I think the basic physics has been worked out by these people. Now, I shall quickly review special relativity because I was told by some of the organizers that there will be young people who still haven't met special relativity yet. So I shall go very quickly over this. And to the experts, my apologies. This always happens in a mixed audience. So this is what we call a light cone, which was, by the way, not invented by Albert Einstein. It was invented by Einstein's professor, Minkowski, okay, Hermann Minkowski. And this light cone is a geometrical way of representing space-time structure. So this is, the edges of the cone are the paths of light, and you or me will have paths which go from here. So this is the future, that's the past. So we have this prejudice about going to the future, and you can see that if you're just standing here, you still move a long time. I mean, this is obvious, right? Now, you actually can't go here, because then you'll have to move at a speed faster than the speed of light. But now let us turn on gravity. See, I'm rushing a bit because I have some amount to discuss. If you look at light under gravity using the principle of equivalence, okay, again, enunciated first by Albert Einstein, then you find this weird stuff. See, this is the Huygens construction. So you have a waveform, and then you construct these semicircles, and at every point on the waveform, join the tangents. This is how light should propagate. But yet, when you have gravity, if this is happening in the presence of a gravitational field, you have this situation, which means light must bend. Well, actually, it's the wrong way, but anyway, never mind. It travels along curved paths. Now, that itself is a great mystery, because light does not have mass. It does have energy and momentum, but no mass, okay? But that happens. Light also changes color as it travels in gravity. It's sometimes called the red shift or blue shift, depending on whether the color goes towards one end of the spectrum or the other. And what this means is the following. So this is my favorite analogy. Suppose that gentleman way in the corner wanted to take the shortest path to come and give me a box because he's tired of my yapping away. But you know, if he tries to really take the shortest path, people inside are going to object. Hey, what are you doing? So he has to turn around like this, take a curved path, because that's the way this room is set up. It's the geometry of the room. So when light propagates, you see, it curves not because there's a force acting on it, but because the geometry in which light is propagating itself is curved. And it turns out that it's true for every particle. And therefore, you have this situation compared to special relativity. You see that if you just for a sec go back to the special relativity thing, this was the light cone, and if special relativity was all there is to it, one light cone will describe all events in space-time. I mean, this is so weird, right? This is such a powerful method. One light cone, all events of space-time for us, for our predecessors, and for our future progeny. But unfortunately, there's gravity. So what does gravity do? Gravity tilts the light cones, okay? So something that was supposed to go here, let's say from there, now has to take a different route, because you can see that there is a tilt between this and this. There's a tilt between this and this, okay? So the tilt just means you can always draw local light cones. So the local geometry of space-time is unaffected by gravity. But then if you go to another point, then there's a difference between this point and that point. That's really the thing that I'm trying to say. So when tilting of light cone, how much should it tilt depends on what is called the curvature. But what causes curvature? And this is again a step that Einstein took away from Newton, just like with special relativity, the postulate of massless particles is away from Newton. Here is another one. So this equation is the Einstein equation. The left-hand side represents curvature. Don't worry about the formula. I don't know why I wrote it with indices. Never mind these indices. And this one is just the energy momentum density, because we have a local theory of every space-time point. So this is curvature at every point, and this is space-time. This is the matter energy momentum density, which is supposed to cause curvature. And this equation is the equation of a particle in a curved space-time. It's called the geodesic equation. See, the geodesic equation is a bit weird also, because usually you would think that, oh, gravity should cause a force, an additional force on the particle. That's the Newtonian viewpoint, but no. What happens is the particle will always take an extremum direction, extremum path. And that means that its acceleration is actually 0. So acceleration, the whole thing is the acceleration, and this is 0. That is what is called a geodesic. Now, so this is something that you see from here, energy momentum. So anything that has energy momentum will curve the geometry, like very powerful laser light will curve geometry, okay, even though it has no mass. Now, if this is indeed laser light, of course, is dynamical, right? Because it's moving photons or oscillating waves, depending on whether you think about it classically or quantum mechanically. So this is changing with time. That means the geometry also is changing with time. Now, if the geometry were to change in time in this room, that would be incredibly difficult to comprehend, right? Because you might suddenly think that the wall decides to do this, and the roof decides to come down because an idiot is speaking here on space-time geometry. So you have to be very careful, right? It is happening. The walls are responding to my speech because there is energy. But the response is so tiny that you can't tell anything, thankfully, okay? So space-time geometry is actually dynamical. But how much the space-time geometry will dance depends on how much energy is dancing around. Okay? And this is from John Wheeler, matter tells space-time how to curve, space-time tells matter how to move. Okay? We have direct evidence now, experiment. Oops, did I do something? Okay, it's going to come back. I'm sorry, I didn't do anything, at least not knowingly. So what are the evidence, direct observational evidence of a dynamical space-time? Gravitational waves, there's the ripples of space-time, little ripples. Like I said, it's happening in this room. Then, of course, we have the idea of an expanding universe. What it means is the geometry of the universe is expanding, okay? The entire geometry. It's in an intrinsic sense, not that you've placed the geometry in a room and you're letting the room expand. No, the room itself is the universe, and it's expanding. So these are slightly tricky if you haven't seen it before, and of course, black holes, my favorite. Problem with black holes, Professor Bamba was asking me, you're doing the black holes, now we should have another conference on black holes, 50 years or 100 years or whatever. Yeah, probably. The problem is if you get into them, you can't get out of them, right? You know that. So why do we trust general relativity? Well, sorry. This is, of course, the perihelion shift of Mercury. And this is an incredible thing that Einstein said, that the way that planets move around the sun is no longer an ellipse, which is fixed in space. It's rotating. So the curve actually never closes, right? And it happens not just to planets. It happens to the star S2, which is going around our Sagittarius A star, which is our friendly neighborhood black hole in the center of the Milky Way. And it's going around exactly in the same fashion with a perihelion shift, okay? And then this is gravitational lensing, the bending of light under gravity. This is something has to do with a time delay between two laser beams, and this is the red shift. So these are experimentally observed consequences of general relativity. There's also more for the dynamics. One of them is very recent, 2015. This is the gravitational wave about which I'm sure you've heard, how if you superimpose the two signals, which were 3,000 kilometers away, miraculously they sit on top of each other. This is just absolutely marvelous. And then you have this, which is a cosmic microwave background, which also has to do with a dynamical gravity. And finally, this is the Event Horizon Telescope picture of this galaxy I think M87. This is, by the way, not a black hole. It's the photon shadow, but I will not get into that. But I want to now come back to this question of discreteness versus continuum versus discrete. Because the question arises, what about gravity? So you have a curvature which is a smooth, continuous function of space and time. And yet you have energy momentum, all energy momentum that we know of matter. By matter, we also include radiation, is made up of small bits, thanks to Einstein. So again, we have this dichotomy. One side of the equation is a continuum, the other side is not. Okay? But then you could ask, well, Einstein found these two wonderful phenomena in which the energy of one was converted to the energy of other, right? And he showed that there is a contradiction unless you change also the continuous left-hand side to discrete, to countability. And there's no such experiment in the case of gravity, but I asked the same question, okay? Can discrete bits of matter produce a smooth continuum geometry? So this business of continuum versus discreteness might arise when you have these conversions, matter being converted to space-time geometry. That's what a black hole is, right? You have a star collapsing, and then all the star is gone, leaving behind this weird space-time called a black hole. And then we have space-time geometry converting to matter. Well, Big Bang, there's nothing, right? So the Big Bang is the opposite kind of transition. And both of these involve what are called space-time singularities. Okay? What's a space-time singularity? Well, this is one example of a collapsing star. This is from Penrose's book. And it collapses to a point, so this is time going in the vertically upward direction, and you can see that for the observer, the curvature continues to increase, and when it comes here, all the matter is now concentrated at this point and remains so forever. Which means that the entire energy density has now vanished. Now, if you believe in Einstein's equation, then that also means that curvature is infinity. So you have absolutely nonsensical geometry and absolutely nonsensical physics. But more than that, if you have this kind of singular situations, you're bringing an end to physics, because all of physics, you see, so what is happening here is, can you describe what is space-time here? No, you can't. Einstein's general relativity breaks down at the singularity. So this beautiful continuum which Einstein had envisaged is true everywhere except at the singularity. And Einstein was aware of this, which is why he never mentioned it. Because the question is that, is your theory also singular? How am I doing with respect to time? Who is, well, Bindu? 5 minutes? Oh, come on. I started a bit late. There was a computer thing. Yeah, okay. Anyway. So I'd just like to mention Professor A.K. Raychaudhuri, who is the forerunner of the theory of singularities. And so this is Raychaudhuri. This is basically a pictorial depiction of the Raychaudhuri equation, because it tells you that if you have a bunch of geodesics, a bunch of particles moving under gravity, then they can do one of these things. They can come closer or get further apart. They can have shear. They can go around. And there could be also a background curvature developing. Okay? So space-time singularity is ignorance about past for the Big Bang and the future for the black hole. Okay? But there's another further conundrum, which is what Bindu was talking about, and this is my favorite. So there is this Hawking area theorem. See, why area? I wanted to say this because black holes, okay, have this funny property that although things may be falling into a black hole, that we know happens. So you see, when things fall into a black hole, well, if things don't fall into a black hole, then the area remains a constant, the area of the horizon. So this is time, this is the value of the area at every instant of time, and you can see it remains a constant. But stuff falling into a black hole, like here, means that the area has actually increased. So Hawking came up with this theorem. He proved the theorem that the area of the horizon cannot decrease in any physical process. Now, when you apply that to binary black hole coalescences, you find that the area of the remnant must be bigger than some of the areas of the two inspired black holes. On that, let me come to this data. So this is the data, right? And this is the analysis of two black holes which are far away, then rotating around each other, and then slamming into each other and becoming one black hole remnant. But after a while, because there's stuff emitted from there, and these stuff are mostly gravitational waves. Now, the data on these experiments were analyzed in great detail, and the truth of the Hawking area theorem was proved to 97% accuracy. And this is some of the data I've shown. Very meticulous work, and these two groups, EC et al. And Kashto et al., they also fought a lot about their algorithms that they used. Now, black hole thermodynamics has to do with, it's something like ordinary thermodynamics, and we've heard a lot about that from Subroto, about the microcanonical ensemble and the entropy being a function of conserved quantities like the area. And of course, with interactions, if the energy increases, then the entropy also must increase. This is the second law of thermodynamics. Now, we can't use this notion for black holes because, you see, black holes are solutions of Einstein equation without any external matter, because the matter has all gone in to produce geometry. And therefore, there is no such thing as energy for pure gravity. See, the other way to think about it is that if you use local Lorentz violations, then this can be shown directly that you can go to a coordinate system in which you can switch off gravity at that point in that frame. So this is very beautiful that there is no energy of gravity, very different from the Newtonian concept. But there is a conserved quantity. That's the area of the horizon, if the black hole is isolated. And if the black hole is not isolated, then the area must increase, and that's the generalized second law. So if you have a universe with black holes, then that's the law that you expect. The area of the black hole initially, plus the entropy of the black hole initially, the entropy of whatever matter is going in, must be less than this sum, okay? The final entropy of the black hole and this. And for binary black hole coalescences, which is this process, this must be true, just taking over from here. Because there's not much data on the matter surrounding these black holes which have been observed to coalesce, okay? And now I'm just going to discard the entropy of the gravitational waves because we have calculated this, estimated it turned out to be very, very small. Okay, now, can I have 5 minutes? Yeah, okay, good. So this is the Bekenstein-Hawking area law. Okay, this is the law. And you can see that this is a ratio of areas in units where the Boltzmann constant is 1, and there's an h bar in it, okay? So that means that there'll be a modification of gravity because you have to bring in h bar somehow, right? And what I'm going to say is, well, I don't have much time again. What I'm going to say is that you can actually calculate the area of a black hole and show that it has this kind of a structure. So if you have a modification of general relativity due to quantization or due to some other reasons, then this has to do with general relativity. These are the corrections, okay? And the corrections are given by small SPH, function of capital SPH, and Q. Q could be a bunch of charges, right? This is very small. So the magnitude of these corrections is much, much smaller. Now, if you go back and look at the data and then plug that in with the generalized second law, you find that the corrections must obey this restriction. Okay? So minus delta SPH must be negative, which means delta SPH must be positive, right? And I'll skip this because I don't have time. And this is the condition that we call absolute consistency, that the delta SPH minus delta SPH should be negative. And if you only allow corrections which are logarithmic in the Bekenstein-Hawking, so logarithmic corrections is what we are looking at, then you find, so the corrections SPH, yeah, it's right here, looks like this. This is the correction coefficient. This is the log of the Bekenstein-Hawking area formula. And then here we find that this, the sign of this must be negative. That's absolute consistency. Now, I just should mention this. I'm sorry, I'm really taking too much time. I think 2 minutes or 3 minutes, right? Yeah, yeah. I'm arguing with Bindu. So there are two main proposals for quantum gravity, and it's an unfinished theory, so we don't know what the final theory is going to look like. There is something called loop quantum gravity, which is a class of theories, which is, so this loop quantum gravity does not need a classical background. You're not looking at small perturbations of a classical background geometry, like a black hole geometry, but you're looking directly at trying to define what a quantum black hole is. And there's also this other approach which has to do with entanglement, okay? That actually falls within this, yeah. So if you look at the string computations, they are special case of this, applied to much more complicated systems. Now, my effort was, see, these two, the people who do these things are always fighting. And I wanted to bring an end to this fight. It's always good to end a fight, right? As Donald Trump has shown. Okay, so anyway, this is the idea of loop quantum gravity, which is like we are all living on a lattice, but this is a kind of floating lattice, like a fish net. So think of a three-dimensional fish net. That's that picture. And I've given colors to indicate that these are called spin edges, and there are spin nodes or spin vertices here. So that's the idea of loop quantum gravity. It started with Amitabh Sen, whom Bindu knows. And then, of course, Amitabh quit physics, so Abhay Ashtekar. So Indians have done a great lot about this. Took charge and polished it up. The funny thing about this approach is that area is quantized. Just like energy is quantized in quantum mechanics, in loop quantum gravity, area is quantized. And there's therefore a minimum area, like a 0-point area, if you wish, okay? So these are the quantum discrete variables. Again, I don't have time. Quantum black hole looks like this. So you have this spin network impinging on a horizon and passing on the spins here. So it's like a whole degrees of freedom which are sourced by these point sources here. And they are called Chern-Simons theories and so on, and you can calculate the entropy. And okay, I'll just give you the answer because I don't have time. So you get the Bekenstein-Hawking term explicitly, but you get a whole lot of corrections. And the leading correction is with a minus sign, 3/2 log. So the minus sign confirms that if you use this formulation of gravity, then you have an absolute agreement with the data, absolute in our sense. So this is something that I should emphasize. Absolute does not mean the other, if it was positive, it would violate the data, except that it will be useless, because you know that it's small quantity. So if you just say that, oh, I have a small positive correction, it's a trivial statement. You know that it's going to be a small correction, but the sign makes a difference. Now, I will again skip, but come to this last page, this page. So the entanglement entropy, which is, you look at now all matter fluctuations around the black hole, You calculate, do perturbation theory to one loop, then you have to renormalize it. I mean, there are all sorts of infinities coming up, so you have to push them off. This is what you get. So Nj here is the number of species of a spin J fundamental excitation, matter excitation, and Aj is the coefficient of that calculation. So this is the result of the one loop computation. Now what I want to draw your attention to is that this S0, so the question is this also positive or negative? Now, this is my little contribution recently. I just said, let's add the two up. And people are going to get very mad. 1 more minute, and I'm done. And then I said, okay, look, if you take Xeon and one graviton, you're still finished. You don't have consistency. Haven't we seen gravitons? No, we haven't. Will we ever see? I don't know. Nobody has ever seen one yet. Well, I'll skip this and just come, oops. Oh, somehow the last page is missing. But anyway, so let me say that this business of, we need quantum gravity because there are issues with singular geometries, like a black hole or Big Bang. But if you follow them, then you have to deal with things like black hole entropy. But what I was able to do in this last work I presented to you is to have LIGO dictate to us how big these corrections would be and what would be their algebraic signs. Now, just to give you an instance, Bindu knows it very well, there is something called asymptotic freedom in high energy physics. And there's Mano Scholz, who's a particle physicist. See, the point is the strong interactions show weird kind of thing, that if you go to high energies, they become weak. So you can deal with them. You can do perturbation theory, which is what we like to do. And I can tell you that this result that I have is related to that through what is called the trace anomaly. I mean, that's a little bit technical, so I'm going to skip it. Anyway, thank you very much, Madam Chairperson. Thank you very much indeed for your patience.
We have time for one question. Oh, two questions. Okay.
Yes, please.
Good afternoon, sir.
Good afternoon.
My question is, does the light is affected by the geometry of the medium?
No, of course, of course.
So what do you mean by geometry of the medium? Does it mean the optical density distribution?
You see, it could be vacuum. So it's not a material medium, right? The sunlight, light from the sun comes here. All the action is in the sun, but between the sun and the earth, there's very little medium. It's very low density matter, right? So it's coming almost through vacuum, but it's bending nevertheless.
So can I say that geometry of the medium is optical density distribution, which is bending the light?
No,
or
it's
something
not
like that?
medium in that sense. So it's curvature. So if you want, you can talk about curvature as causing some kind of optical density. People have tried to do that. People who work on gravitational lensing, but you know, you wear glasses, right? Would you say that you wear glasses because of optical density of this air affecting your vision? It's not exactly like that. It's more focusing and stuff like that. So it's a bit different. Yeah, I would say that it's not the same.
Yes, but that surface is an example of matter density distribution in this medium.
No, it need not be. That's the thing.
What does that makes the bending?
Yeah, you see the space-time, I mean, general relativity. Yeah. See, general relativity has this.
That is bending because there is a paper medium.
No,
that is a density.
Yeah, see, this is why I don't use that example. You see, because the way you raise the issue, you don't want to see a material medium.
Yeah.
But the beautiful thing about, let's say, a black hole. Let's take a simple black hole. Okay, you see that black hole. Well, simple in the sense of GR, general relativity. Okay, so you're solving an equation without any matter present. Of course, there is no matter. Now, of course, the black hole has to have curvature because if you get in, you can't come out. So that has to be a curvature geometrical effect. what is that geometry? It is not the geometry dictated by the Einstein equation per se. It's a new kind of curvature. Okay? So this is the whole thing about GR as compared to Newtonian gravity, that it generates itself. Curvature generates itself, even in the absence of matter. Okay? There could be no matter, and yet you have fantastic curvature.
Is that curvature generated because of the uneven gravitational waves were spread out in the
No.
universe?
Gravitational waves are fluctuations which travel in that geometry. Okay, so gravitational waves, when they travel towards a black hole or away from a black hole, they're traveling in the geometry of a black hole. They somehow manage to escape, but they're being held down. I mean, it's not an easy thing for them to do, right? Because they are being pulled back somehow. All right? There was another question.
Sir, one question.
So, no, I will answer all the questions, but let the formal part finish.
Sir, my question is a bit of a thought experiment. Thought experiment.
Okay.
So, sir, if we imagine a black hole that is at the scale of Planck length.
This is my sign for what we in Bengali call Bhojo Gaurango. That means that I don't know the answer.
Sir, but
my black holes are all astrophysical black holes.
But
Planck scale black holes are impossible to analyze. They're very difficult. So I can't answer anything about that. But it's a good question. And you know, when I die, you'll be around, so you'll have to explore that.
Sir, but still,
it's your
job. Thing about it that if at that black hole we try to measure it by a light, then would be able to measure its position and its velocity at once, because the black hole has gravity, so it will suck the light.
Certainly not. All the laws of quantum mechanics which you're learning in college will be valid. So there is in fact, to answer your question, some people who work on generalization of uncertainty in a curved space-time have the usual Heisenberg terms, but also some additional terms which come from the curvature.
I'm sorry, I've been asked that
the formal part
a lot of
should
people are hungry because it's 1:40. So
well, you wouldn't guess that with the hands going up, but anyway.
I've been told to stop, so
yeah.
I take, now.
I request everyone to please wait for a few minutes. There will be some important announcements shortly. May I please request the chair to kindly present a memento to Professor Padsarthi Majumdar.
Thank you. Thank you so much. Wonderful.
Before we...
Okay. Got it? Oh, great. Thank you.
Before we conclude session 2, we would like to express our sincere gratitude to the chair of this session, Professor Bindu Bamba, for graciously chairing the session. May I request Dr. Abhiram Suri to kindly present a memento to her as a token of her appreciation. Okay, this concludes session 2, but we'll now have a lunch break. After that, we'll have a poster session outside the auditorium. And after that poster session, we'll assemble here again at 3:30 p.m. And please don't forget to carry your ID card, because that carries your lunch coupon. Yeah, thank you so much. 2026. This session will be chaired by Professor Rukmani Mahanta. So may I request the chair to kindly take in charge of the session. But I'll begin with the first invited talk of session 3, which will be delivered online. It is my pleasure to introduce Professor V. Balakrishnan, Professor Emeritus at IIT Madras. Professor V. Balakrishnan is a distinguished theoretical physicist. He obtained the PhD degree from Brandeis University, US. As a faculty and researcher, he served at TFR Mumbai, IGCAR Kalapakkam, and IIT Madras, respectively, from 1970 to 2013. He is currently a professor emeritus in Department of Physics and Center for Quantum Information, Communication and Computing, IIT Madras. He works on various areas of physics, in particular stochastic processes, nonlinear dynamics and chaos, fractional Brownian motion, anomalous diffusion, and open quantum systems. And he has published over 200 peer-reviewed research papers. And today he'll deliver a talk on distances between probability distributions in quantum mechanics and quantum optics. So may I now invite Professor V. Balakrishnan to kindly begin his talk.
Thank you very much for the introduction. Am I audible?
Yes, sir. Yes.
Is the volume enough?
Yes, sir. You are clearly audible.
Okay. Let me start by... Yes, please. There's an echo. Okay. Yeah, let me begin thanking the organizers for giving me this kind invitation to speak at this meeting. I want to first of all apologize for not being there in person. For personal reasons, I'm unable to travel there at this time. So I'm sorry about that, and I hope it works out, long distance talk works out. My topic today is on distances between probability distributions in quantum mechanics and quantum optics, a sort of unfamiliar and rather uncommonly visited part of quantum mechanics. But it's fairly elementary, and the idea is very simple. But it's very important to understand why we need this particular technique, particular topic to be pursued further, and I'll try to make a case for it. This talk is basically based on the paper shown, which has been published in the Journal of the Indian Institute of Science, the special issue on the 100th year of quantum mechanics. As we know, probability and statistics pervade all of science, including much of modern physics. Quantum mechanics in particular is inherently statistical in nature in several respects. In general, we know that the state of a quantum mechanical system or subsystem is specified at any instant of time from a density operator rho, which is also called the statistical matrix in the early days of quantum mechanics. This applies to both pure states and mixed states, to closed systems as well as open systems. In principle, one can, if you have the knowledge of the density operator or density matrix rho, one can calculate in principle the expectation values, higher moments, and correlators of all the observables pertaining to the system. Above all, in particular, we can deduce the probability distributions of individual observables. Although the procedure is somewhat lengthy and intricate, it's a straightforward procedure. The question then arises, the following question arises: can the difference, in some sense, difference between two different probability distributions of a given observable, corresponding respectively to two different states of the system, be specified quantitatively? This is not only a basic question in probability theory itself, apart from quantum mechanics, but also one that has numerous important practical applications which are not necessarily restricted to quantum mechanics. For instance, pattern recognition, image reconstruction, tomogram interpretation, and other such information theoretical tasks require the quantitative estimation of how close two distributions are or how far apart they are for a given random variable. There are many quantifiers of the divergence of a pair of probability distributions from each other, or of the distance between them in the space of distributions. Our interest here is very restricted. It's in the possibility of using some of these quantifiers to distinguish between different states of light arising in quantum optics. Specifically, we focus on the famous Kullback-Leibler divergence dRL, the Bhattacharya distance d Bhattacharya, and in particular on the Wasserstein distance W1. So most of the talk will be focused on W1, which is the one that's been studied the least in this context. I'll begin with the definitions of these quantifiers, followed by their application to some case studies in basic quantum mechanics, basically one-dimensional quantum mechanics, to bring out the dependence of the quantum numbers, dependence of the quantifiers on the quantum numbers labeling the states concerned. Finally, we will discuss application to various states of light, both pure and mixed. For definiteness, let's consider a random variable x that takes values on the real axis. The extension of what follows to the case of a semi-infinite interval, semi-finite interval, finite interval or a semi-infinite interval is quite straightforward, as also to the case of an integer valued random variable, such as, for instance, the photon number of the radiation field. We will come to the photon number distribution in a little while. So let's suppose that f of x and g of x are two different normalized probability distributions of x with corresponding cumulative distribution functions CDFs given by the integral shown. Integral from minus infinity to x dy f of y, which is the probability that the random variable capital X has a value less than or equal to small x. And similarly for the other distribution g of x. F of x and g of x are non-decreasing functions of x, with f minus infinity equal to g minus infinity equal to 0 and f infinity equal to g infinity equal to 1. The Kullback-Leibler divergence between the two PDFs f and g is defined as follows, as shown in the integral. It's an integral over all x of dx times the density times the PDF f of x times log of f of x over g of x. Here f is supposed to be is called the reference distribution of PDF, and g is the one which you're comparing with f. The Bhattacharya distance between f and g is given by d Bhattacharya, less intricate an expression than the Kullback-Leibler divergence. It also involves a logarithm. So minus log the integral over x, f of x, g of x, square root of. dKL is also called the relative entropy of mutual information, and d Bhattacharya are both rooted in information theory. d Bhattacharya is actually a measure of the overlap between the two distributions. D Bhattacharya is symmetric in the interchange of the two distributions, while dKL is not. But neither d Bhattacharya nor dKL is a proper distance function in the sense that it doesn't satisfy all the axioms of a distance function. For instance, the triangle inequality is not satisfied by these two indicators. Another different kind of measure, which is what we are going to focus on mostly, is the so-called Wasserstein distance or earth movers distance stemming from optimal transport theory, defined as follows. In statistics, there's a basic concept called the quantile. The Q quantile, where Q is a number between 0 and 1 of a cumulative distribution function, capital F of x, is that value of x at which f of x equal to q. In other words, x equal to f inverse of q. The formal solution of this equation is just the inverse function f inverse of q, which is about the inverse CDF or the quantile function. The so-called P-Wasserstein distance WP for f comma g is defined in terms of the quantile functions of the two probability distributions f and g, as shown in this integral. It's an integral between 0 to 1 of dq, the quantile function, modulus of f inverse of q minus g inverse of q, the power p, the whole integral raised to the power p, 1 over p, where little p is greater than or equal to 1. It's obvious that wp of f comma g is equal to wp of g comma f. So it's a symmetric like the Kullback, unlike the Kullback-Leibler. Now this distance, the so-called Wasserstein distance, is a genuine distance measure in the space of probability distributions. For three CDFs f, g, and h, we have wp of f comma f equal to 0, wh of f comma g is greater than or equal to 0, and the triangle inequality is satisfied. As it stands, the definition of the PWD for p greater than 1 does not provide in general an analytically tractable expression for its computation. Numerical computation is necessarily the way you get hold of this quantity. For p equal to 1, however, the case most commonly used in practice, the definition simplifies to a very convenient formula in terms of the CDFs themselves as follows. And this is what we're going to focus on. By definition, W1 is equal to integral 0 to q 1 dq to f inverse of q minus g inverse of q, the difference modulus. With q as the axis are the vertical coordinate and x as the ordinate, with q as the axis are the horizontal coordinate and x as the ordinate, the vertical coordinate, W1 of f comma g is just the magnitude of the area between the curves x equal to f inverse q and x equal to g inverse q in the qx plane. That's obvious by looking at the integral. Now suppose we interchange the coordinate axis by a reflection followed by a rotation. So you flip the page over and turn by 90 degrees so that x becomes the abscissa and q the ordinate. So x becomes the horizontal coordinate and q the vertical coordinate. The area between the curves does not change in this transformation. So that W1 of f comma g is now the magnitude of the area between the curves, the inverse curves, q equal to f of x and q equal to g of x in the x comma q plane, i.e. W1 of f comma g is an integral over x, all x from minus infinity to infinity, modulus of fx minus g of x. Notice the modulus here, it's very crucial. But it's also an expression that's explicit in the cumulative distribution functions themselves, and therefore we can make progress. While dk and db are dimensionless, W1 is the physical dimensions of the random variable concerned. That's something to bear in mind to check our calculations. Since f of x and g of x lie in the unit interval for all x, it's obvious that W1 is very loosely bounded by the length of the interval on which x takes values. So a geometrical picture of what's going on is this. The blue shaded area here is the original distribution, little f of x, the PDF, and g of x is the one to which you want to shift, compare f of x with. In physical terms, W1 f comma g is the optimal cost of reshaping the pile of earth f of x into the pile g of x. Equivalently, it's the optimal cost of completely removing the pile f of x to fit the pit minus g of x exactly. Hence the name earth mover's distance for this particular indicator. The cost of moving is the mass moved times the distance moved. And we want to optimize this. This is a problem in optimization. In its general framework, there is no solution to it known for this most general case of multivariate distributions, as well as the p greater than 1 case. We are going to look at the single univariate distribution with p equal to 1. Some care is needed in using this formula for this indicator, for the WD, because both integrals, when they run up to infinity, if f of x and g of x go up to infinity in general, both the integrals integral up to infinity dx f of x and g of x diverge. So you have to take the difference and then take the integral, not the other way about. So one has to be careful in doing these integrations. The problem is, of course, easily fixed by using, instead of the series f and x, g, the survivor functions sf and sg, where sf is 1 minus f and sg is 1 minus g. Then the Wasserstein distance becomes the difference, modulus of the difference between the survivor functions. It's just a technicality, but it's worth bearing in mind. For example, suppose you have two normalized exponential distributions on R, with PDFs f of x is a to the minus ax and g of x is p to the minus bx, where x is an element of 0 to infinity. Sorry, not the full interval, but half, not the full real line, but half a real line. And a and b are positive constants. The Wasserstein distance between these two distributions is trivially calculated, and it's equal to modulus of 1 over a minus 1 over b. Similarly, a short calculation shows that the WD between two normalized Gaussians centered about the same point, but with different variances, sigma 1 squared and sigma 2 squared, is some constant multiplied by the modulus of the difference between the standard deviations. So it's always helpful to bear in mind the geometrical picture of moving one pile of earth into another pit. But here a disclaimer is in order. In recent years, a lot of work has been done on developing a mathematically rigorous formulation extending the notion of the Wasserstein distance to define quantum analogs of the WD for the states of general multipartite quantum mechanical systems. This particular aspect Wasserstein distance is part of optimal control theory, optimal transport theory, sorry. And a huge amount of work has been done on this by very famous mathematicians, including Caffarelli and other. And the topic is still an open one in the general case. Now let's consider some examples from basic quantum mechanics. If psi ket vector psi is a normalized pure state of a particle moving on the x-axis, the density matrix is just the projection operator, bracket psi dot psi. The PDF of the position of the particle in the position basis is given by xi mod squared, expectation mod squared, which is psi of x whole square. Similarly, if phi is another such thing, you again ask for the how the wave function is a positional PDF. You may ask for the difference between the two PDFs. More specifically, let's have a family of this PDFs corresponding to the energy eigenstates of the particle labeled by the quantum number n. So we have mod phi n of x over mod squared. This is the probability density functions that we are going to consider. N runs from 1 to infinity. This to us as physicists to analyze the independence of the distance between the probability distributions in the ground and excited states, especially its asymptotic behavior as n tends to infinity. We'd like to see how far the asymptotic state differs from the ground state, for instance. So we start with the most trivial example of all, the particle in a box, which is not all that trivial actually, but it's a useful and analytically tractable example. When the energy eigenvalues are known to be proportional to n squared, the PDF is a sine squared function, the cumulative distribution function is a linear term and a sine function. Computing Gn with the classical PDF, comparing the Gn with the classical PDF f classical equal to 1, uniform distribution, we get the Bhattacharya distance to be log some constant, pi over square root of 8. The Kullback-Leibler divergence is log 2. Decay in the other order is 1 minus log 2. There's absolutely no independence of dB and dk in this instance. The reason for it is that the classical distribution corresponds to n tends to infinity, and differences in finite values of n are not reflected in these quantities. So that's the reason why these things, when you compare with the classical, you get exactly the same answer, no independence. And that's not going to be true in general, but we'll see. Corresponding Wasserstein distance, however, is given by f classical Gn is given by 1 over n pi squared, which decreases monotonically from 1 over pi squared to 0 and then increases from 1 to infinity as shown in this picture here. It's interesting to note that the PDF for the nth state, which is the CDF is 2 sine squared, the PDF is 2 sine squared n pi x, has a finer and finer comb-like form as n increases, with values 2 at each of its maxima. But the gap between the maxima decreases also, so that it looks like a fine comb. And notice that when n tends to infinity, this Wasserstein distance actually goes to 0, even though the PDFs do not coincide. The f classical, little f classical is a constant, it's 1, whereas Gn is a very highly oscillatory function. But still the Wasserstein distance vanishes because the work done is actually tending to 0 as n tends to infinity. So here's what the CDF looks like for n equal to 1 and n equal to 5. You can see that n equal to 1 is simply a uniformly monotonically increasing curve, whereas the n equal to 5 has steps in it. This is going to be typically the case. The Wasserstein distance between the two corresponding states is the shaded area in between the two lobes here. And as n increases, this is going to get finer and finer, as you can see. Next, let's consider the Wasserstein distance between the ground state distribution G1 of x and Gn of x where n greater than 1. Interestingly, there's a very strong dependence of W1 on the parity of the states concerned. For odd parity states corresponding to n equal to 2, 4, 6, etc., the Wasserstein distance between the ground state and these states remains at or close to the constant value 1 over pi squared for every n. For even states, even parity states 1, 3, 5, etc., W1 increases from 0 as it should and approaches the limiting value 1 over pi squared from below as n increases. As you can see in this figure, the hollow circles correspond to the odd parity states. They are different parity states, whereas the even ones are given by the black curve. Heuristically, you can ask why does this difference arise? It arises because the even parity PDFs, G1, G3, etc., have a prominent central peak at n equal to x equal to half in the middle of the box, while the odd parity states G2, G4, etc., have a central minimum. This implies a dominant contribution to the WD between G1 and G2n. More intricate patterns occur in W1, Gm, Gn for general m. As n tends to infinity, W1 of Gm, Gn tends to 1 over n pi squared. In the case n equal to 1 corresponds to the figure shown, 1 over pi squared. Now let's go a little further and look at orbital angular momentum eigenfunctions of a particle moving in three-dimensional space. The spherical harmonics are the eigenfunctions while m of theta phi, where the angular momentum quantum number n can have the value 0, 1, 2, etc. For every given value of n, the magnetic quantum number m runs over the integers minus n to plus n. When m equal to 0, the magnetic quantum number equal to 0, yn m reduces to the Legendre n of x, where x is cos theta, takes values n minus 1 to 1. From the orthonormality relation for the Legendre polynomials, we know that the probability density is given by n plus half times mod Pn of x whole square. And this is what it looks like for small values of n. Most of the probability mass in Fn of x for n greater than 1 is concentrated near the endpoints of the interval. This comes as a big surprise because normally one draws these pictures of Legendre polynomials, it looks like it's something uniformly oscillating with not much surface. Let's explain why the Wasserstein distance W1 remains essentially the same for all n, all finite n, after fluctuating for the first few values of n. As we can see from this picture here, there are fluctuations in the beginning and after that it's more or less a constant value. Let's look at another problem, which is relative radial PDFs for the L equal to 0 states of the hydrogen atom. Let's consider the PDFs with the radial coordinate r and the spherically symmetric S states of the hydrogen atom. Setting the orbital angular momentum quantum numbers L and m equal to 0, the radial PDF is given by an exponential e to the minus 2r over n multiplied by r squared, the phase space factor, times Ln minus 1 associated Legendre polynomial L1 n minus 1 of 2 pi 2r over n peak for each n. And this is what the peak for each n. And this is what the Wasserstein distance between the ground state and the end state looks like for the hydrogen atom, for the S states of the hydrogen atom. This graph fits very well with the quadratic function of n. The asymptotic n squared behavior should be explained. We can do so on physical grounds as follows. The position of the dominant peak in Fn of r increases with n like n squared because that's how the classical turning point behaves. Remember, we are in the same point behaves. Remember, we are in the semi-classical region. So if I write an energy balance equation, I have p squared. Whereas the positional PDF in the ground state is strongly peaked at the Bohr radius r equal to 1. The Wasserstein distance therefore goes like n squared. This is exactly what we found inside by numerical computation. We can generalize what we've done so far a little bit more. The leading asymptotic behavior of the WD between the probability distributions in the ground and excited states can be read off for a class of generalized oscillators as follows. So the oscillators I'm looking at are the Hamiltonian is p squared plus mod x to the power 2 lambda, where lambda is a positive constant. When lambda equal to 1, you have the oscillator, harmonic oscillator. When lambda equal to half, you have the linear potential, and so on and so forth. Classically, the motion is periodic for every initial condition. The phase trajectories are simply closed curves around the origin in the xp plane, some kind of ovals. Quantum mechanically, the oscillator has a discrete infinite energy spectrum E0, E1, etc. with E0 greater than 0. Although En and the corresponding eigenfunction cannot be expressed in closed form for a general value of lambda, the leading large n behavior of W1 is easily deduced classically, semi-classically at least. Semi-classical quantization, the Bohr quantization rule gives us the result that En is proportional to n to the power 2 lambda divided by lambda plus 1 in the exponent for large n. The level spacing is the derivative of En with respect to n, and it's given shown in the next line. The spacing decreases with increasing n for lambda less than 1 and increases for lambda greater than 1. And it's equal space for n lambda equal to 1, which is right in the middle of this class of potentials. On the other hand, the classical turning points in the potential are at x equal to plus or minus an, where an is the amplitude of oscillation, and is given by an to the power 2 lambda proportional to En, which implies that an itself behaves like 1 over lambda plus n to the power 1 over lambda plus 1. The probability mass in the ground state lies mostly under the central peak at x equal to 0, while in the PDF f sub n of x, it's predominantly under the peaks at plus or minus the amplitude an. Hence, we expect the leading asymptotic behavior of the WD to be given by n to the power 1 over lambda plus 1, namely the amplitude's behavior, for the class of potentials parameterized by lambda. For lambda equal to half, the piecewise linear potential mod x, W1 goes like n to the 2/3, so lambda equal to 1, it goes like n to the power half, as we've seen already. As lambda tends to infinity, the central peak tends towards that of a particle in the box, which we know corresponds to n goes to n squared, and the spectrum goes like n squared. Correspondingly, W1 of f0 Fn is constant, as we've already seen. So all this ties in with the good semi-classical analysis. In all these cases, the PDF mod some wave function squared, that phi n of x is an orthonormal set of wave functions. In a comparison between PDFs and FN and FM, the most obvious way of doing comparison with easily computed quantity would be to consider the overlap or fidelity in quantum mechanics, defined as mod phi n of star of x, phi m of x, dx whole square. But in the present case, this doesn't help at all because these are orthogonal, mutually orthogonal polynomials or functions polynomials multiplied by weight factors like exponentials. So since this orthogonality property makes sure that the fidelity is actually 0 between every n and a different n. So it's not of use at all in this instance. The WD, on the other hand, provides a handle on a distinction between the two distributions. Let's now look at photon number distributions. The quantifiers expressed considered so far can be extended to discrete probability distributions. So let's little p of n running from 0 to 0, 1, 2, 3, etc. be a normalized single mode photon number distribution. That is, the density matrix of the radiation field in this case is the summation from 0 to infinity of little p of n times the projected n, the photon number or Fock basis. The Wasserstein distance between Pn and the distribution delta n, 0 corresponding to the vacuum state 0 is by inspection cost of moving every Pn by distance n to that state in the summation n Pn equal to the average value. Similarly, W1 between the Fock state j and k is just mod j minus k. These are trivial statements. A very useful result for the calculation of W1 for the photon number distributions is as follows. Consider two normalized photon number distributions, little p of n and little q of n with CDFs Pn equal to summation k equal to 0 to n of k and q of n equal to summation k equal to 0 to m q of k. By definition, the Wasserstein distance is equal to the modulus of this difference between the CDFs, capital P of n minus capital Q of n, sum from n equal to 0 to infinity. Then, in those cases in which this integrand, the summand has the same sign for all n, in other words, Pn is always either greater than or less than capital Q of n, the following simplification occurs. Suppose Pn is greater than n for definiteness, so that W1 has the same form without the modulus present. The double summation over n and k is involved in this problem because P of n and Q of n both each involve a summation over k from 0 to n and then n from 0 to infinity has to be carried out. Before integrating, changing the order of summation, we must worry about the convergence of the sum, which is a facet I had already mentioned earlier when we talked about continuous distributions. So we again work in terms of the summation k is n plus 1 to infinity, little q of k minus little p of k. The order of summation can now be interchanged to give this result that I've written on the next line. The summation over k is trivially done, and the result is, the final result is, the Wasserstein distance is just the difference between the mean values in the q distribution and the p distribution. This is an extremely useful result because it helps us read off the Wasserstein distance immediately once we know the mean value of the number distribution concerned. Sure. In general, therefore, provided this P of n minus Q of n doesn't change sign, we again have a formula in terms of the modulus of the difference between the mean values. And the same thing can be extended to continuous distributions back again. So as an illustration of this, I consider this family of distributions tailing off like a power law, and it ends up with a mean value, which is 1 over m minus 2, which diverges at n equal to 2, showing that if you have a Wasserstein distance between a distribution with a mean value that's finite and another with a mean value which is infinite at some point, the Wasserstein distance is naturally going to become infinite. So this divergence of or singularity in the behavior of the Wasserstein distance is very significant here. It's characterized by the simple property of divergence showing up as a pole or something like that. Well, common examples in physics, elementary physics, including black body radiation, for instance, the intensity distribution can be regarded actually as a photon number distribution, if you like, and a continuous distribution in the frequency ends up with the Wasserstein distance between two intensities, which is proportional to the difference in temperature, which we could have read off on dimensional arguments here. In wavelength, it would be the inverse temperatures. For coherent states between the vacuum state and the coherent state, we end up with a average number mod alpha squared as the Wasserstein distance. Similarly, for two coherent states, it's the modulus of the difference between the number states, mean numbers in the two distributions. The Kullback-Leibler is a little more intricate, etc. Thermal distributions also the result is easily read out by terms of the mean value. And then the displaced thermal state, the Grauer-Lach state, etc. And then we can go on to calculate generalized coherent states, photon-added coherent states, squeezed coherent states, displaced states, squeezed thermal states, and so on. Now we come to the photon number in the X distribution in the X quadrature, and this is the harmonic oscillator problem, which I'll skip through here. This is what it looks like. The ground state, then the probability distributions or density functions are all Hermite polynomial times the Gaussian. And the important point to notice is that for n not equal to 0, there are secondary peaks, and there's actually a minimum at the center. So you can see here for n equal to 0 and n equal to 50. So not surprisingly, the dominant part is how much are we going to do, how much work is going to be done in moving the central peak to the edge peaks. Yeah. That depends on what the distance between them is, which is a function of n, and that's what is going to be the Wasserstein distance. It goes like square root of n, which we can also justify by semi-classical arguments. Corresponding Kullback-Leibler reduces to this graph here, which looks qualitatively like the previous graph, but it is not for a reason which I'll explain in a minute. Similarly, the Bhattacharya distance also looks qualitatively similar, but it is not. And what happens is that the asymptotic behavior of both dk and dp is actually a linear function of log n in contrast to square root of n. This makes them less sensitive quantifiers than the Wasserstein distance in confining states. When using SUSY quantum mechanics, supersymmetric quantum mechanics, we can form a whole family of nonlinear oscillators which are isospectral to the original oscillator. We can again compute the Wasserstein distance between these states and between the original vacuum state or the original linear harmonic oscillator states. I'll conclude with these two remarks. The Wasserstein distance, the Kullback-Leibler divergence, and the Bhattacharya distance are some of the quantifiers of the degree of closeness of different probability distributions of an observable pertaining to a given system. In particular, these quantifiers provide useful information for the comparison of the respective photon number distributions in appropriate pairs of quantum states of radiation. The WD supplements, augments, and in certain respects outperforms more traditional distance quantifiers in the space of probability distributions. It certainly merits more attention than has hitherto been paid to it, not only in tomogram interpretation and image reconstruction, but also in quantum mechanics itself. This is all I have to say here today. Thank you very much for your attention.
Thank you so much, Professor, for the informative talk. I now request the chair to kindly conduct the discussion and Q&A. But for that, if you have any questions, you are supposed to come there and ask the particular questions. You have to be here, yeah.
You need to come here and go there.
Okay, great. I don't know. I predict the future is a very hazardous occupation. Predicting the future is a very hazardous occupation. It's very, very unreliable. Then it's impossible to predict what's going to happen. Certainly, there are aspects of quantum mechanics which we have not looked at carefully enough over the last 100 years, and there are lots of aspects which we still have to understand, particularly the measurement problem, the problem of the wave function collapse, and so on. But the fact remains that a great deal of progress has been made, and it's very difficult to tell in what direction it's going to go in the future. Welcome.
Okay, so regarding memento collection, Professor S. Lakshmi Bala as a collaborator of Professor V. Balakrishnan, has agreed to collect his memento on his behalf. Ma'am, I invite you to please collect it.
Thank you. Thank you. Thank you. I apologize once again for not being able to come there in person. I hope. Okay.
All right, so we now move to the next invited talk of session 3. Our next speaker is Professor Manas Maiti from Visva-Bharati Shanti Niketan. It's my pleasure to introduce him. Professor Manas Maiti is a distinguished particle physicist. He obtained a PhD degree from TFR Mumbai in 1997. As a researcher, he served at Boston University and HRI. He has also worked as a visiting scientist at Saha Institute of Nuclear Physics. He works on various areas of physics, in particular experimental studies of standard model, QCD, supersymmetry, and collider experiments. And today he'll be delivering a talk on elementary particles and quantum adventure. May I now invite Professor Manas Maiti to kindly deliver his talk.
Okay, so thank you very much, the organizers, for this kind invitation and to be on the same list of speakers, very distinguished speakers, and I hope. Nope. Okay, so I'll be talking about particle physics. Yeah. Okay, so I mean elementary particles or particle physics experiments is one important area where we can test the quantum mechanics in many different aspects. Okay, so this is my plan of talk, but let us not spend time on this. And as you know that experimental particle physicists, they do detection work. They are basically detectives who detect particles produced in different types of interactions. So I think it will be important to remember for this great detective, I mean one of the greatest detectives mentioned, it is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, is the truth. And I think that is a very apt way where, I mean, how science has moved. I mean, there have been many cases where something has come up which apparently was impossible or improbable at that level of understanding prevailing in those days, but we had to accept it and we had to move forward. So we have a very ambitious project. I mean, starting from the universe, which has a dimension of 10 to the 27 meters, to proton, and even below proton at the level of constituents of protons, we try to poke our nose everywhere. I mean, inside the stars where the nuclear fusion, etc., taking place, to the interiors of a proton to the dimension of 10 to the minus 15 meters. And what we share, I mean, the common thing is that we are asking questions. It's not the Q of quantum mechanics, but the more important is the questions we are asking. And more important than the answers, it's the way we are asking the questions and the way we are trying to find the answers and trying to find out if the answer is wrong in view of future experiments are, okay, so that's how we have come to this quantum era, and probably I'll try to put some light, throw some light on this. So we have a lot of questions. What is this universe made of? Dark matter, antimatter, what is the future of universe, how neutrinos change identity, etc., etc., etc. So we are trying to understand all these questions, and what we have, where we have arrived at this moment is, basically we have a very empirical theoretical structure which is called the standard model of particle physics, which we have put together maybe with sellotape, or I don't know. We have this electroweak theory, which is a nice theory. We have QCD. Yeah. So we have QCD. Again, it's a nice theory, quantum field theory, etc. Fine. Sorry? No. I mean, the QCD, it is there. Okay, so then we have this QCD and electroweak theory, as Madam has mentioned. Spontaneous symmetry breaking is an important part of this thing. But we have many loose ends within this theory, and that is more important. I mean, that is what I meant, that it is put together, not really a very wholesome way of doing things. Okay, so there are serious deficiencies, and I am not qualified enough to discuss all those things. I will just try to tell you about what we have experimentally found out and how we have, those experimental results have supported the theory we have at this moment. And as we have mentioned a few times, the speakers have mentioned earlier, gravitation is not part of it, but we compete with, the particle physics interactions, they compete with gravitation as the, within the stars or as the universe evolves. So we will be having, so let us see how we can proceed from there. So this is the particle content. I think many of you, you are in your particle and nuclear and particle physics course, and some of you who have taken the particle physics course are familiar with these numbers. I don't want you to go through all those numbers, but what I want to emphasize is that in the experiments we have achieved a very high level of precision in many areas, and that's where we are challenging the theory, or where we are trying to find out where the theory is not adequate. So there are many very precise measurements, like the mass of muon, mass of electron. Even if you take these relatively new particles, these W and Z, their masses have been measured to a very good accuracy. This recent result from CMS has taken, those who are familiar, there are only a few MeV has been reduced from this uncertainty. But that takes a lot of effort and a huge collaborative effort for that part, in which for which the particle physics experimentalists are now famous or infamous. A collaboration with 3,000, 4,000 people, and even the smallest collaborations are these days number more than 100 people. Okay, so that's, one good thing is that it's a, that so many quote unquote intelligent people can come together and do an experiment. That itself is a marvelous thing. Okay, so one thing we have mentioned in, we know in this standard model that we have leptons, we have quarks, the leptons have their integral charges. Okay, we have defined the electron charge to be unity, fine, no problem. But then we have decided, we have proposed that the quarks have fractional charges. And nobody has seen a quark. We do not see the quark. We can see hadrons which are made up of quarks, and they do not tell me, there is no experiment, there is no easy way to find out that the quarks have the fractional charges. Now, there are many calculations which support this, but what are, is there any direct experimental evidence? Okay, there is one, electron-positron scattering, particularly if we compare, in quantum mechanics, we, given something, say electron-positron scattering, there are many different outcomes, and those outcomes are completely random. You cannot switch on electron-positron collision and ask that, okay, now this time only mu plus mu minus will be produced, or this time B or anti-B will be produced, and things like that. So you do the experiment and you see how many times you are producing a pair of muon and antimuon and how many times you are producing hadrons. Hadrons because we cannot see the quarks. So whether it is a up or anti-up, whether it is down or anti-down or strange or anti-strange, I do not know. I mean, a priori for each event, I cannot tell that this is this type of interaction. So I count how many times hadrons have been produced, and I count how many times muon-antimuon pairs have been produced. Now, if you consider this is, this calculation many of you have done, but let me tell you one thing, this is electromagnetic interaction until the energy is not very large, say, let us say up to 50 or 60 GeV, when the neutral current interaction, weak interaction starts to make its effect felt. So up to 50-60 GeV, you can electron-positron scattering will produce electron and electron-positron pair, muon-antimuon pair, and things like that. So if you consider electron-positron scattering to a quark-antiquark pair, let us say U bar, the difference is only in the final state where the up quark has a plus 2/3 or 2/3 units of charge. And the electromagnetic interaction is proportional to the charge of the particle. So the ratio, we can write this quark-antiquark pair production probability in terms of the muon-antimuon pair production probability. With that, this is the Q square, Q of the charge of the quark, and there is a factor 3. Now you know that quarks come in colors. They have this color quantum number. So up quark or down, up quark with red or green or blue, they are 3 different final states. So I multiply the probability with the factor 3. So this is my quantum electrodynamics calculation. Now, if I count the total number of hadrons with respect to muons, then I have to add up the probability of producing up bar, down bar, etc., whatever is kinematically possible up with that electron-positron scattering energy, the energy of the collision. So we define a ratio, this R, where the electron-positron scattering produces hadrons and the electron-positron scattering produces muon-antimuon pair, and this comes out to be a very neat number, 3 times the sum of the charges square, charge of the quark square. So let us go to the next page. So till we have only up, down, and strange quarks produced with our center of mass energy less than something like 3 GeV. After 3 GeV, the charm quark pair production starts, opens up. So it will be 2/3 square for the up, 1/3 square for the down, anti-down, and for the strange, anti-strange, it will be 1/3 square, and if you add this number, it will be 2. Now, when we cross the charm quark pair production cross section, limit, this energy, then up to from 3 to 10, after 10 we have the bottom anti-bottom pair production opens up. So up to this we have this thing additional. So I will add to this sum another 2/3 square. So that will come to 10/3, and if it is more than 10, then the bottom anti-bottom also joins, and my ratio becomes 11/3. So this is the E plus E minus scattering cross section, E plus E minus going to hadrons. This huge peak is when the Z production, we are at the Z peak, the center of mass energy is equal to the Z mass. So up to this, we can say that the it is purely QED mediated by the photons, and the ratios, if you look at this ratio up to 3, it is roughly following this 2, and after that it is this 10/3, and after 10 it becomes slightly larger, 11/3. So experimentally this number, we have very clean numbers. We are just counting how many times the hadrons are produced, we are counting how many times muons are produced, and that ratio is very clean, not uncluttered by, not cluttered by very complicated theoretical numbers. So From this, we can have two important conclusions. I mean, if you, so here I have put this thing, and from there I have come to this number. So, if, I mean, after the experimental numbers, I can claim two, we can have two important conclusions. One is electromagnetic interaction, the probability or event carbon depends on the squares of the interacting particles charges, and also the values of R compatible with the following ideas. Color quantum number, quarks have this color quantum number proposed in QCD, and also quarks have fractional charges with respect to electron or positron, 2/3 for up-type quarks and 1/3 for the down-type quarks. Again, I have mentioned with respect to electron or positron because it goes as square. So I do not know if the up-type quark is plus 2/3 based on this data, or the down-type quark has minus 1/3. So all I can say is that some quarks have 2/3 charges, some quarks have 1/3 charges with respect to the electron or positron. Another important thing, I mean, this is probably a little bit old, this mixing of neutrinos. But okay, so let us start. I mean, this started in the 70s, actually 60s and 70s. So if we look at sun, it is a very intense source of neutrinos. I mean, that number you can see, I mean, there are many different cycles going inside the sun. I mean, different these nucleosynthesis processes, and from these different cycles, you can have neutrinos of different energies, but most of them are up to say 2 or 3 GeV, and some, from some cases, boron, and this is some other process, it can go up to say 10 or maybe 20, 30 MeV, but really not more than that. So most of the neutrinos are rather low energy neutrinos, and one is charge current, where a W is the mediator and the interacting particle change its charge. So basically the neutrino becomes, I mean, the neutrino of becomes the lepton, and in the process we have this particle X also changed to Y. And the minimum energy required, this is a very simple calculation where we can calculate what is the minimum energy required for this interaction, and this comes out this. And remember, this L could be electron, muon or tau, depending on what we are observing. So what could be the interaction? A neutrino will interact with a neutron and produces a proton. So basically this type of interaction can take place where the neutron is inside maybe a neutron in the chlorine or a gallium, and then we have the argon or the germanium. Now, Ray, Davis and Buckle, this is Bacal, I don't know what is the exact pronunciation. This is a Homestake experiment where they used a very chlorine-rich medium as target, and you can see this is 380 meter cube of this C2Cl4 they have used for this experiment, and this is this famous Homestake experiment. But the basic idea is, I mean, they see the conversion of the chlorine nucleus to argon nucleus, and this argon nucleus is unstable. So they count the number of argon nuclei produced in interaction with the solar neutrinos. Now, to give you some idea, I mean, out of this 380 meter cube of C2Cl4, what you get is barely half an interaction per day. Barely half an interaction per day, and those 1 or 2 argon atoms are flushed out of that tank every 15 or 20 days, because that is the, I mean, that is limited by the half-life of that argon nucleus, and you have to count them. But this is a humongous experiment, and they have come up with this number, this about half an interaction per day, which converts to this unit. This is called solar neutrino unit, roughly 2.5 solar neutrino unit, where the standard solar model tells us that we should get about 8 interactions per, 8 standard solar neutrino unit of neutrinos we should have seen. So this is roughly 1/3 of what we are getting in the experiment. So this is the huge tank, I mean this is the photograph, this is the schematic, this is a huge tank where this C2CO4 is stored, there is pump, etc., etc. And I mean it will be, I invite you to go through this experiment. You can find it on Wikipedia or any book, and it's really astounding how they did this experiment. But anyway, so we are seeing 1/3 of the ghost particles. I mean this ghost term is very popular. So where are the ghosts hiding? Maybe they are not. Maybe we have just overestimated the number of detected neutrinos. I mean, maybe sun is not producing that many neutrinos. Maybe your experiment is not that efficient. Maybe you are missing some of those argon nuclei produced in the experiment. Who knows? I mean, you have done, I mean, you are talking about half an interaction per day, and you claim that you are doing it very correctly. So it could be neutrino flux, it could be the theoretical calculation about the neutrino interaction probability, it could be the experiment's efficiency, and since it is a counting experiment, we cannot say anything more than that. So let us move to the other experiments. As I mentioned, this experiment can be done with gallium, and this is the chlorine-based experiment, this Homestake. Water-based experiments like Kamiokande and later Super Kamiokande, they also saw this deficit. Gallium-based experiments, SAGE and GALEX, later another experiment, they also did this counting. Then there are two later experiments, two results from a later experiment, Sudbury Neutrino Observatory. In one of those results, they saw a big deficit. In one of their results, they did not see that deficit. But let us talk about these three experiments first. These, I mean, they are seeing this deficit where basically they are counting, I mean, they are seeing the charge current interactions that I have mentioned before. So let us talk about neutrinos from a different source. These cosmic ray neutrinos, cosmic ray particles, they are constantly bombarding the surface of Earth, I mean upper atmosphere, producing pi plus, pi minus, k plus, k minus, and if you look at their decay process, they ultimately, these are the final particles you have. So basically you have one muon neutrino, one muon antineutrino, and an electron neutrino, depending on whether it is pi, pi plus. In case of pi minus, it is again one muon antineutrino, one muon neutrino, and one electron antineutrino. So basically, if you, I mean, these interactions are basically charge symmetric. So you have similar number of pi plus, k plus, or pi minus, k minus produced. So if you take the ratio of number of muon neutrinos and electron neutrinos produced in the upper atmosphere of Earth, interactions in the upper atmosphere of Earth, this ratio should be 2. Now, there are experimental efficiencies. I mean, we cannot catch all of them. So some experimental details will go in. So what we calculate is basically the ratio of ratios, what we see in data, number of muon neutrinos and number of electron neutrinos, and what we should see according to the theoretical calculations. So this ratio, again, this ratio is less than 1. I mean, ideally, I mean, if there was no, if the neutrinos were behaving properly, then this ratio R should have been 1. But number of experiments measured this number, and that is much small compared to 1. And with increasing statistical and systematic, I mean, decreasing statistical and uncertainty. So there is no doubt that we are missing some of the neutrinos. Now it could have been, again, it could have been an overall factor. You could still hide under the excuse, you could still give the excuse that probably your calculation is wrong, or probably your experiment is not that efficient as you are claiming. But in the atmospheric neutrinos, let me go back to this one. This water-based experiments, these are Cherenkov experiments, and this D2O heavy water experiment, these are Cherenkov experiments. So, I mean, basically they detect the Cherenkov light produced by energetic charged particles. That tells me from which direction the charged particles are coming, and that tells me the neutrinos, direction of the neutrino which induced that interaction from which the charged particle was produced. So I can backtrack and find out from where the neutrino came. So basically the direction of the neutrino could be found out. Unlike the chlorine or gallium experiments where you could only count the number of interactions, here you have a differential distribution in terms of the incident angle of the neutrinos. And the atmospheric neutrinos are typically much more energetic compared to the solar neutrinos. So the solar neutrinos and atmospheric neutrinos, the same Super Kamiokande experiment, they can detect the solar neutrinos, they can detect the atmospheric neutrinos, but they can separate out, and also depending on the time of the observation, because now you know the time and direction of the incident neutrino, you can figure out whether it is coming from sun, whether it is coming from the atmospheric neutrinos. So here we have a differential distribution. So they observed the electron-like events where the incident was induced by an electron neutrino, and muon type events where the incident was induced by a muon type neutrino. And you see there is a big difference between what was expected in the theory and what is observed in the experiment. And this is differential distribution. You can no more give the excuse that your counting is probably somewhere wrong, maybe in the cross section, maybe in the your experimental efficiency. Again, here the muon-like events, there is a big difference in the angular distribution, basically at which angle the neutrino is entering the experiment. So now a theory is given. I mean, there are many theories. At that time there are several competing theories, and one which ultimately survived is the oscillation theory, which says that the electron type neutrino, muon type neutrino, and tau type neutrino, they are basically admixture of three neutrinos, nu1, nu2, nu3. Basically these are the mass eigenstates and these are the weak interaction eigenstates. So the mass eigenstates and the flavor eigenstates or the weak interaction eigenstates, they are mixed up. And actually it should have been a 3×3 matrix, but let us take a simplified calculation, a 2×2 mixing matrix, which is very simple, and you can do it on the back of your notebook in 10 minutes. You can see the time evolution of the mass eigenstates. I mean, the nu1, nu2, nu3, they have 3 different masses, so their time evolution will be different. So what is initially produced? So let us take this. So the flavor states, let us say alpha and beta, maybe electron muon, maybe muon and tau, etc. And the mass eigenstates, mixing angle, and let us consider the initial state is nu alpha. It could be alpha could be electron, alpha could be muon or anything. So the survival probability that the neutrino was originally of alpha variety and after some time it is still of the alpha variety, that is given by this expression, and the transformation probability that it was initially alpha type and now it is beta type is given by basically 1 by 1 minus p and this. Now you have an expression where a number of things are there. I mean, you see the time has gone into this where the length, I mean the distance covered and the energy of the neutrino has been put together in this format. The length is in meters and the mass in this expression is in electron volt. So delta m square basically m1 square minus m2 square, the absolute value. But anyway, so we have something where the length and energy of the neutrino can be utilized to test my theory. And remember, this minimum energy required for a particular type is this. So if the initial neutrino, I mean for the charge current interaction this is, so electron type we need basically any minimum energy will do. For muon type, the charge current interaction, basically the chlorine type interaction or the argon type interaction, that needed 110 MeV. For tau type initial neutrino, it needed 3.5 GeV. But the poor solar neutrino, now think of the solar neutrinos. The poor solar neutrinos have energy a few MeV. So they cannot take part in a charge current interaction where the energy requirement is 110 MeV or maybe 3.5 GeV. So if some of the solar neutrinos have converted into muon type neutrinos or tau type neutrinos, those poor souls cannot take part in the charge current interaction, but they can take part in other type of interaction. This is called this elastic scattering and neutral current interactions, where they can be counted. And here I have this result from the SNO experiment, where this electron type neutrino is shown to be 1/3 of what is expected. But if you consider all neutrinos, you include the neutral current and elastic scattering experiments, where all types of neutrinos can take place because the energy requirement is not there. I mean, any amount of energy, almost any type of any amount of energy will do. Here you have almost 90% of what you should have seen. So the difference between this charge current and neutral current interaction can be, I mean, this deficit can be explained in terms of this, this neutrino oscillation. Some of them are changing identities, and after they change the identity, they cannot take part in certain type of interaction, and those who have converted, they can take part in elastic scattering or other type of interaction. And that is how the Sudbury Neutrino Observatory, or SNO, sorry, only 5 minutes, maybe 5 more minutes. Okay, so I'll pace through it. So you have a differential distribution. You can see the oscillation because this calculation gives me this term, which I can theoretically calculate and come up with this. And the Super Kamiokande, with their this Cherenkov detector, where they can find out the direction of the neutrinos, they come up with this, and this is matching with the oscillation theory. I mean, you can see the oscillation theory in the in these graphs and the experimental data. They are matching very well. Now you can say, okay, so the some of the things are some of the neutrinos are changing identity. Do you have any other proof? Yes, we have. Apart from this this oscillation part, this T2K experiment, where the neutrino beam from some 300 kilometer distance was sent to this Super Kamiokande detector, and they observed that muon neutrinos are changing to electron neutrinos. So they observed 115 electron neutrino type events, where the expected background should be only 41. Or more recently, the Opera experiment at the Grand Secho, from CERN the neutrino beam is sent to this Grand Secho, where this Opera experiment is there. They observed 5 events. Okay, 5 is not a very large number, but then I mean tau, the muon neutrino is converted, I mean transformed into tau neutrino. The number is 5, but the expected background is only 0.25. Some other experiments are also doing this at Fermi-Lab. But let us quickly cover some more ground. So this is the more recent, okay, so no more event has been more, attracted more media attention than this Higgs discovery. Okay, for many reasons. One good reason is that some 8,000 scientists were involved, so per scientist media attention was probably not that much. But anyway, so this is how Higgs boson can be produced in the Large Hadron Collider, gluon fusion, quark antiquark quark pair annihilation, or anything like that. And so there are many different ways the Higgs may be produced at the Large Hadron Collider, and the Higgs can decay into different decay modes. Actually, the story is, I mean, this is only the surface, because the W can decay in a number of ways, Z can decay in a number of ways. So Higgs going to W plus minus is actually many different final states. Then Higgs going to gamma gamma, Higgs going to gamma ZZ, etc. So there are many different, I mean, Higgs going to quark antiquark pair and lepton anti-lepton pair, etc., etc., etc. So it's a huge task at a hadron collider, because you cannot produce only Higgs boson at a given point of time. All sorts of events are taking place, and Higgs events are only a very small fraction, several orders of magnitude smaller than the other interactions that is taking place. So it's a huge task, and you will be, I mean, you have among your teachers who are participating in this experiment, I mean, we are collaborators. So finally, at this moment where we stand is after, I mean, there is still a huge data set which has not been analyzed, but from what we have from the run 2, this is how the Higgs decaying to 2 photon looks like. This is Higgs decaying to 2 Z, one virtual and one real Z produced. So this is the peak, invariant mass peak. You know the invariant mass peak from your this relativistic kinematics. Now, at the time of discovery in 2012, this was the peak. You can see this huge background. On this, there is a small, almost a very small blister, Bangla Ghamachi boli amra. So there is a very small this thing here, and when you subtract the background very carefully, you get a very small peak. The numbers are not very large. Probably you can see it here. No, it's not very clear here also. But anyway, you can see the numbers are very small. Similarly, Higgs going to ZZ. Now it has, I mean, with improved statistics. That's why the experiments are, they are very serious about gathering more statistics, because with more statistics you can reduce the uncertainty on the measurements, you can make much better measurements. So this is how we stand at this moment. Now this is how the Higgs looks at its decay. But now, after all, I mean, give me a few minutes. I'm just almost 2-3 slides left. So, so the Higgs is produced. These are the production mechanism. Don't look at all the details. Basically, if it is standard model like, it should be 1, and we see that it is conforming to the value of 1, which is in the standard model within the uncertainties. There is no serious deviation. If you look at the decay modes, again we are looking at the decay modes which are again compatible with a standard model scalar particle, standard model scalar. So what we can say, it is born like a standard model scalar, it decays like a standard model scalar. So this must be standard model Higgs. There are many other Higgs particles produced in different, I mean, mentioned in different theories. I will not go into that. But at this moment, we are happy with something which looks like, which behaves like, born like, and dies like a standard model scalar particle. So I'll quickly cover I have 2 more slides. I will just finish. So the top quark is unique in many ways. It has a very small lifetime, 10 to the minus 25 second, where the hadronization time scale is 10 to the minus 24 second. Spin decorrelation time is 10 to the minus 21 second. This is the only quark that decays like a quark, not as a hadron. Because the other quarks, they immediately form hadrons, and what you see is not really the decay of the quark, it is the decay of the hadron, which is a much more complicated thing. Now, since this hadronization, it is smaller than the hadronization time scale, it decays as a hadron, and it retains its spin information, and that spin information is passed on to the decay particle. So it is, so look at the TT bar pair production at the LHC. If the top decays into, if the top decays through the leptonic channel, basically if we have electrons or muons and neutrinos in the final state, this type of final state, there the visible particle, I mean the, the L plus or L minus, it could be any combination of electron and muon or tau, that retains the spin information with which the TT bar pair was produced. So this is one, I mean, the proton-proton collision is a huge chaos. And out of that chaos, I can still get some meaningful information if we observe the lepton-anti-lepton pair. And that has been done. So the spin correlation, so this is what is observed. I mean, this asymmetry is defined where the azimuthal angular difference between the lepton-anti-lepton pair is greater than pi by 2 or less than pi by 2. This asymmetry is measured. And if there was no spin, if there was no correlation at the time of production, it would have been the dotted line. But this is the observed. Similarly, from the, this is from CMS experiment, this is from Atlas experiment. So at a very, very, I mean, it's still very crude, but still we have some information about the correlation present in the pair. So we come back to that big Q, we have lots of questions, and we are trying to find answers. And as Alice and the Cheshire Cat had this this conversation, we have to move, we have to keep walking, even if we don't know in where we have to go to. At this moment in particle physics, we are really in a very binding situation, difficult situation. We don't know in which direction we have to go, but we have to keep working, we have to keep gathering statistics, do more new measurements, and find out where are the gaps and how to fill up the gaps. Okay, so with that, and again, thank you for your invitation and the kind attention.
Thank you, Professor Maiti, for the nice and interesting talk. We'll just take one question from the convener.
I think I would better, if the students ask the questions. Because, that is, the discussion, this talk is, if the students are there, I would be, that will be. Okay, please.
Thank you for this amazing session. My question is that, sir, as we celebrate 100 years, particle physics produces massive data. Can photonic integration be the solution for fast data handling?
What solution? Integration, you said?
Integration means light chips.
Okay, for the experiments, we have to use very complicated technology, etc. What is this light chips? I didn't understand. Some computing chips where photonics is used, or
Yes, photon is used.
Yeah. So right now, I don't know how widely that is used, but probably we'll move in that direction in the future, because the computation is becoming a very, very crucial part of the experimental particle physics. Starting from the data taking to the final result. So we are always exploiting whatever development in computation is taking place. Now, people are using this GPU, artificial intelligence, machine learning, everything. Whatever tool we get in the computing area, we try to use that. So,
is there a scope in future?
Yes, of course there is scope in future. As the previous speaker said, it's difficult to predict future, but of course, there is possibility. Okay, so maybe, sorry, I took a lot more time, little more, but definitely less than Parthoda.
Okay, thank you so much.
Thank you for this opportunity. Thank you very much.
Okay, so may I request the chair to present a memento to Professor Maiti.
Thank you. Very nice. Could I get that box? Okay, so I quickly take off from here, please.
It should be put here. I don't know how to do it. Okay. Here, no. Put it here. Put it here. This is a good place to put it in.
Okay, so we now move to the final invited talk of session 3. It is my pleasure to introduce Professor S. Lakshmi Bala, professor at IIT Madras. She's a distinguished theoretical physicist, and she is currently working as a professor at Center for Quantum Information, Communication and Computing, IIT Madras. She works on various areas of physics, in particular classical and quantum dynamical systems, nonlinear dynamics and chaos, quantum information theory. And she has published over 75 research papers. She is also known for delivering NPTEL lectures on quantum mechanics. And today she'll be delivering a talk on quantum optics in quantum information. Let's invite her with a round of applause.
Thank you very much. Can you hear me? Through the mic. Okay. Thank you very much for this invitation. I visited this university in the past on many occasions, and every time it felt like coming home. So thank you for this homecoming invitation. Today I wanted to talk about quantum optics and quantum information. I understand that this is a homogeneous audience, undergraduate students, postgraduate students, and PhD students who don't work in quantum optics. So I'm going to keep it at a somewhat elementary level, a little bit more advanced than totally elementary, so that you might be able to take home some lessons when I finish. So there are different approaches to understanding the quantum classical divide. That's a very gray area. And if you want to understand this gray area, my experience has taught me that quantum optics is perhaps one of the finest platforms that you can use. There are some effects in quantum physics, such as squeezing of light. This has no classical analogs. And this is very useful in quantum sensing and metrology, and I might be able to indicate how that happens. Then there are some effects, such as entanglement. Now you can create entanglement between qubits. They could be polarization qubits, because the photon has polarization. And you can create entanglement between atoms and light. You can use electromagnetic waves or photons to create these entanglement effects. And quantum entanglement is, as you know, there is a lot of hype about it, and it is a resource for quantum information and computation. Squeezing is a non-classical effect. What I mean is that this is a consequence of the Heisenberg uncertainty principle. Actually, it is the Schrödinger uncertainty principle, but I find that books concentrate a lot on what we know as the Heisenberg uncertainty principle. The Schrödinger uncertainty principle puts a tighter bound on the whole thing. So, but whatever it is, squeezing is a consequence of the uncertainty principle, and entanglement is big. I want to make the following comment to sort of connect with what Professor Balakrishnan said. He spoke about distances between probability density functions, PDFs. Probability theory is extensively used in classical settings, as you know. And if you look at quantum physics, different states of light are distinguished by distributions, such as the Wigner function and so on, which is quasi-probability, in the sense that there are certain regions where the Wigner function becomes negative. So optics provides us with a plethora of very surprising and interesting and useful elements. In fact, it's a very nice thing that these days in a quantum optics conference, you have theoreticians, you have experimenters, and you have people from Google, IBM, and so on, and you have the devices people as well. So it really brings in different types of practitioners of research in different directions. So what are the tools that we use to measure non-classicality? You start with the experimental data, which you bin into histograms, and this set of histograms form what is called an optical tomogram. An optical tomogram is like a medical image. If you do a scan in any of these medical centers, you will find that they rotate over 360 degrees. They make 34 slices, 160 slices, and so on. And they look at the, suppose you're doing an image of the brain, they look at the intensity distribution in the brain. It is the same thing here, except that you're looking at the PDF. So that is how an optical tomogram is analogous to a medical scan. Now, it is very difficult in most cases to reconstruct this Wigner function or the state of light from the optical tomogram. So it might be wiser, and I think I'm taking the laser all over the place, it might be wiser to read off things directly from the optical tomogram. Now that is something that we attempt to do in IIT Madras where I work. That's one of the aspects of our research. I want to, you know the importance of light. You know, for instance, that there was this International Year of Light in 2015, and that was a UN observance for increasing awareness of the achievement of light science. You know that the Einstein photoelectric effect was about how light behaves like quanta, like particles. And apart from that, I just want to recall this gentleman, Shinichiro Tomonaga, who is a very, he's a very, very important person in quantum field theory and quantum physics in general. In order to use the fact that light has certain properties, it has wave-like nature, he created a drama which was played in Japan in various theaters in his time. So the drama is like this. There is this lady who symbolically represents light and who is a thief and who steals from various places, and the police are out to catch her. So they know that she is a very slippery customer and she will escape very easily. So somebody says she is out there in that house. So the cops go and they say, if we open one window, she will jump out, but she will go so fast. So let us open all windows and one of us will stand at different windows so that whichever window she jumps out from, we will catch her. So they opened all the windows and they all reported she jumped out of all the windows. So that was Tomonaga's play, and apparently it went very well with the public. They might not have understood waves and particles and duality, but they certainly understood this. So how do you introduce quantum optics? You know the harmonic oscillator problem. The Hamiltonian has actually a p squared by 2m plus half m omega squared x squared. Let us forget this m and omega and all that. They are parameters. Let us set their value to 1. Then essentially it is a quadratic form. It is x squared plus p squared, right? But then you see this strikes a bell because you also know that if you look at the electromagnetic density, it is E squared plus B squared. That is another quadratic form. You do have a 1 by 2 mu naught, there is an epsilon naught. Set them all equal to 1, you have a quadratic form. Now theoreticians like to use the same mathematical framework wherever possible and map it onto different problems. And that is what is done in quantum optics. So you know, for instance, if I set h cross and omega to 1, the Hamiltonian for the simple harmonic oscillator is n plus half h cross, is a dagger a plus half h cross omega. You have a single simple harmonic oscillator. There are equally spaced energy levels. And A takes you from a higher level to a lower level, and A dagger takes you from the lower level to the higher level, and the Hamiltonian is A dagger A. And you can use the same thing, exploiting this quadratic form equivalence in quantum optics. And now you will say it is the same Hamiltonian, it's the same algebra, but my interpretation is going to be different. A is going to be the photon destruction operator. A dagger is the photon creation operator. But see what you have done. You have gone from a single simple harmonic oscillator to multi-photon production. Because if you repeat A many times, then you're destroying n photons on the original state. If you apply A dagger many times on the original eigenstate of the oscillator, in this case, you're going to talk of optics, you're going to create many photons. So it's the same maths, but you see, I can really circumvent a lot of complications by just making this analogy, and this takes me very far in life. So A dagger A was really the number operator in the simple harmonic oscillator problem, where the eigenstate of A dagger A, that ket n, is the nth level of the oscillator. Here ket n is the n photon state. So with that analogy, we can define the field quadrature operators. X is A plus A dagger by root 2, and P is A minus A dagger by root 2i. And you know that A is the lowering operator and A dagger is the raising operator. Same mathematics, no changes. Interpretations are different. This ideal laser light is really an infinite superposition of photon number states. So ket alpha, ideal laser light or coherent light, is apart from this normalization, it's an infinite sum over the 0 photon state, 1 photon state, 2 photon state, and so on, with this probability amplitude. Normally, we use this as the reference state and refer to it as classical light. Now, for low values of alpha, if you just plug alpha as 0.0001, for instance, you will find that because of this probability amplitude being very low, it's going to be dominated by the 0 photon state ket 0 and the 1 photon state ket 1. So you see there is a probabilistic method of producing a single photon if you just use low intensity or attenuated laser light. And what do you do with a single photon? A single photon has 2 polarization states. You can think of it as a qubit. And you could do some kind of logic gate operations, quantum logic gate operations in optics using these polarization qubits. There are properties of alpha, which I will not go through right now. But I want to point out that ket alpha satisfies the minimum uncertainty product in the field quadratures. Delta x squared and delta p squared is half. There I have put h cross and all that to 1. But remember that this x is not position and p is not displacement. X and p will be related to the electric and magnetic fields because we have replaced x squared plus p squared by e squared plus b squared. So we call them the field quadratures. Now the average photon number n in a coherent state, as you know that this is the photon number operator now, is mod alpha squared, which is the intensity of light. If you take 2 coherent states, they overlap, so they are not orthogonal to each other. But you see, if alpha is sufficiently large and the other coherent state's parameter delta is minus alpha, this exponential goes to 0. So for alpha sufficiently large, the 2 coherent states can be treated as 2 independent objects forming a qubit, and you could also work with those as qubits. Photon number distribution in the case of laser light is Poissonian. The variance is equal to the mean. With reference to this, what is squeeze light? Squeeze light is if in one of the quadratures the variance is less than half, it is squeezed in that quadrature. Similarly, if in the p quadrature, if the variance is less than half, it is said to be squeezed in p. It can either be squeezed in x or squeezed in p or not squeezed at all. You cannot have a situation where it is squeezed in both x and p because you would have proved Heisenberg wrong, and that is out of the question. So please understand that the squeezing is in one of the canonically conjugate quadratures. This is an example of squeeze light. You have a superposition of the 0 photon state and the 1 photon state. That's an example of squeeze light. So squeeze states are important in quantum metrology and sensing because you see, you have reduced the spread below the standard quantum limit. And therefore, the least count has become very small. Therefore, you can sense better, you can probe better. And therefore, squeeze light is very important in gravity wave detection. The squeeze light was first in Slusher's groundbreaking experiment on atomic sodium vapor. He generated squeeze light. The photon number distribution is sub-Poissonian. I could go to the next slide. There are other examples of non-classical states. For instance, you can take the coherent light, ideal laser light, and keep adding photons to it. These exhibit some squeezing properties for certain values of the number of photons added and the value of alpha. Therefore, again, very important in metrology. These are eigenstates of a nonlinear operator, which is a nonlinear function of A and A dagger. So again, as I said, this is useful in metrology. Apart from this, you have the even cat state and the odd cat state, the Schrödinger cat states. This is a combination of 2 coherent states, one which is ket alpha and the other which is ket minus alpha. And this superposition, this normalization cannot be 1 by root 2 because, as I said, 2 coherent states are not orthogonal to each other, and you have to work out the normalization. These cat states, the even and odd coherent states, are superpositions of 2 coherent states, and these are called cat qubits Because again, for sufficiently large alpha, the overlap is 0, and I can treat this and this as two parts of a qubit, like ket 0 and ket 1, and they are used in quantum information and for quantum error correction codes. So the even coherent state, we can show that it has an even number of photons. It's a superposition of an even number of photons, and the odd coherent state is a superposition of states which have an odd number of photons. So how you do this in error correction codes is, you take a logical qubit and encode it in the cat state. So the logical bit 0 and 1 are encoded in alpha and minus alpha. So if a photon is lost, the even coherent state becomes the odd coherent state, and therefore there is a parity change. So if I just make a parity measurement without probing into the even coherent state and disturbing it too much, then I know that a photon is lost. That is the error. The error comes due to loss of photons or gain of photons. So by looking at the parity changes, I know that there is an error, and I can try to pump in photons to make up for this loss. So in quantum optics, errors are in the form of photon losses and gains. This would be of interest to many people. It comes to many people as a surprise. I usually catch the student community by surprise on this, because we are all taught that if two states, let us call them psi 1 of x and psi 2 of x, are such that modulus of psi 1 of x the whole squared equals modulus of psi 2 of x the whole squared, then you take the Fourier transforms and you're told that modulus of psi tilde of p the whole, psi 1 tilde of p the whole squared equals modulus of psi 2 tilde of p the whole squared. You've measured things in the x and p quadratures. That should be enough. It should tell you everything. In particular, it should tell you that the two states have high fidelity. They should have a fidelity which is close to 1. In other words, it should tell you that these two states, psi 1 and psi 2, are off only by an overall phase. And then, of course, their fidelity, which is the overlap, should be equal to 1. But that is not true, because Pauli raised this question in this handbook, and Reichenbach comes up with an answer by saying that is not true. If you just measure a wave function or a probability density function, the x quadrature and the p quadrature, that's not enough to know about the state, because he gives you counter examples. Take this as one state and that as one state. These are the Fourier transforms. You can check that they are equal. But if you look at the fidelity, that is not unity. So it is not true that if things are equivalent in an x and p quadrature alone, the two states are equivalent. They are not equivalent. They are not off by an overall phase. And here is an example. So you have to measure probability density functions, not just in the x and p quadratures, but in many quadratures. And that is what a homodyne setup does in optics. So to understand the Pauli problem further, what you do is this. You define an object, not x, which is a plus a dagger by root 2, but a dagger e to the I theta plus a e to the minus I theta, keeping the algebra intact. A tomogram corresponding to the state rho is given like this. If it's a pure state, you write rho as psi psi, this ket psi bra psi, and the tomogram is simply psi in that x theta theta basis. This is what I meant by a medical scan, because you fix your theta value, you measure psi corresponding to that theta, you measure modulus of psi the whole square, then you go to another theta value in the laboratory by rotating the homodyne setup. It's actually not a rotation. You have to change the phase of coherent light, which you use as the reference state, and then you measure it. So basically, you get an intensity profile for different theta values. That is like a medical scan. You zero in through all the tomographic slices that you select and try to understand the state and its properties. So that is the whole idea. And a tomogram is obtained from multiple measurements of a set of observables which give complete information about the state. In principle, you need an infinite set of basis states. This is in contrast to spin systems or qubits. These are continuous variable systems, and the electric field strength varies continuously. In practice, you may manage with a finite number of slices. So here is a tomogram. This is the tomogram for the coherent state of light. So that red blob that you see there, I'm just giving you its tomogram. X theta is analogous to position. For different thetas, you have this tomogram, which is basically modulus of psi of x theta comma theta, the whole squared. After state reconstruction, this is the Wigner function. This is the tomogram for the even coherent state or the even cat state, and that is the tomogram for the odd cat state. As I said, reconstruction can in general be a big problem, and so we try to extract properties directly from the tomogram itself, the properties of the state, including squeezing properties, variance, higher moments, and so on. Also entanglement, and so on. In optics, the measurements use beam splitters, a homodyne setup, photodetectors, interferometers, phase shifters, mirrors, lens, etc. Now, what is the beam splitter? A beam splitter can be used to produce entangled states. I think this morning, Professor Subramaniam certainly spoke about the beam splitter, and I just want to point out that the beam splitter has two input ports A and B and two output ports C and D. A lossless beam splitter means it does not absorb the light that goes in. You send light through port A. Maybe you send a coherent light through port A and another coherent light through port B. And then if you look at the output ports, they will be coherent lights, factored products, unentangled products of coherent light. This is an exception rather than the rule, because in general, you send in unentangled or factored products into the beam splitter, they will get entangled. So in optics, it's a very cheap way of producing entangled states. So for instance, if you take a product of the 0 photon in port A and the 1 photon in port B, you will find that it is going to be an entangled state 0C1D plus 1C0D by root 2. So very, very easy, and beam splitters are readily available. So it's easy to produce entanglement. If now I take 1 photon in input port A and 1 photon in input port B, because it's a lossless beam splitter, there should be no absorption of photons. So I will expect by photon number conservation, 1 in port C and 1 in port D, or 2 in port C and 0 in port D, or 0 in port C and 2 in port D. Nothing else is possible. But in truth, you will never have 1 in port C and 1 in port D. Coincidence counts will not be there. And that is called the famous Hongou-Mandel dip. 1 photon in each input port leads to 2 and 0 or 0 and 2. Simultaneous clicks of 1 photon in port C and 1 in port D is not possible. This actually can be traced back to Bose symmetry, but that's the genesis of why it does not happen. Those of you who have worked with Klebsch-Gordon coefficients will know that when you add angular momenta, 1, 1 does not appear in the coupled state when you start with 1 plus 1. So that's the Hongou-Mandel dip. Now the ability to precisely control and verify the indistinguishability and entanglement of photons is fundamental for building and operating quantum computers based on photonic systems. Means you want to know that there is only 1 photon, that really it's a single photon. Then a coincidence count should give you the Hongou-Mandel dip. So a good Hongou-Mandel dip with 0 coincidence counts indicates that the source is producing indistinguishable single photons. I do not know how much time I have. I think I will get back to the slide if I have time. So then I will definitely not get back to that slide. So I told you about the homodyne detection. Now what you do in homodyne detection is, the 2 output ports of the beam splitter have detectors that measure the photocurrents in output port C and D. You see, photons will be translated to photocurrents, right? You have to look at the photocurrents and then make statements. But the photocurrents really correspond to the electric field strengths. So you're back to the quadratures. And that is precisely how a homodyne setup helps you. So from a homodyne setup, what you get is the tomogram. You use a homodyne setup in a continuous variable quantum key distribution system also, people keep talking about Alice and Bob and Eve eavesdropping and so on and so forth. So basically, if you use a homodyne detector, both at Bob's end and at Alice's end, of course, she's sending out light signals, the information is coded in the light signals, in the field quadratures. Bob and Alice have to make measurements in some quadratures and see if the output tallies, if the numbers tally. Then you know that no information is lost. So that is how in CVQKD homodyne detection is used. There is this very nice paper, Tomographic Reconstruction of the Density Operator from its Normally Ordered Moments by Unshaw. And that tells you how to compute things like this from the tomogram. Now, if I computed this, it means I can get all moments. I can do it for any k and any l. Therefore, I can get the skewness, the kurtosis, the variance, you name it. I can get everything straight from the tomogram. And that is enough to characterize the state of light. So I found this paper very useful. You could have many systems where there is entanglement. An example is the double-well Bose-Einstein condensate. But in optics, for instance, you can have a multi-level atom interacting with the radiation field. Then there is an entanglement between the atom and the field. You could do cavity optomechanical systems where there is you could have that system and the radiation pressure can be connected to a membrane in an entangled state, and you can put an atom inside it. You can have a 3-level atom, a lambda atom. It's in the shape of a lambda. No? There is a ground state, 2 ground states if you wish, in an excited state. And then you send laser light or any form of light to do atomic transitions here between these 2 levels and between these 2 levels. This is very important. This kind of atoms are obviously very important for experimenters, and they work with rubidium, for instance. And in these 3 levels, you can do very interesting phenomena like electromagnetically induced transparency, electromagnetically induced darkness, and so on. Then the double James-Cummings model, where you have an atom interacting with light, another atom interacting with light, but these 2 atoms are not talking to each other. But the Hamiltonian, or the interaction of the system, is such that there is entanglement between the atoms. That entanglement can suddenly die. It's called entanglement sudden death. It can suddenly revive. So you see different types of entanglement, and entanglement as a resource for quantum information. You have a plethora of models in optics which are experimentally very viable. So now, single photon production. You can have on-demand production or probabilistic production, as with dull lasers. The brightness you need to worry about to take care of photon losses. The wavelength, you need to choose the right wavelength to match telecom wavelength or any other communication requirement. Entangled pairs can be produced in certain processes. Beam splitter is an example. Photons do not interact directly with each other. The entanglement transfer is through atoms. Entangled photons can be produced through what is called spontaneous parametric down conversion. And you can actually buy these setups. They are available. You can use quantum dots, and there are many ways of doing this. I'm going to skip this except to say that I have here for you a bipartite extension of the optical tomogram, and you can get information about the extent of entanglement straight from the tomogram. See, here the entanglement dips to 0. Here the entanglement is there, here all over, but there are small local dips and so on. And these can be quantified very easily. I want to point out that if you look at a tomogram, when the entanglement suddenly changes, suddenly there is a change in the qualitative appearance of the tomogram. Compare this one's appearance with that and that. Similarly, compare this tomogram's appearance with this and this at a slightly earlier time and at a slightly later time. So a tomogram itself tells you many things. I skipped this slide because it's about quantification of the extent of entanglement. You can use the IBM platform for doing experiments and simulations in the models that I spoke about. You can see this, the sudden death and sudden birth and so on. We have ourselves done it and in model Hamiltonians and found that the experiment results are mimicked very well with our models. And we have also looked at 2 entangled photon states which were seen in an experiment and shown that from the tomogram you can see the difference between the 2 photon pairs. And I have the following take-home points. The simple harmonic model is a good model for quantum optics. States of light and their importance I have tried to explain to you in the context of quantum information. Squeezing is very important for metrology, in particular gravitational waves. Entanglement creation and transfer can be done by light interacting through atomic media. There are many measurement procedures, including homodyne detection and so on. You can have single photon qubits, atomic qubits, and the quadratures in CV systems for quantum information. I've also told you something about the uses of the optical tomogram when state reconstruction becomes a problem. I hope you can take home something. Thank you.
Thank you very much for finishing in time and wonderful talk. So now we have time for 2 questions.
The 0 photon state is the ground state.
Yeah, so like for the quantum harmonic oscillator, we will A of 0 state is equal to 0. Is that
Quite so.
No, for you, no. Any other question?
The last what? This one? Let me just keep going back and then maybe you can this one? This one? You want to understand this? Okay. So this is in dynamics. I have a model. This model, the first one for instance, is a very realistic thing. It is an atom with any number of levels but equally spaced interacting with light. So if I start, the question is, do I start with Fock states for light, which means photon number state, 0 photon, 1 photon, 2 photon, or do I start with coherent light? Doesn't matter. The first figure, the top panel, is about starting with an n photon state, say state. This tomogram corresponds to a 5 photon state. Just a little bit before the entanglement dips to 0, you have a tomogram like this. And just a little bit afterwards, you have a tomogram like this. So I know I can see signatures of entanglement changes. The same thing here, except that it has been done not with the photon number state, but with coherent light. You can see qualitative changes in the tomogram when there is a sudden change in the entanglement. That's the shape.
Ma'am, is there any
where am I now?
Is there any experiment where one can see squeezed states?
Yes.
So where?
A lot of experiments where you can see squeezed light. For instance, even if you take the squeezed vacuum, for instance, I can measure the delta X.
No, in that case, what is the system and where they observe it? Is it just...
You add a photon to the coherent state. That has been done. Zavata and company have already added 1 photon to the coherent state. They have produced the 1 photon added coherent state. Change the value of alpha, mod alpha. For some values of alpha, you will get it squeezed, and you can measure the quadrature variances, and that will show squeezing.
So it doesn't need any atom, etc.
Not necessary,
Only
because it has come out.
Manipulating light.
I can look at the tomogram. I can look at the tomogram and take a look at it. And
means they can also control all this.
They can control alpha.
I see.
Actually, there are experiments where mod alpha is changed. Squeezed light itself, there are experiments to change the extent of squeezing by changing the squeezing parameter. The atom is used only to produce that photon, which will be added to alpha. Coherent light interacts with the atom emits a photon, the photon is absorbed by alpha, it becomes the 1 photon added coherent state. I have the tomogram for the 1 photon added coherent state, I compute squeezing from that. So I can, yes.
All right, thank you so much,
You're
ma'am.
welcome.
So I kindly request the chair to present Professor S. Lakshmi Bala with a memento as a token for
Before I
appreciation.
break this, just remove this off. It's generally get nervous about these things. Just So I go home with 2 mementos and with the promise that I will keep.
All right, so before we conclude session 3, we would like to express our sincere gratitude to the chair of this session, Professor Rukmini Mohanta, for efficiently chairing the session and guiding the discussions. So this concludes session 3 of 100 Years of Quantum Mechanics 2026. We'll now have break for tea, which will be served outside the auditorium. We request all the participants to kindly return by 5:50 p.m. And there is one announcement regarding participants who have yet not collected their participation certificates. Please do contact the registration desk. And the poster presenters are requested to collect their certificates from the same place. Thank you.
Hello, hello. Hello, hello, hello. Hello.
Narayana Rao. May I request the chair to kindly take in charge of the session?
We are going to have a very exciting evening today with two beautiful talks. The first one is by Professor Umakant Rapal. He is a very distinguished experimental professor, and he is working currently at Department of Physics, IISER Pune. He did his PhD from IISc Bangalore. He was previously working as a scientist at GE Global Research Bangalore. Did his postdoc work at École Normale Supérieure Paris and University of Innsbruck, Australia. He works on various areas of physics, particularly in atomic physics, quantum optics, ultra-cold atoms, precision spectroscopy, and quantum technologies. He has published more than 100 peer-reviewed papers. With this brief introduction, I request Professor Umakant to give the talk and make us ultra-cold.
Thank you very much, Professor, for the kind introduction. Yeah, so good evening, everybody, and it's my pleasure to talk in this auditorium. I think this is the first time I'm coming to Central University for giving a talk. I did visit this place many times, but thanks to the organizers for inviting me to give a talk on this occasion of celebrating 100 years of quantum mechanics. So today I will briefly introduce you to some experimental aspects of making a Bose-Einstein condensate and how Bose-Einstein condensate can be used for a variety of experiments, not only for experimental research but also for practical applications. I'll just give you a small flavor about that in the context of what is going on specifically in our lab using a Bose condensate. Okay, so before I begin the technical part, I would like to generally acknowledge everybody and all the funding agencies that are involved in basically for enabling the research that goes on in our group. So as usual, we get, my students get funding from various sources including CSIR, the Institute, and we also have Prime Minister's Research Fellowship. Other than that, the funding is, I mean, for the running the experiments, the funding is supported by our own institute, the two missions of the Department of Science and Technology, the ICPS mission and the current quantum mission. And we have a technology innovation hub at IISER Pune, which is funded by DST through the National Mission on Interdisciplinary Cyber Physical Systems. So all these students have, over the past 15, 16 years, all of them have contributed to the growth of the lab and all the science that goes on in the lab. Currently, I have 4 students, and all of them have finished, and then 2 more have joined very recently. So there are in all 6 students in my group. So what do we do? This is just a broad overview about the different activities that go on in my research group. So basically, we use ultra-cold atoms as well as ions for doing variety of things. When I say ultra-cold atoms, they are atoms either in a thermal state or a quantum degenerate state like a Bose-Einstein condensate. So for instance, the first set of experiments or the research direction that we have in the group is to use Bose-Einstein condensate or just thermal ultra-cold atoms when subjected to certain dynamical perturbations. I will not get into the details right now. And then we also use it for doing physics of revival of wave functions. Like for example, you start with a wave packet, which is basically a Bose condensate. And then when it goes through certain set of perturbations, the wave packet splits into different paths, and then finally it merges with some fidelity. You can do, for example, simulate ratchet motions where under the application of certain set of perturbation, you can make the wave packet walk in one direction or the other. So this is just a brief glimpse of what goes on. I will not get into the details of each of them, just to tell you what all goes on. Now this second and third program is on using ultra-cold strontium atoms for doing two different things. One is to use these atoms, because these atoms have an extremely narrow optical transition. It is a very good candidate for the future optical frequency standard. So because of that, our group is also focusing on efforts to do some physics related to the narrow optical transitions. We are not a place where we can build clocks, because that's basically the job of National Timekeeping Laboratory, like National Physical Laboratory. But we are working on some physics aspects of these clocks. The same atoms using the same narrow optical transition, one of our goals has been, right now this is kind of gone into a cold storage, is to couple the atomic dipole moments to plasmonic nanostructures, also use optical field that's enhanced near nanostructures to create optical trapping potentials to transfer these atoms into those potentials, so that you can get interatomic spacing which is much smaller than what you can get in standard optical lattices. In optical lattices, the lattice spacing will be of the order of half a micron, whereas here, if this works, we made the structures, but we have not yet tested it. Tested the trapping, is that you can go down to distances which are smaller than 100 nanometers. And one can do many body physics in completely different regimes of tunneling rates and so on. The fourth program is on using matter waves to do optics. Okay, like for example, interferometry with matter waves. Like this picture depicts, these are images from a camera of real wave packets, which are split, like a Mach-Zehnder interferometer, you see the wave packet is split into two different paths, and then you recombine them and look at the populations, look at the interference, and build atom interferometers. Now using such an interferometer in a configuration where the wave packet falls vertically down under gravity, one can actually build a Mach-Zehnder interferometer to measure gravitational acceleration to extremely high degree of precision, up to 8th or 9th decimal place. And then it has many, many applications which I will tell you, which I will cover in this talk. The recent addition to the lab has been the development of a ion trap quantum computer, and this is one of the directions, this is one of the deliverables for the National Quantum Mission, where we have promised to deliver a more than 50 qubits ion trap quantum computer. And these images that you see here are fluorescence from individual ions. So each of these dots is a single ion fluorescence, which are trapped and laser cooled in a linear Pauli trap. So you can see up to 25 ions we could trap. And the qubit transition that is used in these systems is, again, there are choices of using either a microwave transition or an optical transition. We are using an optical transition, very narrow optical transition, whose line width, whose lifetime, the excited state lifetime is about a second or so. So it, yeah.
So will you have all-to-all coupling here when you?
Yeah, we will. So that's the goal. I mean, we are now, right now, optimizing gate operations, and then we had some breakdown in the experiment, so we are rebuilding it, not rebuilding, we are setting it up again, the vacuum chamber. So what you saw here, these blinking dots, for example, are quantum jumps. So when you excite to the clock, when you excite the qubit transition from ground state to the excited state, on an auxiliary transition, you don't see any rapid scattering of photons on an auxiliary dipole transition. The excitation of the clock transition, the qubit transition is on an electric quadrupole transition, which is much more difficult to excite than a dipole transition. Anyway, and okay, you see all kinds of strange structures also, and there is a lot of physics that one can do just by looking at these phase transitions between different structures. Anyway, today I will focus my talk on this part here, which is connected to using Bose-Einstein condensate for different things. Okay, so some of the initial slides are very elementary. I was not sure about the spectrum of audience, but so all the elementary particles can be put in two buckets, bosons and fermions. And if you look at what all exists, then you see that you have electrons and you have photons, which fall under two different buckets, either the fermions or the bosons, and then there are many more fundamental particles which fall under these two categories. So if you look at the bosons, down here are photons, which mostly we all work with, or we work with atoms whose total spin is an integer multiple of h bar. We don't work with fermionic systems, we only work with bosonic systems, and I thought it would be an apt place to give a talk on Bose-Einstein condensate today here, because even BEC is almost the prediction of Bose condensate is also again close to about 100 years now. Okay. So yeah, we all know this. Most of us know this here, that these two particles, the fundamental distribution that these particles obey, the occupation of these number of particles in a given energy interval, we know that they follow these two fundamental distributions, the Fermi-Dirac distribution and the Bose-Einstein distribution functions, right? And if you plot those distribution functions, they have a very peculiar characteristic differences. So the Fermi-Dirac statistics at zero temperature is like a step function here, whereas the Bose-Einstein statistics shows you that as you decrease the temperature, you have the occupation going to as high as possible. And this comes out because of the fact that your particles are either distinguishable or non-distinguishable, and so on. So to simply put it, if you have a basket or some kind of a potential in which you want to put these particles, then you know that bosons can occupy the lowest energy level. All of them can go to the lowest energy level, whereas fermions will not do that. They will only, the pairs of fermions will occupy different possible states in that particular basket or a potential that you would like to put these particles in. And this is what, in this particular state, is something very miraculous that happens, and that's where you get a Bose-Einstein condensate. Now, just to simply put it, simplistically looking at it, what happens is that when you have at very high temperature, the particles' velocities are so high that the associated de Broglie wavelength of these particles is very tiny compared to the extent of the size of these particles. Now, as you keep reducing the temperature, then the de Broglie wavelength keeps increasing, and it becomes, waves start overlapping with each other, and at one particular and below a particular transition temperature, all of them kind of interfere, something like a constructive interference, and become a massive wave function, okay? And that's where you get a giant matter wave. Now, this was predicted by Einstein based upon the statistics that Bose gave for photons, which Einstein extended it to particles also, and specifically for all these particles with integer multiples of spins. And the first paper was published in 1924, which was basically Einstein had communicated what Bose had written to him in German, and he got it published. Basically, what Bose did was, in order to get the Bose-Einstein statistics, the Bose-Einstein statistics comes from the way, when Bose dealt with photons, he derived the Planck equation completely from the statistics, counting statistics of the particles. Unlike what Planck derived the Planck distribution from a hypothesis that he had made, right? So there was a big difference, and this attracted Einstein, and he extended it to all the particles, and that led to the Bose-Einstein distribution, Bose-Einstein statistics, and the Bose-Einstein condensate. Now, a lot of interesting things happen when you look at bosons when they go into this condensate phase, right? Now, one of the things is superfluidity. This is a very interesting phenomena. These are, this earned the Pierre-Capizza Nobel Prize, and this was because when you have a mixture of helium-3 and helium-4, helium-3 are bosons, fermions, and then they kind of, it was predicted that they kind of pair up and become like, they behave like bosons, and it goes into a state where all these bosons go into a superfluid phase, and there is a mixture of superfluid and normal phase in these liquids. And this, if you have a pure, if you go into the superfluid state, then you see interesting things like your liquid will start flowing without any friction through any orifices, or it can even climb the containers of a wall and it can overflow the container. Other thing that happens is like in solids, superconductivity. Electrons, fermions, they pair up, they become bosons, and then they flow through the system under the application of an electric field without any without any loss of energy, and it leads to superconductivity. And for example, if you look at this plot, so this is a resistivity versus temperature. So if you look at the plot for mercury, so Kamerlingh showed that there is a sharp phase transition in the resistivity at certain temperature below 5 Kelvin or so, which is basic, I don't remember the exact number, and then the resistivity completely falls to zero. It's not only just about resistivity, but the way this current behaves, it's like a supercurrent in superconductors, and then it will lead to things like the Josephson effect and those kind of things. Now, all those things that I showed you were in natural systems, in a kind of a not so pure systems, okay? So there are a lot of things that go on inside the superconductors and superfluids. It is very difficult to understand exactly what goes on. Even now people are working on superconductivity, trying to understand how superconductivity takes place in the first place, and so that it will allow us to design materials that can work as a superconductor at some reasonable temperatures, so that we can use them for practical applications, which is basically the holy grail for so many people going after trying to discover new superconductors which can work at close to room temperature or even at room temperature. So this is a big dream. Now, the problem with all those systems is, as I said, they are kind of dirty. We don't understand a lot of things. So people had a dream of creating this Bose-Einstein condensate in the laboratory using pure systems like atoms. And the initial efforts went on into basically using spin polarized hydrogen gas and using cryogenic techniques to confine spin polarized hydrogen gas and then try to make a Bose-Einstein condensate. But those efforts completely, they put a lot of hard work for about two and a half decades, but nothing moved forward. It only led to a lot of complications into the system. Parallelly, there were efforts that were being developed in cooling atoms, not by cryogenic techniques, but by using lasers. So what exactly happens is that you use photons to transfer momentum to the atoms and the atoms will absorb these photons, re-emit them, and basically in the absorption and re-emission process, you take away the kinetic energy of the atoms, and then if you have a collection of atoms where you subject them under vacuum, you subject them with laser fields in such a manner that with proper frequency tuning and all that, you can go to a regime where you start reducing the temperature of these atoms down to several millikelvins or even fraction of a millikelvin, and there are additional techniques where you take these atoms from fraction of a millikelvin to fraction of a microkelvin, thereby realizing situations where scenarios where your phase space density of the particles goes beyond 1 and you can go into a Bose-Einstein condensate state. Now, in that direction, before this Nobel Prize was announced in 2001, the techniques that were developed for doing all this to achieve very low temperatures with atoms. When I say laser cooling of atoms, we are only talking about a maximum of 1 billion or 10 billion atoms, as opposed to the Avogadro number scale atoms that we have in macroscopic systems, where there is enormous amount of cooling power that is required, and it is very difficult to go to millikelvin temperatures or sub-millikelvin temperatures. Although people have these dilution refrigerators and all, which can take you to several tens of millikelvins, and there are even more advanced cryogenic techniques like adiabatic demagnetization and all that, which allow you to go to microkelvins, but they are extremely complex techniques which only work with certain things and so on. In this case, using lasers, all these three people and many other people, they developed techniques to reduce the temperature of atoms using the force of light, basically. And there are a lot of details that people worked out over a decade or two, which led to techniques that made possible to cool atoms down to temperatures of the order of 100 nanokelvin or so, where you can put them into compress them to a phase space density that goes beyond 1. When I say phase space density, it's basically number density times the cube of the de Broglie wavelength of those particles at that particular temperature. So this was the first image of a Bose-Einstein condensate made in the lab artificially, and this was with rubidium atoms. What is shown here is a surface plot basically of the density of atoms, integrated 2D density of a cloud of atoms when you take the temperature through the phase transition. So this particular distribution is of a thermal cloud of atoms. So these atoms are typically held in some kind of confining potentials. Either it could be magnetic fields or laser fields, focused laser fields. And if the temperature of these atoms is below the transition temperature, they are in a thermal state. And when you release this cloud from the trap, the cloud expands symmetrically. Whereas as you go through the phase transition, suddenly the density peaks in the center, and then the atomic density shoots up very rapidly as you go through the phase transition, and there is a small thermal fraction. And then when you are completely deep below the transition temperature, then there is no thermal fraction of atoms. There is only the condensed phase of the atoms. This is the parallelly when this was being done, even in MIT, there were efforts going on with sodium atoms. But there is another story to this. There was even earlier effort that started in Paris with John Dalibar's lab using cesium atoms. They were very unlucky at that time because the techniques that are used to lower these atoms, lower the temperature of these atoms, they rely upon the physics of scattering of these atoms, because there has to be a good ratio of elastic collisions versus non-elastic collisions. And for their bad luck, cesium had, in those days, there was very little knowledge about all the molecular potentials which are involved when you have atoms colliding with each other. So it turned out that, of course, after a lot of hard work, that they realized that these cesium atoms had a very bad collision channels, which led to non-elastic scattering and loss of energy, thereby didn't allow them to go through go below the transition temperature. Anyway, so sodium and rubidium, they were the lucky atoms at that time, although the MIT group saw it a little later than the Gila group. But what actually these people, what they did, although they saw it a little later, they did a lot of experiments that basically repeated whatever was seen in superfluidity and superconductivity using this collection of Bose-Einstein condensate. For instance, they saw interference of two Bose-Einstein condensates. It's like two matter waves, coherent matter waves, which have definite phase. When you merge them together, there is an interference. They saw that. And some other group, the Paris group, they switched over to some other atom and they also got Bose-Einstein condensate, and they also did some more experiments on that. Now this particular picture is an extraction of pulses of Bose condensate from the reservoir, which is like a pulsed atom laser, you can call it, atom laser in quotes. It's a coherent equivalent of a laser that you see for light with matter waves. Now, the last one, what I said about this atom laser, this is an experiment in our lab itself. So there is a Bose condensate which is made, and then you extract coherently a stream of atoms from that. So this long strip that you see here, it is actually a beam of coherent beam of atoms coming out of a reservoir of a Bose-Einstein condensate. Now, if it were not a Bose condensate and if it was just a thermal atomic cloud, what would happen is these atoms, they would just immediately spread as they fall down. Whereas in this case, because it's a coherent matter wave, it comes as a very sharp streak of atoms, and when you let this atomic beam, coherent atomic beam, interact with the standing wave of light. Standing wave of light is like a grating for atoms, whereas in case of light waves, we have physical gratings, which are basically slits, right, through which we send light and light will diffract. So this is in a regime called as Ramannath regime, where the diffraction, as you can see, the diffraction pattern, it follows Bessel functions, which is basically a result of the Ramannath regime, the diffraction in the Ramannath regime. So you have a trap where you have a condensate and then you release those, you extract the atoms by combining magnetic fields and the gravitational potential and so on, and let the atoms spill out of the trap and you get a beam of this coherent atom. So this is another thing that the MIT group did, was observation of vortices inside a condensate. Now, you know that when you put a superfluid inside a bucket and you rotate the bucket, if it were a normal fluid, this is how the atoms of the fluid would rotate. Whereas in case of superfluid, you will form vortices inside this, and it's a result of some quantization, principles in superfluid. And this is exactly what they have seen using a Bose condensate made in a lab. So you take a BEC, you make the BEC, and then you spin it with a tweezer or something, with a pair of tweezers. You spin it very rapidly and you start seeing minimizing the densities of the atoms in the cross section when you image the cross section of the condensate. Very interesting experiments that people later did with this condensates is that, with this superfluid, is that they mimic the physics that goes on in solid state systems in terms of various phase transitions, like conductivity to conductor to an insulator, and one of the famous transitions is this Mott insulator phase transition, and this was demonstrated by a group in Munich, where they took this superfluid and superimposed a three-dimensional lattice potential, optical lattice, which basically creates potential wells in three dimensions. The way it is created is that you when you take one standing wave, you create a sinusoidally varying potential, like you will create disks of potentials. When you have two intersecting standing waves in orthogonal direction, you create potentials which are like cigars, and you bring in the third pair of standing waves. These cigars will turn into small ellipsoidal packets inside a three-dimensional structure. Now you superimpose that on a Bose condensate, Bose-Einstein condensate, and what happens is that as you increase the strength of the trapping potential, by increasing the strength of the trapping potential, you can vary this J and U. Basically, the depth of the trapping potential will decide what is the tunneling rate from one point to the other. No, sorry, the on-site interaction, because you're making the potential very steep. And by changing this rate, and by changing the potential well, you control the ratio of J and U. By doing that, what they have shown is that they could see a transition from a superfluid state to a localized state. When you have these particles localized in the sites, the phase fluctuations are very large. But when the particle is delocalized in a superfluid state, the phase is very definitive. Exactly, that's what happens. So when the phase is very definitive, then you see this in the Fourier plane. When you expand it, it's like an X-ray, X-ray diffraction. So you expand the cloud from this three-dimensional optical lattice, you see this very nice X-ray diffraction-like pattern, very distinct pattern. So you go from a superfluid to an insulator state. So when you have a superfluid state, when you have an insulator phase, there are very large phase fluctuations, as I said, and you get in the image, the interference basically just vanishes. Whereas when you are in a deep, in a superfluid state, then there is a very well-defined phase. So you go from that to this. So this was it was a milestone experiment, which basically allowed people to think of doing, come up with different types of such Hamiltonians, which condensed matter physicists are interested in, to understand real systems, and you can actually test them using such systems. So you can use this as a simulator. Oops. Okay. I think I should go really fast. 8 minutes, yeah. Okay. So other thing is Anderson localization. So when you take a condensate and you put potential which is kind of random, which acts like a disorder, you can see that the wave function exponentially localizes in that. And in our lab, we use this condensate and simulate a kicked rotor system, which basically is the physics of Floquet dynamics, in the sense that you have a perturbation which periodically varies. In this case, there is a standing wave optical lattice which is periodically turned on and off, and then this system acts like a system which is called as a kicked rotor, where a particle is constrained to rotate on a circle which is periodically pushed. And this leads to a lot of different physics, including dynamical localization. The earlier one was a localization in physical space, whereas in this case you get to a situation where the momentum distribution gets exponentially localized. So these are the experiments that we do, and the setup looks like that in the lab. There are so many lasers and vacuum systems and all that, and this is the thermal cloud, and this is a pure Bose-Einstein condensate. Now we have atoms, and then we trap them in crossed optical dipole traps, which are basically focused laser beams, which are very far away, detuned from the atomic transition. Transfer those atoms into this dipole trap and do an evaporative cooling, and then we get into a regime where the phase space density increases beyond 1. So the typical sequence is you start with 6 laser beams and a superimposed anti-Helmholtz magnetic field. trap the atoms in this, cool them to a few fraction of a millikelvin, then either transfer them into a magnetic trap created with some configuration of magnetic coils, or an optical dipole trap, but there are some other traps also. We have used both. In our first experiments, we used a magnetic trap. Now we use a crossed optical dipole trap. And then in that trap, you transfer these atoms where initially the phase space density is of order 10 to the power minus 6. Now you have to go to more than 1. So what you do is that you put them, you cannot use light anymore to cool these atoms, because any scattered photon is basically giving a kick to the atom. So there is an equilibrium that you reach, and you can't go below that temperature. So the way it is done is you trap them in some configuration, either magnetic fields or in dipole traps, and you slowly lower the trap depth, thereby allowing the higher energy atoms leaving the trap and lower energy atoms basically and the remaining atoms colliding with each other and rethermalizing. So imagine if you had a Maxwell-Boltzmann distribution and you keep cutting the tail of the Maxwell-Boltzmann distribution, meaning throw away the atoms from the tail, the remaining atoms collide with each other and rethermalize to a lower mean temperature. So you keep doing this, you lose about 3 orders of magnitude in number of atoms. So from a billion you come to a fraction of a million, but your temperature, your phase space density increases by 6 to 7 orders of magnitude, and evaporative cooling, the forced evaporative cooling, and you get a BEC. So this is a short animation of how all that is done in the lab. So you start with a rubidium metal here. In our case, it's rubidium. You heat it, and you generate an atomic beam, which is at about 400 meters per second in the beginning, and you shoot an opposite laser beam and slow that velocity of the atoms from 400 meters per second down to 20 meters per second in this region where you have the 6 laser beams which capture those atoms and create a sample of about 1 billion atoms at a few hundred microkelvins. Then this is an animation of the earlier version, so we have a magnetic trap. So these atoms are spin polarized, which means you use laser beams and some optical pumping mechanisms to spin polarize the atoms into one particular momentum F level. And then what you do is, now there is no light, you put radio frequency and flip the spins, and the flipped spins, the atoms whose spins are flipped, they leave the trap. The remaining ones rethermalize to becomes colder and denser, and at some point you get a Bose condensate, and you measure it by dropping it, in the sense you turn off the trapping fields, and since the trapping potential is ellipsoidal, the ground state wave function takes the shape of the trapping potential. Now in the direction where the trapping potential is stiffer, there the uncertainty in the momentum of the wave function is larger. So it expands more in that direction than the other direction. It's because of the uncertainty principle, basically. Now then, that sample of atoms you can use for a lot of things, all these things that I showed in the beginning. We used one of such experiment was to build an atom interferometer. So you take the wave packet. For matter waves, the optical elements are basically formed by light, whereas for light, the optical elements are material objects like any mirrors and beam splitters that you use. In this case, you use standing wave pulses, and you engineer the frequency of these lasers and the phase such that you transfer the momentum of the photons onto the wave packets, and you can split the wave packet into different momentum states. So this is undeflected wave packet, the deflected wave packet, and then you use another pulse. 3 pulses will make you build a Mach-Zehnder interferometer. Now why atoms? One of the applications is that Sagnac interferometer. If you had light and you build a Mach-Zehnder interferometer and rotate this table, as a function of rotation rate, there will be a phase shift in the 2 paths of the light that come and merge at this beam splitter, and you see fringes. This phase shift is proportional to this area that is enclosed in this interferometer. and the rotation rate. If you use atoms instead of photons, just because of the rest mass of the atoms being very high, the sensitivity, theoretical sensitivity enhancement that you get is of order 10 to the power 11. However, as opposed to the fiber laser gyroscopes or fiber ring lasers, fiber gyros, the area that you get is very small. So overall, the sensitivity can be increased by 4 to 5 orders of magnitude, not 10 to the power 11, just for practical reasons. Then these interferometers can be used to do extremely sensitive detection of gravitational fields, magnetic fields, electric fields. Just because atoms have mass, they can have magnetic dipole moment, they can have electric dipole moments if you put them in the right state, and so on. So we have used it to build a gravimeter, which is basically a device that measures your 9.8 meters per second square down to so many digits. People have shown up to 9th decimal place. And once you have such a device, and this is an absolute gravimeter, unlike this suspended mass gravimeters, they have to be calibrated every now and then because they rely upon the spring constant of the spring. In this case, you don't have to do that. It's an absolute gravimeter. And that can be used for a lot of interesting things. Like you can, if you put a gravimeter and continuously measure G over a year or so, you can tell whether the underground water table is increasing or decreasing. That's one application. If you measure differential gravitational acceleration over some distance and move it around, you can also detect underground tunnels, for example. So those are all the applications. And this is an example of the interference pattern that you get in a Mach-Zehnder interferometer. Basically, you measure the number of atoms in the two different paths of the beam splitter. And the way it is done is, for measuring gravity, you take the wave packet. You can also do this with thermal atoms, but thermal atoms will allow you only certain fall distance. Whereas if you take a Bose-Einstein condensate, you can also drop it over many meters because the cloud doesn't expand at all. So you drop it, you apply this pi by 2 pulses when the wave packets are falling down, and then you merge them in the final beam splitter and measure the population differences, and you can get a nice interference fringe, which is proportional. So the laser pulses that you use, the phase has to be, yeah, I'm done. The laser frequencies have to be swept in such a manner that they have to keep track of the phase shift that the wave packets gather as they are falling down. So by matching that phase shift exactly with the laser frequency sweep rate, you can actually sit on one of the minima of the fringes, and then you can measure continuously the G. Now, in our setup, we demonstrated up to here, but we are building a transportable version where we are targeting to go here. And yeah, my collaborators, thank you.
Thank you. Thank you, Professor Umakant, sir. Being an experimental optics person, I would like to give you another 1 hour or 2 hours. But since the time is limited, and I'm sure our optics group will invite you a couple of times more to hear on this BAC.
Thank you.
I'm sure Nirmal, yes, right? Yeah. Yeah. Now the talk is open for questions. Yeah, please.
So, the experiment you did in your lab about diffraction, is it diffraction of light through condensate?
Condensate is diffract. The atomic, the beam, the coherent beam of atoms is diffracting from a standing wave of light. Other way.
So you have a condensate.
I have a condensate which is a reservoir. Then I extract stream of these atoms from the condensate.
Yes.
And that beam of atoms is a coherent beam, unlike a thermal beam. It has extremely narrow velocity spread in.
How are you doing? Means you are separating atoms from the condensate, you are saying?
Yeah, so what you do is that you have this harmonic oscillator, harmonic potential. Then we apply a magnetic field which is like that, the effective the total potential becomes like this. So it kind of tilts. The harmonic oscillator tilts along the side of the gravity, and you have the atoms leaking out of the trap.
I see.
And that's the beam that comes out.
So is there any theory behind that? You have a spectrum with, so you have initially one K and then you have series of
Yeah,
K.
so the Raman-Nath diffraction theory, which you apply for light diffracting of a standing wave, of density wave.
At what temperature you have done this?
So these atoms are below 100 nanokelvin.
I see.
Hello, sir. Thank you for enlightenment. I have one question. Is it possible to trap two different atoms and correlate simultaneously Bose-Einstein condensation?
Yeah, people have trapped different species, created molecules of these two different atoms, and created Bose condensates of that. You can also have two different species, not in a molecular state, but one can be a condensate, the other one can be fermion, one can be boson. All kinds of things are possible to do.
Simultaneously we can correlate?
Yeah, simultaneously you can do it in the same trap.
Thank you.
So, in the Bose-Einstein condensate, you got the vertices is quantized. My question is why the vertices is quantized, and when you plot a figure, the quantized vertices having some patches, in patches there are some dots. Why the shape it looks like?
So, I mean, I'll tell you how much ever I understand. So when you rotate the superfluid, the phase becomes singular at the center. So the wave function, if you write the superfluid wave function and then integrate it along a contour, you get a you get a singularity at the center, because of which those dots that you saw, the black dots, there are no atoms there. That's why when you take an absorption image along the direction of the rotation axis, you see those dots there.
Means the circulation is quantized.
Yeah.
But the dotted, why dotted is comes in the figure?
Because that, so you don't have a possibility of a superfluid existing at that point. Yeah, here at these places, you don't have a possibility to have the atoms there once you start rotating everything.
Yeah, since we are running out and then we have the plenary talk next, okay, let us thank Professor
Thank you
Mokar
very
for
much.
this exciting
Thank
talk.
you.
May I request Chair to kindly present a memento to Professor Umakandi
Thank you
Rapol.
very
Going to invite you other.
Yes.
You are going to be last day on our university.
Thank you. Sure.
We now move to plenary lecture of the day, and the session chair will introduce us with the speaker.
Hello. Yeah. Yeah. The next talk is the plenary talk by Professor Samitra Sengupta. He is a distinguished theoretical physicist. He obtained his PhD from Saha Institute of Nuclear Physics, Calcutta. As a faculty member, he has served at Presidency College, Calcutta, Jadavpur University. He has been working as a senior professor in the Department of Theoretical Physics at IACS since 2008. He works on various areas of physics, in particular extra-dimensional theories, string theory, supersymmetry, supergravity, branded phenomenology, cosmology, and black holes. He has more than 150 publications to his credit. Now I request Professor Sengupta to give his talk on quantum mechanics in the gravitational background. Thank you.
Okay. Okay. So it is so nice to be here. I mean, I very sincerely thank the organizers for inviting me to this wonderful meeting. I missed the first couple of lectures because I came late, but I can see the very vibrant environment in this auditorium. The topic that I will try to discuss, I will not get into very complicated calculations, anything. I'll just do some simple calculations to show some of the most important aspects of the unifications of quantum mechanics and gravity, namely the quantum gravity issues. And I guess that though I missed the talk, Professor Majumdar has discussed few things about it in the morning session. So let me give you a kind of, it's a storytelling I would do, but little bit of mathematics in various places. So we all know the gravitation was first proposed by Newton, and he formulated the force of gravitation in terms of the inverse square law. And all of you know this from our school days, that this is the famous Newtonian gravitation, where the product of the two masses and the inversely proportional to the square of the distance. And this proportionality constant, namely the Newton's constant, has a very small value, and therefore gravity is generally a very weak force, and unless the masses are very large, it is not very relevant in our discussion. So in the domain of particle physics, you have seen that the speakers who are discussing about particle physics, they are not talking much about gravity in most of the cases. But we all know that when we deal with big masses, the gravity play a very important role. Now, Newton's law very successfully described planetary motion, we all know. But according to Newton, gravitational field acts instantaneously. That means, that is, if you move this mass here a little bit, instantly this will feel that this mass has moved. Now this, in a sense, contradicts Einstein's special relativity, that no information can propagate faster than speed of light. So this is a problem. But it worked as an approximate theory. But what Einstein did, Einstein put forward a revolutionary idea that there is a connection between geometry and force. So this is revolutionary in the sense that if you look into Newtonian paradigm of science, we have a force in one side and the dynamics in the other side. So once we know force as an independent entity, it determines the dynamics in a space-time which is given. But what Einstein showed, that the force, the other side of the equation, that is also nothing but a part of that space-time itself. So he actually pointed out this in the context of gravitational force, but if I get time, I will talk about this in the context of other forces as well. Now Einstein's viewpoint was, instead of Newtonian concept of action at a distance between the two objects at a distance they are attracting, Einstein came out with a brilliant idea. He said that we all know that the Euclidean geometry satisfies this what we learned from our very early school days, the sum of the three angles of a triangle 180 degree, the shortest distance is a straight line, circumference is 2 pi r, but these all work for a particular kind of geometry called Euclidean geometry. For example, if you take a kind of football, say for example, and draw a triangle, if it is a convex surface, the sum will be greater than 180. If it is a flat, it is equal to 180, but if it is a concave surface, it will be less than 180. These were known to mathematicians for a long time. But what Newton taught us the space-time is actually perfectly flat, Euclidean-like. A body travels along the shortest path in straight line in space and time, that is suppose some x equal to u into t, that is a straight line equation, in absence of force, and that means there is no acceleration. This is basically Newtonian paradigm.
But in curved line, it travels in a curved line if there is a force in space time, because say suppose something, you have released something from your hand, it is going down, apparently it is moving in a straight line, but it is a straight line in space but not in space time, because the path is x equal to ut plus half gt squared, which is a parabola in space and time. So basically Newton taught us that it will travel in a curved line in space time when there is a force. So that means this curved line implies acceleration. So this was Newton's laws of motion. So this is basically the idea, that no force straight line, this is a curved line, though I cannot draw time axis, but this is a curved line in the time axis. Now Einstein said that instead of thinking it like this, assume that the space time has curved and a body that travels along the shortest path, the Newton's first law of motion, that is the travels along the shortest path along a straight line, that remains. But what is new is that the geometry is curved and therefore it travels along the shortest path, but which is now a curved line. So presence of mass energy curves the space-time geometry, the shortest distance is now a curved line, giving the illusion of acceleration in flat space and hence the existence of a force. So this is the kind of basic idea that Einstein taught us. So force originates from curved geometry. So force is a kind of, it's a artificial concept, basically from curved geometry, writing down everything, we will be able to say this. You may ask why the mass or energy curves the space-time? The answer is the mass of energy curves the space-time. The question should be put in this way, that is the definition of mass and energy which can create curves, change the geometry. So this is the definition of mass and energy. Remember, in Newton's law, you do not have any definition of mass, because an equation force is equal to mass into acceleration contains two unknown quantities, force and mass. You cannot define two quantities from a single equation. So mass was a kind of that, whatever that inertia means, but the quantity, now this theory tells you the mass and energy is that property which changes the geometry. Now in flat geometry, in flat Euclidean like geometry, a quick summary of that suppose there are 2 points x, y, z and x plus dx, y plus dy, z plus dz. The distance between them is this. This is our old Cartesian coordinate geometry that we learned in our school days. But this result is strictly true for flat space. If the space is not flat, then in a curved space what happens, these coefficients which are 1, 1, 1 in this 3 distance, dx squared, dy squared, dz squared, this coefficient becomes some 1 plus some function of x, y, z. So they deviate from that 1. So in a curved space time, the distance where the coefficients are never 1, 1, 1 in any coordinate, that's, if it is always 1, 1, 1, that is flat geometry, and if it is deviates from 1, 1, 1, then it's a curved geometry. Now then Einstein said, but since we know that, as Newton thought that these coordinates are different for different events, but there is one universal time, but Einstein said time is also with respect to an event as a coordinate. So an event is described with respect to 4 coordinates, we all know the special relativity. So he defined the 4-dimensional distance just to generalize this. Remember, they are just a standard generalization, but with a minus sign here where others were plus, the difference of sign. This was important because this guarantees that the speed of light remains constant in a flat space. This minus sign would guarantee that. So this is the invariant distance. Now this coefficient, which is no longer 1, 1, 1, they define what is called the metric of the space-time, and from this metric, which of course these functions f1, f2, f3, f4, few tensorial quantities were constructed. We all know about this. These tensors, they define the curvature, the extent of curvature of the space-time, which measures the curvature, and if all f1, f2, f3, f4 0, then these curvature functions are 0. So then Einstein wrote his equation, a very famous equation, one side geometry, other side matter and energy. That was the first time in history that
that the strange equation geometry and matters are connected, and this coefficient, which is a kind of, you can assume that the geometry has one unit, matter has another unit, it's a quantity which connects the dimensions of the equation. It turns out to be proportional to g, the Newton's constant, and it should appear because we expect that in some limit the Newton's law of gravitation should emerge, because that was very successful. So, mass energy curved space-time, particle travels in a curved line, and we imagine that there is a force called gravity, and this was general theory of relativity. These are the 5-slide summary of general relativity. Now, of course, we all know that whenever we write something, we look for an action principle, some Lagrangian formulation, and this is the action of a gravity action. If you take del S equal to 0 variation, then it leads to Einstein's equation. Now, test of Einstein's picture. So, now what we have to do, you solve, suppose we solve Einstein's equation, the equation that I wrote here, with say the mass of the sun in the any matter, a spherically symmetric matter in the right hand side, and we get this solution, and this mg, they all appear because in the limit we want to have Newton's law back, and we get this expression, and you see this is not a flat space clearly, because the coefficients in a flat space should be dr square minus dt square plus r square d theta square plus r square sine square theta d phi square in polar coordinate. But now you see they have deviated from 1, and this implies that the space time is curved. And see, interestingly, this curvature actually is the Newtonian potential, what Newton thought to be potential. It is proportional to the Newtonian potential. Now, this geometry for a spherically symmetric mass was constructed by solving Einstein's equation, and you can see if the mass is equal to 0, then you get back your flat space geometry. Now, what you have to do, find the shortest path, which is called geodesic, find the shortest path for a planet, and it turned out to be an ellipse. Now, this is interesting because we all know that Newton also proved the Kepler's law of planetary motion by inverse square law. So, whom to believe? So, the thing is, Einstein said that, but this theory predicts something little more. According to Newtonian theory, if you have a sun here, if you have a planet here, there is a solution is an ellipse by inverse square law, and this is the ellipse. After full 1 year, it comes back to the same point. But according to Einstein theory, after second year, it goes to this ellipse. Then the major axis of the ellipse gradually rotates. And from Einstein theory, the angle of rotation for the planet Mercury, what was turned out to be roughly this 100 years. Of course, this is a very small amount. It needed a lot of developed experiment to measure this, but this matched with experimental data, and also Einstein theory predicted very nicely the bending of light because of the curvature of the space-time. So, I am not getting into details of this, but what I am trying to say that the space-time curvature leading to the explanation of the gravitational force was firmly established. Now, with this, very quickly I give a summary of what are black holes, because that will be relevant for the rest of the discussion. So, basically when a star collapses due to its own curvature or gravitation, because it has mass, it becomes very dense, and space-time around it can become extremely curved, so that when light comes to so curvature is, of course, the closer to the object, it is more curved. So, it becomes so curved that even light cannot escape, and it goes inside. And in fact, you know that when there was an estimation that when the mass is roughly twice the solar mass by Chandrasekhar, that such a black hole will form, or by your misfortune you go inside, then you are forever in. You can, with the rest of the universe, you are disconnected. So, recall for a mass m in the geometry, this was our geometry, and for r, the distance 2gm, the sign of the coefficient of dr square and dt square is reversed, and as a result, actually it can be shown. I am not going into details, but since this becomes plus, this becomes minus. So r can, just like time, r can move only in one direction, just as you can only move in the future of time, or I mean if you could go to the past of time, but just r can change like time only along one direction, and therefore any object once inside r equal to 2 gm, which is called the horizon, it can go. So you can solve the geodesic equation for a particle, and you can explicitly show that once the particle is inside 2 gm, it can never turn. So this is a simple calculation. In fact, you can just do it in the back of the envelope. It's simple calculation. So we find that this behaves like a black hole, that it swallows everything when something comes to a distance from it called the horizon. So once inside r equal to 2 gm, anything even light can travel only in one direction, and all paths converge to the origin r equal to 0, and which is a dangerous point, because at that r equal to 0, you can see from the looking at this that everything diverges. So that is called what is a singular point. So it goes to the singularity. No calculation is possible there. So it is called the horizon radius of black hole. Question is now, I am coming to this meeting is on 100 years of quantum mechanics. So is black hole really black? So when I say that you solve the path of a particle in this geometry and you show that it will inevitably go in, even light, then black hole is black. But if the particle is a quantum particle, what will happen? So let us try to understand the behavior of a quantum particle near the horizon of the black hole. So as you can see, this was our geometry for spherical symmetric matter. At r equal to 0, there is a singularity, everything diverges, but that is expected. Why? Because we all know that the mass is roughly, you can imagine it like this, that the mass is sitting at the center, and you are actually r equal to 0 means you are hitting the source, and if you go to the source, the thing will diverge. Even for Coulomb's law, q square by r at r equal to 0, everything diverges classically. But r equal to twice m, there is nothing in twice m. Suppose this is my black hole, r twice m is some distance from here, there is nothing, this is just a space. But then why it is diverging? Because this term you can see becoming 1 by 0, that is infinity. A metric component blows up, the physics breaks down, but why? There is no reason. There is no matter, nothing there. The reason is, it is because of wrong choice of coordinate. Actually, it will not diverge. So you can appropriately change your coordinate and do the calculation, you will see r equal to twice m is perfect. R equal to 0 you cannot remove because that is real singularity. But r equal to 2m, it is this kind of coordinates called Schwarzschild coordinate, the way you are writing it, spherical polar coordinate, it is diverging. So you can change your coordinate and you can choose any coordinate because the theory is coordinate invariant. You can go to some appropriate suitable coordinate where everything is fine. So change coordinate, there is no singularity at r equal to 2m, and then you can do your calculation in that coordinate. So let us see what happens. It's a very simple way I am trying to show you what is called Hawking radiation. At horizon r equal, so let me take g equal to 1 because 2 gm, Newton's constant, equal to 1 in some appropriate unit. So take horizon is r equal to 2n, capital G1. The metric coefficient becomes singular. Consider a point very close to horizon. So you are, suppose there is a point and you consider sphere r equal to twice m, it's a spherical surface, just very little outside. So 2m plus, I have written it like this just for some calculation and advantage, x square by 8m, where x is a very, very small quantity. So I am sitting just outside the horizon. 2m plus this, where as x goes to 0, your r goes to 2m, that is you are going towards the horizon, just outside the horizon. Then what you do, you substitute this in the expression of in this expression. And when you substitute this, you find this, where you neglect the higher powers of x because x is very small. So when you do that, you see you get this expression where this quantity k is, I have written k equal to 1 by 4m. So there will be some m here, so I have written it like this. So this is a constant 2 sphere. This is 2 sphere with this 1 by 4k is some kind of radius. And this is the by two-dimensional quantity dt square dx square. Angular part is now just a two sphere. This is the problematic part which was there, which was diverging. Now near horizon, two-dimensional space-time is like this. Now how do I get rid of that apparent singular behavior? So what I do, I play a trick. Remember, in two-dimensional to flat space, which of course flat space has no singularity, d square is dx square plus dy square cut in Cartesian coordinate, and d square the same thing. If you substitute x equal to r cos theta, y equal to r sin theta, this becomes this, which is in the polar coordinate. And this is the polar coordinate in flat space. There is no singularity. In flat space, there is no question of singularity. What I do, I make a coordinate transformation. I change t to it. If I do this change, then what happens? This minus sign I can absorb, because this minus 1 means I square, so I can take one it and another it. So what I do, I write that it to be theta, and this coordinate now, this metric now becomes this. Now you would say this looks very similar to this one. If I identify my k theta to be a periodic coordinate like angular coordinate, so I have done a coordinate transformation. There is no singularity, it is looking like a flat space with radial coordinate x and k theta is that angular coordinate which I wrote previously to be theta, now it is k theta. So previously theta has period 0 to 2 pi, if you remember, theta was 0 to 2 pi in the polar coordinate in 2 dimension. Now k theta has the period 0 to 2 pi, means theta has the period 0 to 2 pi by k. Obviously k theta is period 0 to 2 pi, means theta is 2 pi by k. Fair enough. So this is my, in this coordinate if I do my calculation, there is no singularity, I have gotten rid of singularity by this coordinate change. What is the cost? Cost is, consider a quantum theory near the horizon. Now take a Schrödinger equation of a particle, take it to the close to the particle, and all of you know this equation, hi equal to I h cross d psi dt. You know that this can be written as psi t is e to the power minus I h cross integral h dt into psi at t equal to 0. In other words, this is the evolution operator which takes psi from t equal to 0 to t equal to t. This is our famous evolution operator. So this is the operator which takes us along the time axis. This is basically Schrödinger equation. Now I find that how the system evolves. This tells you at t equal to 0 if this psi, then what it would be at psi at t equal to t, and that is the way we calculated the entire time dependent perturbation theory, everything that you did. Now I now want to do this calculation, but now I have to change my coordinate appropriately, because in near the horizon my relevant coordinates t dot t but it equal to theta over a full period. I do this integration, take h to be constant for simplicity, something like energy. It is just a kind of simple way to show this. Now see this integration gives you this evolution operator becomes t becomes it and integrate from what is the period of theta was 2 pi by k. So the result is e to the power minus 2 pi hk, which looks so similar to Boltzmann factor e to the power minus e by k beta t, where this T which I am identifying as a temperature to be Hk by 2 pi into Kb, where Kb is the Boltzmann constant, K was 1 by 4m, if you remember I wrote K to be 1 by 4m, and H is the Planck's constant. So I find, what I find, this temperature is called Hawking temperature. What I find, the horizon of the black hole in a singularity free coordinate exhibits a thermal character with a characteristic temperature T is this. And this presence of H clearly indicates that this is a quantum origin. This is not a classical, this does not have a classical origin. So Hawking temperature clearly decreases because I have substituted the value of K to be 1 by 4m. So in the Hawking temperature is H by h pi m Kb. Now Hawking temperature decreases with mass of the black hole. So as mass increases, the Hawking temperature decreases. Now take a typical twice the solar mass, because that Chandrasekhar taught us that in order to form a black hole you need mass. It has to be sufficiently large mass so that it can condense, it can collapse into a black hole. If you substitute in this formula where K, you know the value of the Boltzmann constant, Planck's constant, the temperature turns out to be nanokelvin. Now the problem is that you are then saying that in the sky we have black holes whose Hawking temperature is this. But the problem is, all of you know that we are living in a background ambient of cosmic microwave background radiation, which is close to 3 degree Kelvin, which was emitted at the time of the, the huge heat wave that at the time of Big Bang, whose still that reminiscence of that at the temperature 3 degree Kelvin filling the entire universe. That is well known, that has been discovered, the Nobel Prize has been awarded for that. But now therefore all the black holes are sitting with a much lower temperature, because 3 degree Kelvin is much higher than nanokelvin, and therefore it is very difficult to find any radiation coming out, because it is sitting in a higher temperature. So what to do? You may say that if we can have a black hole with a small mass, then the Hawking temperature will rise. But if the black hole has a small mass, then black hole will not form. So what is the solution? So as the black hole swallows mass and energy, everything is going inside the black hole, its temperature decreases. It's a very strange thermal object. It's a negative specific heat. And more it swallows, its horizon area keeps on increasing, because horizon area is twice same as the radius of the horizon. As m increases, everything going inside the black hole, horizon area increases and becomes, because as m is in the denominator, as the black hole swallows mass, its mass increases and therefore temperature goes down. So it has a negative specific heat. It is taking mass and energy basically, and then its temperature decreasing. And the more it swallows, its horizon area of course keeps on increasing, and just like entropy. Now you may say that what is the meaning of all this? After all, we have a mass and we have a curve geometry. Suddenly what this thermal thing talking about? Because we know in the back of our mind that when you talk about thermodynamics, there is a background statistical mechanics. There is a microstructure. What is the microstructure here? There is no matter. There is only one mass sitting at the center. But this, therefore, now we get a new vision of space-time. Space-time has a microstructure. Apparently, we do not know what it is, and therefore huge research started from different directions. One direction from string theory, other direction from loop quantum gravity by Professor Majumdar. I don't know whether he has talked about it, and there are many other directions to understand what this entropy, what this temperature, what is the meaning of this. However, this is a simple way to show that this thing is appearing, and so the entropy of the black hole, which is identified as the area of the horizon like this, and you can also find these quantities have similar relation among themselves, just as laws of thermodynamics. So these are, this is the angular momentum of the black hole. So they find a similar kind of expression which we encountered in thermodynamics, but in terms of the parameters associated with the black hole. Is it just an analogy, or there is some deeper truth in it? Or some people say this thermal description is more fundamental. Space-time is an emerging concept. So quantum mechanics brings out some fascinating result about the classical gravity that Einstein taught us. Now, one thing we need to say, before going inside the black hole, the objects have definite information. I am going, the computer is going, the bottle is going, everything is going. But finally, a definite information about their character. So it's a very ordered state. Who are going? Due to its temperature, what is coming out from black hole as Hawking radiation, because it is a thermal object, so it will radiate, is just a thermal disordered radiation like Boltzmann distribution. Or maybe Bose-Einstein, maybe Fermi-Dirac, all have been shown. So it's a completely disordered. So from ordered state to disordered state. Therefore, there is a loss of information. So it's interesting that whatever has gone inside, they had some knowledge, but what is coming out, those energy which has gone inside, what is coming out as Hawking radiation, completely disordered. There is a loss of information. How to understand this? To understand this, see quantum mechanics comes to your rescue. So if you deal with fermions, it gives exactly the Fermi-Dirac distribution. So you get appropriate what kind of particles are coming out, and you can show the calculation that I have shown is a very simple calculation, but a details calculation. What is done is slightly more difficult, but then there you can show that if it is a boson, for you get appropriate Bose-Einstein distribution. For fermions coming out, you get Fermi-Dirac distribution. So you get some parameter associated with the black hole called gray body factor, but otherwise the distributions are like this. No, if it emits boson, it exactly follows the bosonic. So I am assuming, suppose the black hole is emitting bosonic particles, then it will maintain the bosonic Bose-Einstein distribution. No, it is, we cannot predict what it will emit, but what I am saying, that suppose I take a black hole geometry, see, try to understand, this is a geometry, right? It is not really, it is coming from the horizon, right? Horizon is empty space, just empty space. So black hole is this table for a sphere. So here is the horizon from a distance. And then from the horizon, you are assuming the particles are coming out, and assume that when you are doing that calculation, that they are the bosonic particles which are coming out, and then you will see that that geometry will produce a kind of radiation which follows the typical Bose-Einstein distribution. Okay, let me carry on, I will just tell you about this, okay. Okay, so in quantum mechanics, all of you know, transition amplitude when we learn from initial state to final state by a operator which is called S matrix, or basically it is the evolution operator from initial state I to a final state F. All of you know that this is basically that say psi at t equal to 0 to psi at t. So initial state evolving to final state by this evolution operator. Now you can see that if H is a Hermitian operator, then this S is a unitary matrix, because if take dagger, so you find S dagger equal to S inverse if H is Hermitian. Now what is the meaning of this? Consider what is the unitary rate of SB. Suppose you consider a transition probability, transition amplitude is F as I written, I to F is this, but what is probability? You know, this is mod square is the probability. Now mod square, when writing the probability, it is ISF, and it is the, when you take the dual, this F S I. So this is the basically transition probability from I to F. Now if I tell you that transition from I to any state, that is not I to some particular state, but all possible state, and I know the complete information of all F. These are the all possible states. Then of course sigma of P I to F from all F has to be equal to 1, because total probability has to be equal to 1, because these are all the possible states. You have complete information of all the states. So if F forms a complete set, and if you take a summation of this over all F, then you know that this ket F bra F summation over all F gives you identity operator. And you know this will give you I S dagger S I, and which is equal to 1 means S dagger S is unitary. So S dagger S unitary is related to the knowledge that if I go to F state and all state are complete informations are known, then S will be unitary. Now this means if no information is lost, then S dagger S is 1, that is S is unitary. But in this case, near black hole, the S has lost its unitarity. I have showed you that this operator, because of that integration, that it looked like a Boltzmann distribution, this is no longer unitary, even if H is Hermitian.
But if you do weak rotation,
What weak rotation? This is my evolution operator, and my evolution operator is this. I have estimated my evolution operator, and this has lost its unitarity. And therefore, since it's lost its unitarity, But there is no question, because that is the way I have gone to a singularity free coordinate. I have to go to a singularity free coordinate. You are not allowed to do any calculation, right? That is the whole idea. Okay. Now, so the information is lost. So this is, see how interesting that the entropy concept that I discussed is related to some information loss which is manifesting itself by showing that the S has lost its utility. So, of course, question, what are the microstate associated with the black hole? What is the statistical mechanics? What is the microstate of empty space? Microstates on horizon. Horizon doesn't have any particle. This question is one of the most important questions that people are searching around. So instead of semi-classical theory, so why I call it a semi-classical theory, try to understand, we have taken only gravity to be classical. See, we have taken classical gravity and particle to be quantum. Such theories are called semi-classical. So it is believed that instead of semi-classical theory, we must consider a quantum theory of the full system, and we need to know quantum theory of gravity, which may give an answer to this, because you have done a semi-classical theory. All of you know, when you did your semi-classical theory, like an electron which is quantum and the electromagnetic field is classical. We did this in our quantum mechanics class. It gives us some interesting results in terms of transition probability, but it doesn't give us a complete result till you do quantum electrodynamics. You quantize the electromagnetism itself, but therefore it means you have to have the quantum theory of gravity. So what is the problem of quantum gravity? Let us try to quantize gravity in the usual way. So forces between two particles are exchange of some particle. This is the picture of quantum field theory. So if you take a field like electromagnetic field, you quantize the theory, you show that basically this tells you that you can forget about those fields, these are exchange of particles called photons. So when two electron repels, they exchange a photon, basically. Now, and this is called the quanta of force, and appropriately we define the quanta of various forces. So these, accordingly, the Feynman formulated various kind of processes, that how two particle goes to another two particle, and it may straight by exchange of a photon it can go, but then it can there can be some virtual intermediate states, it can jump and then it can go. So there are various possible things happen, and people do at the perturbation theory that various order you can get different kind of internal process, where the initial process and final process are same, initial and final states, but internally many things can happen. And total probability is the sum of all these probabilities. Now, quantum aspect of gravity. For gravitation, the space-time curvature described by the metric is g mu alpha is a fluctuation of geometry about the flat space-time. In other words, we all know that the flat space is just everything is 1, 1, 1. I taught you 1, 1, 1 minus 1. It is eta symbolically. And then my curvature is given by a small fluctuation, which is I defined by a field H, defined by a field small fluctuation. You know that in quantum field theory, the fields are often visualized when you do perturbation theory as a small fluctuation about the vacuum. So it is a small fluctuation about the flatness is this. And for dimensional argument, we find, since we have only one constant, Newton's constant in the theory of gravity, you can write this as root g, then it is dimensionally perfect. Now, take a scalar field theory. Now, a scalar field theory, all of you know the kinetic term gives you del mu phi, g mu alpha, sorry, there is some typo here, so forget about this, d mu alpha, del mu phi, del alpha phi. This is the kinetic term. Normally you write at del alpha phi, del alpha phi. Do you remember? Because g mu alpha is the flat space theta mu alpha, and therefore it gives you just del alpha phi, del alpha phi. But in presence of gravity, you get this. When you get del mu phi, the flat space part, and this gives you the interaction of the gravity. This phi you should come here, somehow has gone down. So root g h mu alpha, del mu phi, del mu phi. So if we substitute for g mu alpha this you get this term, and this is the interaction, and this fluctuation is called the graviton. So Feynman taught us that this vertex H phi phi will have two phi vertex. There are del mu's, there will be momentum dependent vertex, and there will be one graviton exchange, and this is the coupling constant, root g is the Newton's constant. So what is the diagram? 2 phi phi comes, 2 phi comes and 2 phi goes by exchange of a graviton. So phi phi going to phi and exchange of a graviton. This is h mu nu. If you calculate the amplitude of this following Feynman diagram process, you get it turns out to be E squared times g, where E is the center of mass energy of this process. Now the fun is that in the I work in the unit h equal to 1, c equal to 1. Mind it, there will be some hc also. 5 minutes. Okay. So where E is the center of mass energy, so E is the so you can then immediately say that quantum effects of gravity is relevant at energy scale. E is of the order of 1 by root g, because if E is less than 1 by root g, then this you can neglect this term. This term will be less than 1, because this is the term which is proportional to this. So in my perturbation theory, higher powers will be more and more negligible. But if E is of the order of this, then it will be very large term, because this will be equal to 1. You cannot neglect it. And this, if you put the value of Newton's constant, this turned out to be 10 to the power 19 gigaelectron volt, which is the famous Planck energy. So Planck energy actually comes from here, which tells you that at this energy, you cannot neglect the quantum effects of gravity. But you know that our present energy scale, even at LHC, is only TeV. So we are only at 10 to the power 3 GeV, far away. Okay, 10 to the power 4 GeV. Okay, I give you one more round. Okay, fine. Okay. Can ignore quantum gravity effects. Okay, I can give you one more. 10 to the power, no issues. Okay. So, but the problem is quantum gravity is that if you consider the next loop diagram, this loop diagram, I am not going into details. This loop diagram is divergent diagram. This leads to singularity which cannot be avoided. This leads to absolute infinity, and which cannot be renormalized by redefining the parameters. Some of you may have heard about renormalization theory. So unlike electromagnetism, electrodynamics, this theory can never be renormalized, and therefore you are in a mess, because you cannot say that I will ignore this loop effect, because you are not allowed, because if this effect is much larger, if it is infinity blowing up. So this is the problem of quantum gravity. Now I just covered one thing here. If I have more space, see the fun. Now suppose I have more space. I have already seen in 4-dimensional gravity is fine, we understand. Hawking gave us some idea, but that's a semi-classical theory. Full quantum gravity is a problem. But extra dimensions, the new theory of gravity, there are more space dimension. Even for Newtonian level, you can show that the force will be not gmm by r squared, but gmm by r to the power 2 plus d, where d is the number of extra dimensions of space. Now you can prove it by just using Gauss's theorem in higher dimension. But the question is, why do I think, where are the extra dimensions? If they are invisible, why they are invisible? The argument is that, suppose there are 2 dimensions, and as the universe expands after Big Bang, suppose one dimension suddenly starts curling and kind of, so suppose this is my xyz, so this is my xyz, this vertical one, and this horizontal one is my extra dimension. Then if it curls up, then after some time it becomes a cylinder, this xyz is along this, and this is my extra dimension. At every point in my xyz 3-dimensional space, I have circular extra dimension. And if the radius of the circle contracts gradually, becomes a small radius r, then we are living on a 3-dimensional universe, and we are not being able to penetrate this small length, because if the length of this becomes so small that we cannot probe it by our energy, then that dimension disappears from our eyes. So even if there is small dimension, so our force is g5, 5-dimensional Newton's constant r to the power 2 plus 1. If we cannot enter the fifth dimension, that extra dimension, then that extra one dimension you have to replace by the radius, because we are actually sitting on the radius of that extra dimension. We cannot go inside. Then you see, you get back your old Newton's law that you should, because you cannot enter the extra dimension. So GMM by R squared, only if identify higher dimensional Newton's constant by R equal to the fourth dimensional Newton's constant. And it can be shown by a little bit of calculation. I'm sorry, I don't have time. Already I have been given an ultimatum. So this is that you can choose this appropriately, so that G5 is large even though our Newton's constant in our universe is very small. So Newton's constant, if you somehow can go inside that extra dimension, the Newton's constant become a large gravity becomes strong force. It's no longer a weak force. And if gravity becomes a strong force, then the microscopic black holes will form. Now a tiny black holes will form. And therefore, tiny black holes may form. These tiny black holes, since they have a small mass, they have high Hawking temperature, and these tiny black holes should radiate. And there are a couple of, though not so, no positive results so far, there are a couple of detectors in LHC which try to look for the detection of Hawking temperature. If the two proton beams, they raise to energy where they can probe inside, get inside the extra dimension, they will form tiny black holes. Very tiny, extremely tiny, so tiny that they will start radiating and they will evaporate. It's called black hole evaporation. They'll, so it depends on how much energy. Suppose if it happened at the TV scale at the LHC scale, LHC have TV energy. So if you change, it can go up to 10 to the power minus 20. Am I right, Manush? TV scale in the unit of length scale is 10 to the power minus 20 roughly, right? 10 to the power minus 20 centimeters, something like that. Planck length is 10 to the power minus 33. That's very far. That is very far, right? Okay, so let me, and sorry, just last one thing and then I'll conclude. That's it. Consider a two-dimensional world. So I have this extra dimension. If you have a free particle px square plus py square, you know E square equal to p square c square plus m0 square c4 in relativity. m0 is 0, suppose massless particle. So you have E square equal to px square plus py square. Now see the fun. So free particle wave function, all of you have written so many times in your life, wave function of a free particle. Now suppose one dimension has compactified, that extra dimension, it becomes circle. Then after going 2 pi r, you are coming back to the same point, therefore you will demand psi xy equal to psi x plus x comma y plus 2 pi r. So y plus 2 pi r is the same point as y because it is circle. If you substitute this in this expression, you find py has to be integer by r. And if you now substitute in the expression of energy, what you get is very interesting. This where n is any integer. So what you have shown that energy of a massless particle when one direction is compactified and you are lying only in one direction, it generates a tower of particle called Kaluza-Klein towers. So what you will see, suddenly you will see that there are so many particles, you don't understand from where they have come. Actually they have come because one dimension is compactified and they have generated this tower. The values of kk masses depend on the choice of R, of course. This is also being searched in Collider, that in the various scattering process where the Kaluza-Klein particles can be detected for extra dimension. But why you are doing it? Because of a simple reason that we can see that whether we can detect Hawking radiation, that is some effect of quantum effect of gravity. So also find both gravitation and electromagnetic force power. I am not going into details of this, but we can unify both gravity and electromagnetic with extra dimension. And extra dimensions, you can say this is not only our thoughts. If someone believes in string theory, then it is natural in string theory. String theory tells you about extra dimension. It has to be there. So thus we find quantum mechanics and gravity, that is curve geometry, together in 4 and higher dimensions brings out many, many novel ideas. I have just, because of shortage of time, I have so many other things I could share with you because it's a very fascinating area, this quantum aspect of geometry. So, but I'm open to question now. Okay, thank you.
kept your talk at the end. He knows very well that he can hold all the students to the chair. Not a single student has moved. So thanks a lot, Professor.
Thank you. Thank you.
Now the talk is open for questions from the student. Yeah, come. Next time.
So it is not, so you can imagine that when the black hole swallows everything, so its mass increases, and but nothing can go out of the black hole unless you bring in quantum mechanics, right? So nothing can go out. So if the mass increases, what is the horizon radius? Twice m. You remember that? Therefore, if m increases, horizon radius increases. And what is the area? 4 pi r square. So in this process, black hole is such an object where horizon area can never decrease. Temperature is dependent on that is true, but I am saying that whether you agree with this, that black hole is an object where the entropy will always increase because everything goes inside, correct? So this is an irreversible process. So therefore we identify that with this. There are other arguments also to show that how the entropy concept, because of the equations that I wrote, those equations you can write in the form of a thermodynamical equation when you identify that to be entropy. But physically try to understand, you have identified now a irreversible quantity, that is the area of the horizon, which can never decrease. And you heard in your thermodynamics class that the entropy can never decrease in a natural process. So therefore this identification.
It can be possible, entropy will be increased, but horizon area will be constant.
Horizon area in the context of black hole thermodynamics. In the context of black hole thermodynamics, whenever something, what is the process? Process is something crossing the horizon of the black hole. That is the process. You have to understand what is the process. Process is particles are being exchanged, right? So when something goes inside the black hole, then the horizon area always. Now you are a question, what I would like to answer you, that suppose something going, black hole is emitting. So then the horizon area may decrease, if you may say the mass is decreasing. What happens then? Suppose black hole is evaporating out. Then what happens? Then the horizon area decreases, the black hole entropy decreases, but what is going out, that's the entropy increases, the total entropy of the universe always greater than or equal to 0. Answer, right? Okay.
So, when a black hole starts spinning, you must have heard a ringularity also forms. Sometimes.
Right.
So when a ringularity forms, how is it related to temperature and what properties change?
Now see, where does it form? Imagine that doesn't form near the horizon, right? That forms, that ring singularity absolutely inside. Do you remember that calculation? So we are talking about this thermal behavior in the context of the horizon. Okay, so the ring singularity that you are talking about, that forms much inside the horizon.
Okay.
So it is the horizon of the black hole whose thermal character we are discussing.
And sir, can a black hole get so small that Heisenberg's uncertainty principle starts acting on it?
Yes, that is true. Even, do you know that there is a theory called generalized uncertainty principle, which I haven't never worked. It tells you that suppose there is this point particle, assume a point particle, but even a point particle has a black hole radius 2 gm, right? And a point particle being point, it has no dimension. So by this definition, all point particles are black holes, correct? Yes. But black hole with horizon radius so small that we normally cannot go close to that. But your question, if I can somehow go so close to the point particle, then we enter into the horizon of the point particle.
Yes, sir.
Then uncertainty principle will change. Do you understand that? Because it has to.
Yes, sir.
Then people wrote down that xpx is no longer IH cross, the commutator, it is IH cross times function of p.
And so what is p?
P is the momentum. So with the momentum which we are approaching, the function of p. And then what they did, as a result, Schrödinger equation got changed, because Schrödinger equation that you wrote depends on the Heisenberg principle. So in that new Schrödinger equation, they solved the particle in a box, all problems. Those, they show there's a modification. So there's a huge literature, the people who are working in generalized uncertainty principle. If you are interested, I can send you some references. I'll send you. It's an interesting subject, yeah.
As you've talked about the information laws, can I relate the information laws of black body by using Rolls-Landauer theorem of information laws?
In case of black body, of course, information is lost because it's emitting thermal radiation, and it is manifested through the increase of entropy, right?
Yes, yes.
So when a body emits, the entropy of the universe increases. That is true.
Okay.
You are absolutely correct. Yeah.
No, I had one question regarding the thermodynamics, because when we are talking of thermodynamics, in some sense, intrinsically you are saying things are in equilibrium, right? Meaning when we are...
Not necessarily.
No, meaning I'm saying, for instance...
Yeah, so basically, sure.
Thermodynamic laws,
Yeah, sure. So,
there is this
yes.
detailed balance, right?
Right.
When we are doing this, it seems to not be that, right?
See,
Absorbing kind of state. So
right, but we are assuming that they are very close to some equilibrium state, and slowly some energy packets are getting emitted from horizon. It is not that it is emitting, but try to understand one important thing, that suppose you have a black body, or suppose you have some black body, an ordinary black body, it is emitting radiation. Can't you say that in the whole process the entropy of the universe is increasing? Yes or no? Right? So the question is that what we are saying here, if you want to justify that those equations that we wrote, they are close to the equilibrium points, I mean some small quasi-static states, some change of energy dm, change of mass by dm, when I write change of mass of the black hole by dm. So a black hole, then I put dm inside, then as a result the entropy change by this amount, the area change by this amount, those are close to incremental changes from equilibrium states. But even if it is not equilibrium, then also it is increases. Yeah, Parthuda, you want to answer something? Yeah.
Yeah, just Sudipto's question. Actually, what you said is okay, but not exactly the whole story, because you can look at Hawking radiation, which is like spontaneous emission for atomic systems. But in addition, there's also super radiance, which is like stimulated radiation, stimulated emission. And the two together, it has been shown, can actually lead to another idea, I mean, resurrection of the idea of detailed balance. Okay.
Notion that we have a Boltzmann wave.
Yes.
That requires some kind of detail.
And moreover, these things actually come from a full, what Soumitra did not discuss is a full-fledged theory of gravity.
That is not possible here, I mean,
So it is there, right? So it's not something that is outlandish in that sense. So a detailed balance may be thought about, even in this situation.
But super radiance or suppose this
like
kind of process,
emission,
So those are, those are simulated. So just like you throw a stone inside, right. So those are, sure. But Hawking radiation is some kind of spontaneous emission.
Hawking radiation is more like
spontaneous emission.
If I say that, we can have more questions during the dinner time, I'm sure most of them are going to be sitting here and having a questions to you. Okay. So, one last question, anybody? Okay. Yeah. Okay. Huh? Okay. He has been asking a long time.
Actually, I was waiting for a long time. The session was very wonderful, and it was very deep conversation happening. Maybe as a physics student, I'm not able to get what you're saying. But in between, you said that the small black holes people are trying to make.
Yeah.
As a curiosity, I'm asking.
Trying to make in the sense, if there is extra dimension, and we can get into the extra dimension, as a result, the Newton's constant rises, that can create the tiny black holes. That's the statement. It's not that if there is no extra dimension, we cannot create it. Will not be. So you can say that our extra dimension size definitely not at the length scale of LHC which has probed, because no tiny black hole has been formed. But that does not mean it cannot be generated at a higher energy scale.
What if we make a sufficient black hole which can suck all the things that we are having? For example, Earth.
No. So do you know what happened when this was shown? Do you know, in CERN, there were a lot of court cases that this tiny black hole may come out of the tunnel and they will swallow everything in France and Switzerland. I mean, so there were many quotes. You have seen that paper, Barthoza, that then they released a paper, they wrote a paper that if such a black hole forms, they will be so tiny, they will radiate, Hawking radiation will be very high because high temperature, it will evaporate so fast that before it comes out of the tunnel, it will evaporate. And then the people got happy that they will not be swallowed. Otherwise, people thought that that black hole will come out and the next house, it will take everything, that everything on the street, they will take everything.
Okay. Thank you, sir.
Last question.
Last question. What is the meaning by flat space-time in simple words?
Planck space-time.
Flat space-time.
Oh, flat space-time means okay, so let's first say flat space. Let me tell you flat space. Where you learned Euclidean geometry, there are some axioms of Euclidean geometry. Shortest distance between 2 points is a straight line, right? So that defines flat space. So the exact definition will be, if I ask you to write the distance between 2 points, x, y, z and x plus dx, y plus dy, per dz, then there will be at least one coordinate system, at least one, which is called Cartesian system, where you can write the distance to be dx squared plus dy squared plus dz squared. If you cannot write this, you search for any coordinate, but all possible coordinate, but you cannot arrive to a single coordinate where it is in this form, then I'm coming to that. Now suppose, go to space-time. Now in flat space-time is a space-time where so dx square plus dy square plus dz square is the invariant distance, right? And which is basically invariant under a 3-dimensional rotation. Now a flat space-time which takes care of two things. One, Einstein's one assumption that laws of physics should be invariant from one inertial frame to other inertial frame, right? That is special relativity number one statement. Second is speed of light is invariant from one frame to another frame. In order to maintain these two, the kind of transformation that you have is Lorentz transformation. Okay. So a flat space-time, a Lorentz transformation everywhere in the space-time globally keeps this quantity I wrote, dx square plus dy square plus dz square minus c square dt square, this quantity invariant. So a flat space-time defines which remains invariant globally under Lorentz transformation.
Okay. Yeah. Now we are running very late. Let us thank Professor Sengupta for an exciting talk.
Before we conclude session 4, we would like to express our sincere gratitude to the chair of this session, Professor D. Narayana Rao, for efficiently chairing this session. May I request Dr. Abhiram Suri to kindly present a session. And I request Professor Narayana D. Rao to give away the certificates to best poster presenters.
So there are best poster awards in optics, condensed matter physics, and high energy physics categories. So the first, one of the recipients of this best poster award is Bijay Kumar Sahu. Another awardee is George C. Reggie. Another award goes to Gummadi Arun Prakash. optics. And another award goes to Vedant Kumar Deka. Another award goes to Dilip Kumar Upadhyay. Yeah, so one more award, it goes to Somdeep De.
All right, so this is how we conclude session 4 of day 1 of 100 years of quantum mechanics. Dinner will be served shortly outside the auditorium. Thank you all, and we look forward to your participation again tomorrow.